Hey everyone, I hope you're all doing well. Are you curious about how audio files retain information about the audio they captured, where that information can be used at a later time to play back that audio? Are you curious about how 24-bit audio samples or 32-bit floating point audio samples work, what their internal makeup consists of, what they represent, and how they're used for audio playback? Would you like to see a simple Python program that generates an audio file where you can gain insight into how a program might create such a file, where you can actually look at a program that's writing samples to a file, where you can play back that file and hear the sounds that they create, where that can put you in touch, in a sense, physically with what's actually going on there? And who knows, maybe from seeing something like that, you might want to write your own Python program to process an audio file for your own purposes, or just for fun to learn about how it works. Have you wondered how you might calculate the average level of an audio file and use that level to compare it with the average level of other audio files? Or to use that ability to create noise floor recordings where you can compare one with another? If you're curious about any of those things, then this video series is for you. In this video series, we'll cover the following topics. The first part of this video will cover some fundamentals. It's basically an introduction or refresher on decimal, binary, and hexadecimal. And that'll include a refresher on fixed point and binary point, along with custom binary encoding schemes. Part 2 of this series will be an introduction to audio samples. The topics included will be how audio samples are captured into digital format. This includes an introduction to the 24-bit signed integer format, or what we might refer to as the format for the 24-bit audio sample. 32-bit floating point, aka Float32 or binary 32, or some people know it as IEEE-754 binary 32. We'll go into that format in detail, including some examples. And when we get into binary 32 or Float32, we're going to get into the bits and bytes of it all. We'll go over some exercises so you can grasp the magnitude of the 32-bit float format, so you can understand the size of the numbers it can represent. And we'll go through an example of recovering signals which exceed the clipping point, but because they were recorded in 32-bit floating point, the signals are ultimately retained and can be brought down into a range where they're not clipped. We'll go through an example of that, and we'll compare it to some of the limitations that are encountered with the other ways to avoid clipping, and relating to situations where the signal actually is clipped. In the third section, we're going to get hands-on with some walkthroughs. The walkthroughs will include using Python and packages that are very popular with Python to process audio. This includes Numpy, popular audio packages, and other packages which can help us create a .wav file or a .wav file, which is an audio file, and we'll create such a file in the 24-bit signed integer format, as well as the 32-bit floating point format. We'll even use a Python program to create some graphs of these audio files. We'll actually look at hex dumps of an audio file, both in the 24-bit signed integer format and the 32-bit floating point format. And we'll touch a little bit on the file format standard, which defines the format of the .wav, .wav, or .wav file. In the fourth part of this video, we'll cover averaging an audio signal. We'll learn about root mean square, or RMS, and we'll use Python tooling to extract statistics and information from audio files so that we can compare those audio files and their average signal levels, or average RMS. The techniques used in that section can be used to actually compare noise floor samples that you take within your own environment. While everyone is encouraged to join and watch this video series, if you have a little bit of Python experience, a little bit of programming experience, if you understand binary a little bit, all of those things can act as a nice foundation for the content in this video series. If you are already familiar with binary and hexadecimal, or if you're not interested in a quick recap, feel free to skip ahead to the next section. So before we get into the primary discussion, let's review the number systems. So that would be decimal, binary, and hexadecimal. We're going to be using these number systems, especially the binary system and hexadecimal, in a lot of the discussion that's coming up. So the decimal number system is one that we're all familiar with. It has 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And when you reach 9, it wraps back around to 0. But what happens to the 10 that we just counted? Well, we increment the place over to the left of the ones place that we're in. So the tens place would get a 1, and then we count again. The idea of the decimal number system is that all symbols, 0 through 9, can be used in a single place, and that you can't wrap around from 9 back to 0 without incrementing the place immediately to the left of the one that you're currently in this case, the ones place. If the place immediately to the left is already at 9, then it itself can't wrap around to 0 without also incrementing the place to its left, and so on and so on. You will see that regardless of the number system, whether it's decimal, the one that we're very familiar with, or binary or hexadecimal, all of those number systems have a set of symbols that will fit into one single place within that number system. When the highest symbol for a particular place is reached, it never wraps around to the first symbol without first incrementing the symbol to its left. Each number system might be referred to by its base. So the decimal number system might be referred to as base 10. The binary number system would be referred to as base 2. The hexadecimal number system would be referred to as base 16. So one useful interpretation of this base nomenclature is that the base number, like base 10 in the case of decimal, indicates the number of symbols available for a single place. So for base 10, there are 10 symbols available for a single place. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are no other symbols available in base 10 for a single place. Each place will have one of those symbols of the 10 which are available. The other number systems we're going to discuss here are no different. The binary number system, or base 2, has a total of 2 possible symbols that can be in any given place. Those symbols are 0 or 1. You won't see any other symbols in a single binary place. Each place in binary will either be 0 or 1. And then you have base 16, which is hexadecimal. Hexadecimal has 16 symbols available for any one place. Those symbols range from 0 through 9, and then you have A, B, C, D, E, F. So that's 0 through F. Or when translating that to base 10 or decimal, you might say 0 through 15. So the hexadecimal number system is base 16 because it has 16 possible symbols that can be used in a single place at any given time. You'll never see any other symbols than one of those 16 in a single hexadecimal place. So let's compare these number systems. Here's 3 decimal digits, and we can count from 0 to 9. When we reach 9, we wrap back around to 0, but as part of wrapping back around to 0, we increment the place immediately to the left, or the tens place, by 1. And that would give us what we know as 10. And then the ones place can continue incrementing from 0 back up to 9 again. When we count from 0 to 9 again and reach 9, we wrap back around to 0. This time, again, we increment the digit to the left, or the digit in the tens place in this case. And so we would increment it from 1 to 2, and that would give us 20. And then we continue incrementing from there. When we reach a point where both of the first 2 places, and in the case of base 10, that would be the tens place and the ones place, each have the maximum symbol value, which would be 9 and 9, or what we refer to as 99. When we reach that maximum value of 99, the same sort of thing happens again. The first place, or the ones place in the case of base 10, would wrap around from 9 back to 0. That would trigger incrementing the place to its left, which in the case of base 10 is the tens place. The tens place would wrap around from 9 back to 0, and as part of doing that would increment the place to its left, which in the case of base 10 is the hundreds place. And since you're familiar with the decimal system, you can see that continues on here. And in this example, we count up to 255 or 255. Now let's show binary and decimal together. So as we increment decimal here, we're going to show the equivalent binary value. Since binary can only use the symbols 0 and 1, we see that the two numbers look very different on the surface. But the quantity they represent is the same. So a 1 in binary is a 1 in decimal. A 2 in binary is a 2 in decimal. But a 2 in binary is represented by 1, 0, whereas in decimal it's represented by the symbol 2. That's because the decimal system can hold the number 2 in a single place. The binary system can only hold 0 or 1 in a single place. If it wants to represent 2, it has to use another place, in this case the 2's place. Remember, binary is base 2, so each place can only hold 2 possible symbols, 0 or 1. That's why the places are named differently for binary. You have the 1's place, the 2's place, the 4's place, the 8's place, and so on. One way to look at these places is that if there is a symbol in a place, it indicates that many of the value of the place is part of the value of the entire number. So in the case of decimal, if you have 1 in the tens place, it means you have 1 10. If you have 2 in the tens place, it means you have 2 tens. Well, the binary system is no different. If you have a 1 in the binary 2's place, it means you have 1 2, meaning you have the value of 2 one time. So if you have 1 1 in binary, that would be 3, a value of 3, because you have 1 2 and 1 1. There's a 1 in the 2's place, so that's 1 2. And there's a 1 in the 1's place, which means you have 1 1. And that might sound confusing, but just remember, binary is either 0 or 1, and 0 and 1 are both very well suited to represent digital signals, either electronically or even in conversation when talking about numbers in relation to software engineering or digital electronics, and so on. That's why you'll very often hear the use of binary and or hexadecimal in software or electrical engineering discussions. We'll get to hexadecimal in a second, but keep in mind that hexadecimal is kind of a shorthand to represent binary digits in a manner where you don't have to write so many numbers down, and they become kind of second nature to programmers and engineers. They look at a hexadecimal number and they kind of know right away what binary bits are set from that hexadecimal number. So as we continue to count up here, and we get to 9, you can see that 9 looks different in binary. Of course, it's 1 8 and 1 1, which is 9. And now we'll increment further up here, and we're going to go all the way to 255, and you'll see that that's equal to all binary 1s. That's 8 1 values. And if you were to look at the name of each of those places, the 128th place and the 64th place, each of those has a 1. So if you add up all those numbers, 128, 64, 32, 16, 8, 4, 2, and 1, the total quantity or value you'll arrive at is 255. Therefore, 8 bits in binary, or 1 byte, can represent the values 0 through 255, and it does that with 8 places, each of which can have the symbol 0 or the symbol 1. And this is binary, or the base 2 number system. And if we bring the hexadecimal number system in here and we compare these as we increment up, we can see a similar thing happen, although the hexadecimal number system has different places. It has a 1's place and a 16's place. In some sense, that means the hexadecimal system is more compact than the other two systems. Decimal and binary each require more places to represent the same quantity that the hexadecimal system can represent with only 2 places. So you can see we've reached the value of 9 in all of these systems here. When we increment to the next value of 10, notice how hexadecimal can store 10 in its first place, in the 1's place. And it does that by using the symbol A to mean 10. So A is 10 in hexadecimal. So the decimal system requires 2 places to represent 10. Hexadecimal requires only 1 place to represent 10. And the binary system requires 4 places to hold the value 10. The value 10 in binary is 1, 8, and 1, 2. That's 8 plus 2, which is 10. Now we're going to count up to 15 here, and notice how the hexadecimal system can represent all those numbers from 10 through 15 in the ones place of the hexadecimal system. The decimal system requires 2 places to represent 15, and the binary system requires 4 bits. Notice that 4 ones in binary, 1, 1, 1, 1, is 15. And if you add up the place values, 8 plus 4 plus 2 plus 1, you'll arrive at 15. When developers see 0f in hexadecimal, they will usually know immediately that that is equivalent to binary 1, 1, 1, 1. Other relationships between hexadecimal values to their respective binary values also become well known. It becomes second nature to the software developer or the digital electronics engineer what these relationships are between hexadecimal and binary. For example, I know off the top of my head that A is the number 10 in hexadecimal, but more importantly, I know right away that it's a bit pattern of 1, 0, 1, 0. That is 1 in the 8's place, which is a value of 8, and 1 in the 2's place, which is a value of 2. 8 plus 2 is 10. And there are other bit patterns, like off the top of my head, 64 in hexadecimal is 100 in decimal. How do I know that? Because I've been looking at these numbers over many years, and you just get used to some of the patterns and the values. When we increment one more, we are going to go to 16. 16 in hexadecimal is 1, 0. And we can see in binary it is 1, 0, 0, 0, 0. That's 1 and 4 zeros. Many developers who work with binary and hexadecimal values probably understand that 16 hexadecimal, which is 1, 0 in hex, is 1, 0, 0, 0, 0 in binary. When a software developer sees a binary value of 0, 0, 0, 1, 0, 0, 0, 0, immediately they'd probably think of the hexadecimal value 1, 0. Or at the very least, they would know that's 16. Everybody's going to have their own way of imagining these numbers or using the facilities of their memory and any imagination they have of these numbers in order to figure things out and to understand them and to recall them and to relate them to one another. This is just based on my personal experience, and I have a hunch that most developers who work with bits, bytes, C, C++, assembly, that kind of thing, are going to know right away when they see 1, 0 hex that that's 16, and they're going to know that that's binary 0, 0, 0, 1, 0, 0, 0, 0. And again, there are many other bit patterns which just become second nature because people encounter these things over time, and relating the bit patterns to the hexadecimal values or vice versa becomes second nature for many of the values. And even for values you might not encounter all the time, it's very easy to derive what the bit values will be when you understand a hexadecimal digit. So when developers see 0D in hex, they're going to understand that's 13 in decimal, and they're going to understand that the bit pattern for that is 1, 1, 0, 1. Hexadecimal is kind of this numeric system that helps you deal with binary more efficiently. So you can make your own interpretation for what you like about these number systems, but I'm just sharing my own personal experience and viewpoint. Let's advance now from 1, 0 hex to 2, 0 hex. So if 1, 0 hex is 16, 2, 0 hex is going to be 32. And you'll notice that there is a 1 bit in the 32 place of the 8-bit byte, and there's no other ones. It's just 1, 0, 0, 0, 0, 0, which is 32. And it's very easy to see that when you have 2, 0 hex, that's 2 16ths. And what's 2 16ths? That's 32. So it's very easy to see that 2, 0 is 32. And because hexadecimal sort of encapsulates 4 bits per hexadecimal digit, it's very easy to visualize the first hexadecimal digit being 0 is all 0 bits. The second hexadecimal digit, because it has a 2 in it, we know that the value must be 2 binary in that upper 4 bits. That's going to be 0, 0, 1, 0. So you can kind of see how it's easy to relate hexadecimal to binary and vice versa, especially when you're dealing with values of byte size. The hexadecimal digit divides the byte up into 2 digits, each one going from 0 to 15. And each of those 2 hexadecimal digits, each themselves represents 4 bits of the 8-bit byte. Therefore, if you remember the bit patterns for numbers 0 through 15, and you remember the hexadecimal values for 0 through 15, by just knowing those, you can figure out the bit pattern and hexadecimal value for 2 hexadecimal digits or 1 byte. And you can even expand that out, where you can figure out the bit pattern for 2 bytes, because 2 bytes happens to be 4 hexadecimal digits. So you can see the power in using hexadecimal as a way of looking at sort of a compressed representation of 4 bits of a byte, and how you can then apply that to understanding the hexadecimal digits that make up a full byte, which would be 2 hexadecimal digits. And then you could expand that out to 4 hexadecimal digits, or 2 bytes, or what we would call a 16-bit word, and so on and so on. Now let's increment all these numbers up to 255, which is the maximum that will fit into 2 hexadecimal digits or 1 8-bit byte. And you can see the 8-bit byte is filling up with ones. You can see the hexadecimal digit is 2 Fs, and you can see the decimal value is 255. Here is a single binary digit, and we see how it represents 0 and 1. The question is, how can we get it to represent -1 or a negative number? How about we use a minus sign, just like we write on paper? Well, that's great for human beings when they're writing on paper or on a whiteboard or something, but it doesn't really work in digital electronics because I don't know where I would put an actual physical minus sign, a human readable minus sign. So then maybe we can ask, is there a way for us to use binary to represent negative? Well, in fact, why don't we actually just add an extra bit, and we'll use that to represent the minus sign. With that extra bit in place, we can now count from +1 to 0 to -1. And then we can count back up from -1 to 0 to +1. We're able to represent -1 by using that new bit that we added. When that bit is 1, it's a negative number, and when that bit is 0, it's a positive number. That sine bit, which is that new bit that we added, is used only to represent positive or negative. The remaining bits, and there's only one remaining bit in this case, is used to represent the number. If that remaining bit is 0, the number is 0. If that remaining bit is 1, the value is 1. And whether it's +1 or -1 is dependent on the sine bit. This method of encoding the sine for an integer in the high bit is generally referred to as 2's complement. And we can extend this out to 1 byte, where the highest bit in the byte is the sine bit. When that sine bit is 0, the number is positive. When that sine bit is 1, the number is negative. By adding more bits, we can now represent higher positive values and lower negative values. Let's go through some of the values here so you can see some interesting characteristics with a 1 byte signed integer. Let's start by counting from 0 to 15 and back from 15 down to 0. And as we can see, it's pretty much the same as the way it was before without there being any sine bit. However, even though we don't see any difference when we're counting like this, it's important to remember that the other bits still do have meaning, especially in this case, the sine bit. The sine bit being 0 actually means that we're counting from 0 to 15 and from 15 back down to 0. If the sine bit were 1, we would be doing something different than counting from 0 to +15. All right, now let's take the important step of going from 0 to -1, and let's see what happens. Wow, okay, what just happened here? If you notice, all the bits turn to 1, and that is -1 in 2's complement form. Now, how did we get here? Well, first let's explain this in human terms. Now, if you look at that Wikipedia article, which you don't have to do because we're going to go through one example here, it'll explain how to convert from a positive number into its negative 2's complement form and vice versa. Let's do that with the calculator here with the number 1 right now. So what we do is we start with the number 1 in the calculator, and then we negate that value, which reverses all the bits, and then we add 1, and that will give us the representation for the negative value of that positive number that we started with. If we want to reverse things and get back to the positive number, we can negate the value again and then add 1, and we'll be back at the positive number. So you can see I started at 1, negated the value, added 1, and we ended up at the negative 1 representation in 2's complement form, which is all the bits being 1. I then repeated that by negating all the bits and then adding 1, and I arrived back at the number 1. All right, let's try one more. Let's enter in 50. Let's negate the 50. Then let's add 1, and we'll have 2's complement form for negative 50. Let's negate that. Let's add 1, and we'll be back at the 2's complement form for positive 50. So that's the human way of looking at 2's complement and how to convert between the positive and negative values. If we just step back for a second and look at this byte value and we see all of the zeros there before we decrement and get all the ones there, what we see is we're at the lowest value for the byte. If you look at it strictly from a raw byte standpoint, like an unsigned value, when you're at all zeros, there really is no lower value from a raw byte standpoint if you're looking at it from an unsigned perspective. So the CPU, when it's decrementing from it, it has no choice but to do something, but it can't go to a lower value because 0 is the lowest value. So what it ends up doing is it ends up wrapping around to the highest possible value in the unsigned byte, which is all ones, as we saw all ones. It just so happens that all ones is negative 1. And that's why 2's complement works so nicely here, is it sort of makes sense. If you're decrementing the byte and you're at 0, you end up wrapping around to the highest value that the byte can hold from an unsigned perspective. But for a signed binary value, like in this case a signed byte, that bit space, if you will, below 0, which really wraps around to the highest unsigned value, which is all ones. That bit space gets interpreted a little bit differently when doing signed math and instructions. And you can kind of see as we decrement down here to 15 as an example, we can see a similar thing happens as we begin to use that upper bit space for the unsigned byte, right? So the unsigned byte has all these bits there, and as we decrement down, which is really wrapping around in a sense. But for a signed value, we don't look at it as wrapping around. We look at it as going into the negatives. But from a computer and CPU standpoint, it happens to work out very elegantly and very nicely, where we're just simply underflowing, wrapping around to the highest value the byte can hold, and that happens to represent negative 1, and we continue to use that bit space up there for negative 2, negative 3, as you'll see when we're counting here. Okay, now let's go lower down here until we get to the lowest possible negative number. That's the place where the lowest possible negative number meets the highest possible positive number. Let's go see what happens at that point. All right, it's going down, 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 and here it is at 128. Negative 128 is the lowest possible negative number. And now if we decrement one more, we see that it goes to positive 127. Okay, let's rewind this and go back to negative 128. Now, if you look at negative 128, you can see that there's just one bit set, and that's the sign bit, and that's negative 128. Now, if you forget about signed arithmetic for a second, and you just imagine that you want to take the number 1 and subtract it from that value, that 1 with all the zeros, you can clearly see that there's no way to satisfy subtracting 1 from that unless you borrow from the sign bit, which is all the way over to the left. So if you subtract from negative 128, which is 1, the sign bit, with all zeros, there's no way for that subtraction to be satisfied unless the 64's place can borrow the 1 from the 128's place. So that would make the 128's place go to 0, and then it would make the 64's place have a 1. But then the 32's place would need to borrow 1 as well. And that triggers a whole chain of borrowing that goes on. And that chain of borrowing leads to all ones, as we'll see again as we replay this. So let's replay this and watch that, and you can see it changes to all ones. Now, if you're savvy with your hexadecimal, you'll recognize that this is 7F, or 127. And with 1 byte signed integers, that happens to be the highest integer value, positive 127. What effectively has happened here is we have underflowed from negative 128 to positive 127. But from a raw binary standpoint, looking at it as a unsigned byte, all we did was subtract 1 from the value 1 with 7 zeros. And that subtraction just naturally led from 128, which typically in an unsigned format, that would be positive 128. But a 1 byte signed integer can't use that as positive 128 because it's used as negative 128 because the sign bit is set. And the sign bit kind of dictates how these values are sort of used. And with signed integers like this, the positive side is always shortchanged 1 value. And it's the value at the highest end of its values. So in the case of a 1 byte signed integer, it goes to 127. It can't make it to 128 because that signed bit is not available to it for a positive number, because that would make it a negative number. And that's just the nature of 2's complement signed integers, binary integers like this. So when we subtract 1 from this, we're really subtracting 1 in a sense from an unsigned value that's equal to 128, and it's just simply decrementing and going down to 127. But with signed operations, like in the CPU and whatnot, it's viewed as going from negative 128 to positive 127 in what is an underflow that wraps around from that most negative value to the most positive value. This is a little excerpt for people who are into the assembly language and machine instructions of the processors that you're working with. Now, at least on the AMD/Intel processors, I've seen it on other processors as well, typically you will find this is if you see that there's unsigned operations that are supported by the CPU, which the AMD/Intel CPU architecture supports, you'll see that they have a subset of operations. These are jump operations as well as mathematical operations that are called signed operations, and they actually work based on looking at certain flags. And there's certain flags in the CPU that will get set if there's like underflows or overflows and things like that. Now, that's a little bit of a sidetrack for this discussion, but I just wanted to mention it in case you wanted to go peek at signed operations in your CPU manual, just to kind of see that if maybe you had looked at that before and it didn't make sense. You can maybe now go and look at that. And for those of you who know all this stuff, thank you for hanging in there. Okay, now let's travel back up to 0, and then let's go to the high end, which would be plus 127. Now, this may sound different, but obviously it's sort of the same thing. We're just going in the upward direction, and when we reach 127 and we increment 127 by 1, as you can see here, it actually rolls over in a sense, or overflows to negative 128, which is really just incrementing from 127 to 128 in the unsigned value. But because we're talking about signed values, there's really no way it could be positive 128 because the sign bit is set. And as mentioned earlier, that's just the nature of 2's complement positive and negative numbers. The negative side always has 1 more negative than the positive side. So in the case of 1 byte signed integer, you have negative 128, but you only have positive 127. You don't have positive 128. And the same would apply for any other signed integer. So a 24-bit integer is going to have 1 more on the negative side than it will on the positive side. Positional number systems in general, such as decimal and binary, have certain properties. Now, generally with like a number system like the decimal number system, we don't have to be aware of these properties because we use it all the time. It surrounds us from the time we're born. So it's like second nature to us to both interpret it and to use it and to perform math using it. We really just don't have to think about the properties of it on a regular basis. However, with the binary number system, since we don't use it on a regular basis, it can be helpful to revisit some some of these properties because it can help us understand certain subject matter within, let's say, software engineering that relates to the binary number system and positional number systems and their properties. So some of this stuff I'm going to recap might be second nature for some of you guys out there, and for other folks it might just be a good refresher. Whatever the case is, I just wanted to touch on these points before we go into the next section. Two such properties I want to highlight at this time are that each digit place in a number system such as binary or decimal has what we'll refer to as an index. The index is to the left of the point, the radix point, or we would call it the decimal point in the decimal number system, or the binary point in the binary number system. But each digit to the left of that radix point, whether it be explicitly there or invisible, you might not always see a decimal point, for example, but it's implicitly there. And each digit to the left of that will have a number starting with 0, and then the next one will have a 1 and a 2 and a 3. We've seen this when we've numbered some of the digit places in the past sections. Each binary bit has an index position starting at index 0. Then you have index 1, index 2. When you take the base of the number system, whether it be base 10, so the number 10, or base 2, which would be the number 2, and raise that base to the power of the index of the digit place, you arrive at the value that each digit in that place contributes to the number's overall value. So for example, in the decimal number system, the ones place, which we're very familiar with, that would be index position 0. If we take the base, which is 10, and we raise it to the power of 0, we arrive at the number 1 because any number raised to the power of 0 is 1. And each digit in that place contributes a value of 1. So if we multiply 10 to the 0 times the digit which is in that place, we arrive at what that place is contributing to the overall number. Well, because 10 to the 0 is 1, multiplying the digit in that place to 1 just is the digit itself, and that matches up with what we know about the ones place. Whatever the digit is that's there is the value that it's contributing to the overall number. If we move to the tens place, that would be index position 1. The ones place is index position 0. The tens place is index position 1. Well, if we take the base, which is 10, and raise it to the power of 1, well, 10 to the 1 is 10. Any number raised to the power of 1 is the number itself. So in this case, the number 10 raised to the power of 1 is 10. That means each digit in that tens place, in that place which has an index position of 1, each one of those contributes a value of 10. Therefore, you can say that the value of the tens place is 10 to the 1 times the digit which is in that place. If you have the digit 5 in the tens place, 5 times 10 to the 1 is 50. Therefore, that digit's place is currently at that time contributing a value of 50 to the overall number. And if we move to the hundreds place, the hundreds place is index position not 0, not 1, but 2. It's the third digit to the left of the decimal point, or what we might call the radix point if we're going to be more technical. And so since the index position is 2, we would take the base, which is 10, and raise it to the power of 2, and we arrive at 10 to the 2, which is 100. That means every digit in that place that has an index position of 2, that's the third place over, contributes a value of 10 to the 2, or 100. Therefore, if we have a 3 in the place that has an index of 2, which we call the 100s place, but in this case, let's just say it's the digits place that has an index of 2. Well, 10 to the 2 is 100, and if we multiply that by 3, we come out with 300. So at that particular point in time, that digit would be contributing a value of 300 to the overall number. Now, we take those mechanics, if you will, for granted when we're using the decimal number system, because we kind of know, well, that place is the hundreds place. So if you have a 3 there, it's 300. We just kind of know it. We don't say in our head, well, 10 to the power of 2 times whatever the digit is there. But when discussing positional number systems in mathematics, it would not be uncommon to raise this point where you can actually, and no pun intended there, and raise this point that, if you take the base of the number system and raise it to the power indicated by the index position of the place itself, you arrive at the value that each digit in that place contributes to the overall number. The binary system is no different. Each digit's place has an index, so we know that the first binary digit has an index of 0. The second binary digit has an index of 1, and so on. Now binary is base 2, so it only has 2 possible digits per place. The possible digits are 0 and 1. Now, the value of 0 really contributes 0. So the value of 1 is the only non-zero digit that contributes a value to the overall number. Now, the actual value that a 1 and any given place contributes really depends on which place it's in. If the value of 1 is in that first place, it'll contribute a value of 1. If a value of 1 is in the second place, it'll contribute a value of 2. But how can we break this down and relate it to what I just discussed about raising the power of the base? What we can say is the base is 2, and if we raise 2 to the power of the index of the position of the digit, we'll arrive at the value the digit of the place contributes to the overall number. Since binary only has one non-zero digit, there's really only one digit that can contribute a value to the overall number, and that's 1. So for the first binary digit, which is in index position 0, you would raise the base 2 to the power of 0, and we know that any number raised to the power of 0 is 1. So any digit in that first place contributes a value of 1 to the overall number. And since there can only be one non-zero digit in any binary position, and that would be the value of 1, we would say if you have a 1 in that first place, you would say 1 times 2 to the 0, which would be 1, which would end up being 1 times 1, which ends up just being 1. We would say that the place with index position 0 contributes a value of 1 to the overall number. Moving to the next place over, which we sometimes call the 2's place if you're familiar with the binary system. But instead of calling it the 2's place, let's say that second place over has an index position of 1. And if we take the base, which is 2, and raise it to the power of that index position, which would be 1 in this case, well, any number raised to the power of 1 is going to be the number itself, in this case 2, which is the base. So 2 to the power of 1 is 2. So any digit in that second place, we would multiply it by 2 to the power of 1 to arrive at the contribution that digit makes to the entire number. Well, the only non-zero number that can exist in any digit in the binary number system is, as I mentioned before, 1. So if you have a 1 there, you would say 1 times 2 to the 1, which is 2, and so 1 times 2 is 2, and we would say that that 1 there contributes a value of 2 to the overall number. Makes sense, right? Now, if you had a 0 there, you would just be saying 0 times 2 to the 1, and anything multiplied by 0 is going to be 0, so there's no contribution to the overall value when you have a 0 in any given place. So if you have a 0 in any given place in any number system, really, it's really going to be an indication that that place is not contributing to the overall number at that point in time. Now, if we go to the next place over, that would be the third index over, which would be not index 0, not index 1, but index 2. That's the third index over. So 2 to the power of 2 is 2. So we would say whatever digit in that place multiplied by 2 to the power of 2, 2 is the base, raise it to the power of the index is 2, so 2 to the power of 2 times the digit, let's say there's a digit of 1 in there, well that would contribute a value of 4 to the overall number. And this continues in the binary number system for any number of digits we have. So we're working largely with a byte right now for explanatory and illustrative purposes, so you can see that each binary digit's place in a byte has this principle that you can apply to it in order to figure out what the overall value is. If you were to take each digit that's non-zero in a binary byte and you were to multiply it by 2 to the index of that position and you were to add all those together, you'd come up with what the value of that overall byte is. There are 3 remaining points I want to mention regarding positional number systems, especially as they relate to the binary number system. Notice how when this binary bit is shifted to the left, it is multiplied by the base of 2. So basically every time we shift the digit to the left, we're multiplying it by the base. And in this case, it's the binary number system. So each shift to the left ends up multiplying the overall number by the base, which is 2, or multiplying the number by 2. Likewise, when we shift to the right, each time we shift to the right, we end up dividing the overall number by the base of 2. Each shift to the right divides by the base, and in this case, the base is 2, so it ends up dividing by 2 for each shift to the right. Each shift to the left multiplies by 2, each shift to the right divides by 2. And in this small example of magnitude amplitude, notice how when we only have one bit, we can only represent two numbers. If we add a bit, we can now represent four different numbers. And when we add a third bit, we can represent up to 8 numbers. Notice how when we add a bit, we double the overall numbers that can be represented with the bits that we have available. So when we went from 1 bit to 2, we went from being able to represent only 2 different numbers to 4 different numbers. And when we added a third bit, we went from being able to represent only 4 different numbers to being able to represent 8 different numbers. Let's discuss encoding or digitizing source values into destination binary values. Let's say we have temperature readings from some real-world sensor. We want to encode those source values into a 2-bit binary number, which only has 4 possible values. While 2 bits is small, it offers a nice simple example illustrating anomalies around digitization of real-world values such as temperature readings, audio amplitude values, or what have you. We're going to take this simple approach so you can gain a strong visual of certain key concepts. These key concepts are applicable to larger ranges such as 24-bit integer audio. Let's first calculate the total potential range, or total range, which is the highest potential source value minus the lowest potential source value. In this case, the highest potential source value is 100. The lowest potential source value is 0. 100 minus 0 is 100. So we have a total range, or total source range, of 100. Now let's determine or calculate the total potential destination values that we have available that we can use to encode those source values in that source range. We can do that by raising the power of 2 to the number of bits that we know we have available. And that indicates that we can encode source values into a maximum of 4 different destination values. Another way with this small range is simply to look, and we see that there's 4 potential values available to us. So in this example, we know our total destination range size is 4. Our source range of 100 potential different source values is 25 times larger than our destination range of only 4 available values. How is it that we can digitize or encode all of those 100 values into only 4 destination values? The answer sort of lies in our acceptance that in order to achieve digitization of any of these 100 values into our destination range of only 4 values, that we're willing to accept a certain loss of accuracy or precision or quantization error over time as we convert values from the source range into the destination range. It's therefore impossible for us to convert all of those 100 source values into the destination values with 100% accuracy. We will be losing some accuracy in that conversion. However, if we deem such loss of accuracy as acceptable or negligible for our application, then generally we find the conversion into that destination format acceptable for our needs or our use case. For example, let's say you had a very low-cost microcontroller with not a lot of memory, and let's say it had a little small solar panel on it, and you wanted to leave these things sitting out in various places, and there was no RF or anything like that. They were very low power devices, and they're meant to simply get a reading over time as to whether or not the temperature is low, medium high, or high. Well, in such a case, we might look at 2 bits of data as being very memory efficient, and that will allow us to capture more data over time because our application here doesn't need exact temperatures. It just needs to know if something was very low, maybe medium low, just below the halfway point, or above the halfway point, that'd be medium high, or at the high end, which we would call high temperature. So in such a case, we might view 2 bits as acceptable. Now, if we needed super high precision to be maintained over time, we might demand more bits than 2. But for this simple example, let's say that it fits our application. And what this will allow us to do is look at this simple example, and it'll give you a really good idea of what happens when we convert these values and the kinds of errors that we see, the loss of precision that we see when we convert certain values. The key point here with the number of bits is that while 2 bits might seem ridiculous for some situations, it might be completely reasonable and acceptable, more than enough for some particular use case or application. When it comes to other applications such as recording audio or video or whatnot, when people make selections about the bit depth to use, they may do so because there's just general industry acceptance that it's good enough for what they need it for. Most consumers tend to do that. Or somebody with more expertise in a particular situation like field recording or something like that might actually choose something like 32-bit float or something like that because it offers something that they need for their specific application. So just keep in mind that a low number of bits to encode something to is not necessarily bad. It's not necessarily great either. You have to understand what's going to happen to the data, how it will be used, the anomalies around that when you're making choices like that. Or as a consumer using a device or something, you can just use selections that are recommended, and if you like the results of those, you can just be happy with those. But for this simple example, we're going to have these 2 bits to use, and it's going to be very illustrative. So how do we take a source value and convert it into the target binary format? In this case, a 2-bit binary integer. First, we have the source value we want to convert. That's the value from the source range that we want to convert into the target binary system. Then we also have the total range of source values. That's the high source value minus the low source value, which gives us that total range of source values. We divide the source value by the total possible values from the source. That's the total range. So we divide the source value by the total range. This gives us a ratio which represents the value itself as a percentage of all possible values. I find it helpful to think of a ratio like this as the ultimate format agnostic way of expressing a value within a range. When we perform a division like this to create this ratio, we create this percentage value which we can apply to any range, whether it be the source range or the destination range, or whichever range we wish to apply it to, in order to determine how we would represent that original source value in whatever system we apply it to. And this is actually what's happening here, as you'll see. Next, we multiply that ratio by the maximum number of values that our target binary system can represent. In this case, it's a 2-bit integer binary system. Now, as we discussed, it represents a maximum of 4 values. We multiply that ratio against the maximum number of values that the target system can represent, in this case 4. And remember, that ratio is kind of format agnostic in a sense because it represents a percentage of a whole. And so by multiplying that percentage of a whole against the total number of unique values that the target system can represent, we end up effectively finding the number within the target system that we should use to represent the source value. It can probably help to remember that adage about multiplication expressing the verb of. Now, that may not always be the case, but very often it can be. It's almost like taking that format agnostic percentage and saying, give me this of you, target system. So the target system can support 4 unique values, and we apply this multiplication of a ratio to the number 4. And it's like saying, I want to take this ratio of you 4 in order to find out where I fit into that amount of 4 that you have available. And so I hope that helps, to really see this kind of clearly. The multiplication of the ratio to 4, which is the total number of unique values in that target system, that multiplication may have a fractional amount. And we want to minimize loss of precision when we go to a target system that has less granularity than our source system. So in order to minimize loss here, we're going to add 0.5 before we do a floor and an int, as you can see here. And ultimately, that's going to minimize the amount of error or quantization error that will incur when we convert a source value into this more limited 2-bit binary system. Finally, after we calculate that final number that our source value represents in the target system, we clamp that value to 3, which is the highest possible value in that target 2-bit binary integer system. So that maximum value is 3. Remember, we have 4 potential unique values, 0, 1, 2, 3. That's 4 potential values. But the highest value is 3. The lowest one is 0, then you have 1, 2, and then you have the highest, which is 3. In case our rounding exceeds 3, we want to clamp it down to limit it at 3. All right, let's look at some examples. The first example has a source value of 0 of the range size 100. 0 of 100 leads to a ratio of 0.0. Of course, 0 of those 4 bits is 0. So this ultimately leads to a target value of 0. That makes sense. If we have a source value of 0, it's likely going to be associated with the lowest value of that destination range. The next example has a source value of 25 of that range of 100. 25 divided by 100 is 0.25. 0.25 is 25%. 0.25 times 4 possible values in that target system, or 0.25 of those 4 possible values, or 25% of those 4 possible values, is 1. Now we add the 0.5 for rounding, so when we say 1 plus 0.5, we get 1.5. Well, that's not going to bring us over to the next integer, so when we floor, we're going to come back down to 1, and we'll convert that to an integer, so we end up with the value of 1. So when we convert from a source value of 25, we end up with a destination value of 1. And that makes sense when you think about it. We have 4 possible values in that target system because it's a 2-bit integer binary system. And you can imagine 25% would be 1/4 of the way through, and that would be that second value there. So it wouldn't be the number 0 in that target system, but rather the number 1 in that target system. The next example considers a source value of 49. This value was chosen because it's 1 less than halfway through the range. Well, 49 divided by 100 gives us 0.49, or 49% of the total source range. And because it's 49% of that source range, when we go and find out where 49% is in the target range, and the target range has 4 possible values, we basically multiply 0.49 times the number of possible values in that target system, which is 4. So that's 0.49 times 4. When we do that, we get 1.96. 1.96 is pretty close to 2, but not quite there. When we take 1.96 and we add 0.5, we end up with 2.46. This puts us over to the next integer 2. So we're at 2.46. So we're in the space, if you will, of that next integer above 1. We were at 1.96. We added 0.5, which brings us to 2.46. Now the floor takes place, and that brings us down to the nearest integer there, which is going to be 2. That means a source value of 49 from our source range of 100 has a target value of 2. So our source value is 49, which is not quite to 50. However, because of rounding, we pushed it over, so it ended up selecting a destination value of 2. That provides actually less loss of precision than had we given it a value of 1. So if we had just floored 1.96 without any rounding, we would have had a quantization error of 0.96. However, because we were so close to 2 and we did the things we needed to do to round up to 2 because we were closer to it than we were to 1, we ended up reducing the quantization error to 0.04. We're going to talk more about quantization error and stuff in a later section, but I'm just pointing this out. The next example uses a source value of 50 of the source range 100. Well, 50 divided by 100 gives us that ratio of 0.5, or 50%. So that source value 50 comes from 50% into the source range. To the best extent possible, we want to find 50% into the destination range. And that's what we're doing here. So we're going to say 0.5 times 4, or 50% of 4, is the value 2. Now we're going to add 0.5 to that, just in case there's a need to round. That's going to bring us to 2.5, and floor is just going to bring that right back down to 2, so there's no rounding up here. It's just going to select the value 2. So we see a source value of 50 gets a target value of 2. And we see the same thing happen for a source value of 49. So we see that both 49 and 50 got the same target value of 2. And that makes sense because there's many more source value potentials than there are target values, so there's going to be a lot of overlap. Many source values are going to share the same target value. What we notice is with the source value 50, there is no quantization error because 50 just happens to be right there at 50%. There was a slight quantization error when relating that source value 49 to a target value of 2. However, for our application, we're assuming that these kind of quantization errors are acceptable, that converting from a source range of 100 into a target range of 4 possible values is acceptable. So the next example here is 80. So 80 of 100 is 0.8, and 0.8 is 80%, that's like saying 80 comes from 80% into that source range. It's also like saying in order to relate that source range location to a target range, you multiply that ratio .8 to that target range. Notice how that ratio can be used to find the right value not only in that source range, but also in that target range. So .8 of 4, or 80% of the 4 possible target values, gives us 3.2. We add 0.5 to that to get 3.7. That's not enough to bring us over to 4, but even if it did, the clamping would bring it back down to 3 anyway, since there is no value 4 in the target range. Regardless of what happens at this point, the value, once we're in that range of potentially 3, we're never going to really go to 4, so it's going to be floored down to 3. So the source value of 80 is translated into the destination value 3. Using the same encoding formula, here is the encoding of all the source values. Take note that the destination values at the edges of the destination range, that would be values 0 and 3 in this case, are used each a different number of times than the values in the middle of the range. That's caused by both rounding and clamping in the approach being used to encode values in this particular case. The destination value of 0 is only used 3 times at the low end, and at the high end we see destination value 3 being used 8 times. The destination values in the middle of the range, in this case it would be 1 and 2, are used each 5 times. This relates to rounding and clamping. If we did not round, the quantization error for certain values would increase, as we just discussed. For a small negligible cost at the edges, the formula to encode is kept simple and consistent across the board, and the quantization error is minimized. With this small 2-bit destination range having only 4 possible destination values, this edge anomaly may seem stark. But for larger bit spaces such as 16-bit and 24-bit, this anomaly is negligible. Now, to be fair, whether software will exhibit this anomaly when encoding values is really dependent on the software itself. Not all software encodes the same way. By encoding this way with this example, you get an opportunity to look at and be aware of these sort of edge cases around clamping or rounding and whatnot. But with that said, when you approach any given piece of software, be open to discovering what it's doing in terms of encoding or decoding and that sort of thing. So to take an encoded value that's in that destination format, that 2-bit format, and to decode it to a source value, what we do is we take that source range and we divide it by the number of different values we have in our encoded format. In this case, there's 4 different values. By taking the source range and dividing it by the number of unique values in the encoded range, we come up with a ratio that when we multiply it by an encoded value, we'll get back the related source value for that encoded value. Let's go through some examples here of using this and reviewing this to see which ones were accurate and which ones incurred some loss in precision. Because obviously our destination format is not as high a resolution as the source format, so therefore there's going to be some loss here, and that's what we're going to review right now. The source value 25 was encoded to the destination value 1. When we decoded it just now, it decoded to source value 25. Since the original value was 25 and the decoded value was 25, there's been no loss of accuracy with this one particular sample. Let's look at the other ones. The next example was encoded from the original source value 15. When 15 was encoded, it was encoded to the destination value 1. When we decode 1, it decodes to 25. We just saw that with the prior example. What we kind of know now is when you decode 1, it decodes to an original source value of 25. Now in the prior case, since the sample was originally 25 and the decoded value was 25, there was no loss of accuracy for the cost of encoding and decoding into a lower resolution format. However, in this case, since the original value is 15 and the decoded value is 25, there's a disparity between the original value of 15 and the decoded value of 25. 25 minus 15 is 10, so we have a quantization error of 10 with this particular sample, meaning we're inaccurate by 10. The original sample was 15, but we recovered 25 when decoding the encoded value. The source value 20 was also encoded to 1. Therefore, when it's decoded, it's also decoded to 25. Since there's a disparity between the original source value of 20 and the decoded value of 25, we have an error. The error is 25 minus 20, so we have a quantization error of 5. The original source value 30 also encoded to a destination format value of 1. When that 1 is decoded, it decodes to 25. The disparity between the original source value 30 and the decoded value 25 is 5. We therefore have a quantization error of 5. Original source value 35 also encoded to 1, and it itself decoded to 25 with a loss of accuracy of 10. And so you get the idea. We decode a value back to the source value, and we compare it with what the original source value was, and then we can see what sort of error was incurred. Now, if you look here, you can see the different sections and how they're broken down, and you can see where there is higher quantization error. Where you see the green parts, there's least quantization error, if any at all. As we move to the outer edges of these segments, you can see the quantization error increases. In a sense, when we round during the encoding process, we're working to make it so that we use detail available at the time of encoding to make it so that the value we choose for encoding is as close as possible to a green area on this graph as possible. In a sense, when we encode a value, we have the detail available to make sure that we choose a destination value that will incur the least error when we come back to the original source format. Once we encode to a destination format, we no longer have that detail available. And so it's really important to take advantage of that during the encoding process. Now we're going to add bits to the destination format. And as we do that, watch the calculations change. Specifically, watch the quantization error drop as we add bits to the target encoded format. Now let's start at 2 bits and grow it out to a 24-bit signed integer destination format. Watch the quantization error drop quite significantly. A final note before moving forward. Our example here used a source range of 100. While a typical audio range is -1 to +1 or 2.0 in terms of distance, it is generally processed as if there's 2 separate ranges. One range is 0 to +1.0 and the other range is 0 to -1.0, where the sine bit is effectively a selector of which range to use. If it's positive, it'll use 0 to +1.0. If it's negative, it'll use 0 to -1.0. A key point here is that encoding and decoding audio amplitude is pretty much like the example we just went through, except that the source range is 1.0 instead of 100, and that a source range of -1.0 can apply if there's a sine bit that is set. Time for a game. Let's design our own binary encoding scheme. The purpose of this exercise is to prime our brains to take in a set of rules regarding how we're supposed to interpret bits in a given bit arrangement. In this little game we're going to play, we're going to use half of a byte or 4 bits. And we're going to define rules about how we interpret those bits. And the rules have some nuances that relate to actual real-world encoding mechanisms that we're going to discuss later on in this video. So by focusing on this small example, we'll get our brains ready for that more complex example later on. All right, let's get started and look at this miniature binary encoding scheme with its rules. Okay, this binary encoding mechanism only requires 4 bits or half a byte. That'll keep things simple as there won't be too many different bit arrangements. And that way we can easily display a table of all possible values and look at the interpretations. And I'm hoping that's a really good way to sort of get the gist of this. So we're going to be using 4-digit binary or half a byte. Remember, we number these starting from the rightmost bit over to the left, starting at 0. And we can refer to that number as an index, but generally we might just say bit 0, not really bit index 0, but it can be viewed as the digit index. So we have here bits 0, 1, 2, and 3. That's 4 different bits. And we might refer to those digit places as the 1's place, the 2's place, the 4's place, and the 8's place. That's like the human way of maybe naming those places. And if we want to consider the multiplying factor for the digit of each place, we might say for bit 0, any non-zero digit is multiplied by 2 to the 0, and for the next place it's 2 to the 1, 2 to the 2, and 2 to the 3, as we discussed in the prior sections. Let's go over the custom encoding rules for this encoding scheme that we're going to use here. Now, we could have called the custom encoding rules the specification for this encoding scheme. So in a sense, we're going to go over the specification right now. That specification is going to define how we interpret bits in this encoding scheme, what the rules are, and so forth. Well, the first point is pretty straightforward. We have 4 binary digits, 4 bits. Each one can be 0 or 1. Fairly straightforward. Each bit is numbered 0 through 3, starting from the right. So we have bit 0, 1, 2, and 3. As we progress in this example, we might call those bit 0, bit 1, bit 2, and bit 3. We're going to refer to bit 3, or the leftmost bit, as the special case bit. If the special case bit is 0, then the way we interpret the overall value is by looking at bits 0 through 2 and interpreting those in the normal unsigned integer approach to interpreting bits. The example shown here is 0, 1, 0, 1. Well, bit 3, the special case bit, is 0. That means we interpret the remaining bits, that's bits 0 through 2, which are set to 1, 0, 1. We interpret those as we would interpret any normal bits in an unsigned integer. In this case, 101 is the value 5 in binary, and that's pretty much how we interpret the overall value. It's 5. If the special case bit, or bit 3, is a value of 1, that's when things get really interesting. When the special case bit is 1, we interpret the bits differently. If the special case bit is 1, the first thing we need to do is determine what our base value is. Now, in this context, base underscore value is different from base as in base 2 or base 10. That's not what base value means here. Base value means a fundamental value. So the specification of our encoding scheme is calling for us to determine what a so-called base value is. And the base value happens to be the normal unsigned interpretation of bits 0 and 1. So in other words, we interpret bits 0 and 1 like we would interpret any other unsigned binary number made up of 2 binary digits. However, we then add 2 to the power of 2, or the value of 4, to the value of bits 0 and 1. So we interpret bits 0 and 1 as a normal unsigned integer value, and then we add the number 4 to that. So what's sort of happening here is when the special case bit is 1, it's saying interpret bits 0 and 1 as you normally would, but assume that bit 2 is set to 1. So in other words, you're supposed to assume that bit 2 has a 1, not the bit 2 that you actually see in the value that you're interpreting, but that there's an imaginary bit 2, and that you append onto that the bits 1 and 0 that are part of the number. And this will make sense in a second. So if you have a value starting from the leftmost bit of 1, 0, 1, 1, well, the first one is the special case bit. So special case is on or 1. The next bit is 0. Let's just ignore that right now. That's the real bit 2, but let's just forget about that for a second. We're not talking about that. And then the remaining 2 bits are 1. Bits 1 and 0 are both 1. Now, bits 1 and 0 being 1 is a value of 3 if you look at those standalone. But the specification, when the special case bit is 1, tells us to add 2 to the power of 2 to that value, or add the value 4 to that value. So in a sense, we're supposed to take 3 and we add 4 to 3. And what that does is it creates a value 7. But what's effectively happening there is, in a sense, when the special case bit is 1, we're being told to assume bit 2 has a 1, and that you're supposed to append bits 1 and 0 to that imaginary 1 that's always on. And again, this imaginary 1, this imaginary bit 2, is not the real bit 2, because that's going to have other meaning, which I'll explain in a second. So when special case bit is 1, we assume that there's a bit 2 that has a 1, and then we append on bits 1 and 0 to create a 3-bit number that always has 1 as the first digit. So in the case of 1011, we have a value of 7, which is 111, the imaginary always-on bit plus bits 1 and 0 in the actual physical number. Another example might be 1111. In that case, the base value is the same, 7. And the reason why is the special case bit is 1. Let's ignore bit 2 for a second. Let's just forget about that for a second because that's not related to figuring out the base value. And then what we're supposed to do is interpret the bits 0 and 1, and those are both set to 1 as they were in the prior example. And that's a value of 3, and we're supposed to add 4 to that, which gives us 7. What we're seeing here is that for the number 1011 and the number 1111, the base value is always 7. The next thing we need to determine is the so-called factor. So the factor is bit 2 plus 1 times 2. So if bit 2 is 0 and we add 1 to that, that's going to be 1. And then if we multiply that times 2, we'll end up with 2. If bit 2 is 1 and we add that to the value 1, we'll have 2. And if we multiply that times 2, we'll come out with 4. So it looks like the factor can either be 2 or 4. Great, now we know how to figure out the so-called base value and the so-called factor. These are both terms that are used by our specification. Well, now that we have the base value and the so-called factor, we can now compute the final value. And the final value is computed by taking the base value and multiplying it by the factor. And that ends up being the final value of our special encoding scheme. So let's use the same two example values as before. 1011. Well, the first one, which is the leftmost bit, is the special case bit. So when that's 1, we know we have special case interpretation. The next bit, or the multiplier or factor bit is what I'll call it. When that's 0, the factor is 2. We know that from the prior rule that we just went over. And when that's 1, the factor is 4. Since the bit is 0, we know the factor is 2. And then the next two bits are both 1, which is a value of 3. But we know we need to add 4 to that value of 3. So that makes that value 7. We then take 7 and multiply it times 2, and that gives us 14. So the final value is 14. The next example, all the bits are 1. So we have 1, 1, 1, 1. Well, the leftmost bit is 1. That's the special case bit. That tells us we have special case interpretation of these bits. Bit 2, or the second one from the left, is our multiplier or factor bit. And when that's 0, the factor is 2. And when that's 1, the factor is 4. In this case, we add a value of 1 to whatever bit 2 happens to be. If bit 2 is a value of 1, then we add 1 to that to get 2. If bit 2 is a value of 0, we add 1 to that to get 1. That affects the ultimate multiplier we end up with, which is either going to be 2 or 4. You'll notice that in some specifications where you're supposed to interpret bits a certain way, that if a bit is 1, it might be used as a factor in some part of the equation that you use to figure things out or interpret things. And that'll be somewhat applicable to our use of a real-world specification later on in this video. So basically with the value 1111, we have the special case bit set. We have the next bit over, which is bit 2. That's the multiplier or factor bit. That one's set to 1, which means we say 1 plus 1 is 2. We multiply 2 times 2, which gives us 4. So we know our factor is 4. Or we could just remember the table of possibilities for that bit. If that bit is 0, the factor is 2. If that bit is 1, the factor is 4. Probably simpler. But the reason why I'm using bit 2 as part of an equation in the specification is that is used in some real world specifications, as we'll see. And so it can help your interpretation there. So we have a factor of 4, and then those remaining two bits are both on, and that's a value of 3. But we're supposed to add a value of 4 to whatever that value is, so that gives us a value of 7. We then take that value of 7 and we multiply it by the factor. 7 times 4 is 28. So in a sense, you can kind of see that when that special case bit is 1, we interpret the lower two bits as though they're part of a 3-bit number where the high bit is always on. And then we multiply that by a factor that can either be 2 or 4. Fairly straightforward. If the special case bit is 0, we just ignore the special case bit and we treat the remaining 3 bits as a normal unsigned binary integer. So for this 4-bit number, when the values are 0 through 7, we have a normal interpretation of the overall unsigned value of that 4-bit number. For numbers above 7, that is 8 through 15, we have special case interpretation, because for the values of 8 through 15, the special case bit is set. When the special case bit is set, we basically interpret the lower two bits as the value that they are in a normal situation. We add 4 to that value, and then we multiply that, which is the base value, what the spec calls the base value, to the so-called factor. The factor is going to either be 2 or 4, depending on whether bit 2 is on or off. Okay, with a solid understanding of the custom encoding rules in this specification, let's go and look at some actual values in this custom encoding scheme. So here's a table of all the possible values. The first column is the binary representation of the raw 4-bit value. The lowercase b signifies binary. Essentially, those are the settings of the bits that we're talking about in the 4-bit number. The rightmost digit is bit 0, and then you go to bit 1, 2, and 3. Bit 3, the leftmost bit, is obviously the special case bit. The remaining columns are the interpretation of those bits given the rules we just mentioned. The S column in this table will be 0 if it's not a special case interpretation. The S column will have a 1 in it if it is a special case interpretation. You'll notice that the S column follows the bit 3 of the first column, the raw binary column. The F column is the factor, and notice that it's 1 for all the non-special case situations. When the special case bit is set, the factor is going to be determined by bit 2 of the encoded value. When bit 2 is 0, the factor will be 2. When bit 2 is 1, the factor will be 4. V is our value, and for the values 0 through 7, V is determined by bits 0 through 2. It's a normal interpretation of bits 0 through 2, and we ignore the special case bit. For the raw values 8 through 15, V is calculated as we just discussed, where we take the value of the first 2 bits and we add that to an implicit value of 4, as though that imaginary third bit or that imaginary bit 2 is always set. So if bits 0 and 1 are 0, we have that imaginary 4, which we add to 0, which gives us a value of 4. We then take that 4 and multiply it by the factor. Now you might be asking, what does this let us do? So in a normal unsigned binary interpretation of 4 binary digits, we only have the numbers 0 through 15. But given this encoding scheme, this specification that defines this kind of interpretation of 4 binary digits, we're allowed to represent values 0 through 28. In a sense, we have sort of a logarithmic scale here where we have a lot of dense values close together on the low end, but as it gets higher, the distribution gets further apart given the factor at play and the other things that go into calculating a number. This allows us to have an interpretation beyond the typical 0 through 15 interpretation of 4 binary digits. In this interpretation, we can represent values 0 through 28. However, we can't represent all values in 0 to 28. There's basically some gaps in there where we don't have the exact precision to represent some values. For example, if I wanted to represent the value 21 in this encoding scheme, I couldn't do it directly. I would have to round down to the nearest value, in this case 20. That would be a quantization error of 1. I would lose precision by encoding the value 21 in this scheme. So hopefully you can see that given 4 bits here, we're interpreting them differently than the standard unsigned integer interpretation, and it allows us to represent higher values, albeit we can do that at the expense of not being able to represent contiguous values in that higher range. It's a trade-off where we get to represent higher values, but we may not be able to represent every single higher value possible. For whatever the application is, that trade-off might be quite acceptable. Another example is, let's say we wanted to represent the number 27. Well, we couldn't represent the number 27 in this scheme in a direct sense. But if we had to, the best we could do is round up to 28. In that case, there'd be a quantization error of 1. And we would lose the exact precision of 27 if doing that. We would end up with a number of 28. And that might be acceptable for our application. And as you'll see, there's a real-world bit encoding scheme that has similar anomalies, and they're deemed acceptable given the flexibility that that encoding scheme offers. It It offers immense power in one way, partly for the exchange of precision to some extent. The loss of precision is not deemed a deal breaker in most use cases, so the net gain for the flexibility given the encoding format is deemed a worthwhile win for that loss of precision. If you ever have to design your own bit encoding scheme, you'll probably have to think about these kinds of considerations. How do you want to use the bits? How do you want to define them? And you'll have to think about what the application needs and what are the fair trade-offs to make given the application's use of those bits that you have available that you're trying to define to have some sort of meaning. All right, with this ruler here, you can actually get a sense for that uneven distribution of these values, which is sort of logarithmic in nature. And you can see as we progress higher up in the range of values that this encoding scheme can represent, that the jumps we have to make from one value to another increase in size, meaning we tend to lose precision as we get to higher values. And that's just a trade-off that this encoding scheme deemed acceptable for whatever reason. Hey everybody, let's get fractional. This is going to be a quick refresh recap on decimal point and binary point. Just as decimal numbers can express a fractional portion using a decimal point, so can binary numbers by using a binary point. Decimal has 10 possible digits, 0 through 9. 0 means 0 or nothing. When a place has 0, it currently expresses no counts in relation to the value that that place expresses. And at that time, it contributes 0 or nothing to the overall number. In decimal, when a place advances by one count, it is advancing 1/10 the value of a single count in the place to its left. You might say that when a place in the decimal system advances by one count, it is advancing by 1 over the base, which is 10 or 1/10, the value of a single count in the place to its left. Therefore, a 1 in the ones place is one of 10 possible digits, 0 through 9. In decimal, the digit 1 in the ones place is 1/10 the value of a single count in the place to its left, or the tens place. 5 in the tens place is one of 10 possible digits, 0 through 9. Therefore, a 5 in the tens place is 5/10, or 1/2 of a single count of a digit in the place to its left, or what we call the ones place. A 5 in the tens place is 5/10, or 1/2 of one count in the ones place. Binary has two possible digits, 0 and 1. 0 means 0 or nothing. When a place has 0, it expresses no counts of value to the overall value. In binary, when any given place advances by a single count, it is advancing by 1/2 the value of a single advancement by the digit in the place to its left. 1 in the binary ones place is one of two possible digits, 0 or 1. In binary, a 1 in the ones place is 1/2 the value of a single advancement of a digit in the place to its left, or what we call the twos place. The digit 1 in the halves place is 1/2 the value of a single count of a digit in the place to its left. Therefore, 1 in the halves place is 1/2 of one count of the ones place. In base 10, the advancement of a digit is 1/10 the advancement of a digit in the place to its left. In base 2, or binary, an advancement of a digit is 1/2 the advancement of a digit in the place to its left. Decimal 1.5 is equal to binary 1.1. Each has 1 in the ones place, so each has at least 1. Each has a fractional digit in the first fractional place to the right of the ones place, and each of those fractional digits represents 1/2 of a count in the place to its left, or the ones place. Therefore, each has a fractional digit that represents 1/2 of one advancement in the ones place. Well, each advancement in the ones place is one whole. 1. 1/2 of 1 is 1/2. Therefore, The .5, or the 5 in the tens place in the decimal system, is 1/2 of 1. Likewise, in the binary system, .1 is a 1 in the halves place. 1/2 is 1/2. Therefore, decimal 1.5 is equal to binary 1.1. Let's examine the value 12.875 in both decimal and binary. Now, first, a reminder about negative exponents. When you have a negative exponent like 10 to the -1 or -2, you can look at that as 1 over the positive variation of that. So 10 to the -1 is 1 over 10 to the 1. 10 to the -3 is 1 over 10 to the 3. Let's examine the value 12.875 in both decimal and binary. In decimal, we have 12.875. The 1 in decimal is in the tens place, so it corresponds to 10 to the 1. We would say because we have a 1 in the tens place, that's 10 to the 1 times 1. We have 2 in the ones place, which is 10 to the 0 times 2. In the tens place, we have 8, which is 10 to the -1 times 8. In the hundreds place, we have 7, which is 10 to the -2 times 7. And then in the thousands place, we have 5, which is 10 to the -3 times 5. Now we want to calculate each of those and add them up to show that it's 12.875. And you can see we end up with 10 plus 2 plus 0.8 plus 0.07 plus 0.005, or 12.875. The decimal value 12.875 looks quite different in binary. In binary, the decimal value 12.875 has the value 1100.111. Let's break this down, but first, a similar reminder about exponentation. Negative exponents are equal to 1 over the positive variation. So 2 to the -1 would be 1 over 2 to the 1. 2 to the -2 would be 1 over 2 to the 2. So if you have 2 to the -2, that's 1 over 2 to the 2, which is 1 over 4, or 1/4. All right, let's break this down. The decimal value 12.875 has the binary value 1100.111. The first or leftmost 1 is in the eighths place. So that's 2 to the 3 times 1. The next non-zero digit is in the fours place. So that would be 2 to the 2 times 1. There is no value in the twos place or the ones place, so we'll skip those. The next place is the first fractional place, or the halves place. There's a 1 in the halves place, so we'll calculate that as 2 to the -1 times 1. Next, we have a 1 in the quarters place, so that would be 2 to the -2 times 1. And finally, we have a 1 in the eighths place. That would be 2 to the -3 times 1. Let's expand those out, and we end up with 8 plus 4 plus 0.5 plus 0.25 plus 0.125. Add all those up, and we get 12.875. The following is a very general overview of how audio is captured by a microphone and recorded digitally. Generally, a microphone is a transducer that converts changes in sound pressure or vibrations into an electronic signal. The initial electronic signal captured by a microphone is generally very weak and requires some level of preamplification before further processing by the recorder. After preamplification, the audio signal goes through an analog to digital converter, or ADC. The ADC's purpose is to measure the audio signal's amplitude level and to use that measurement to produce a number or sample. The ADC essentially takes readings of the audio signal many times per second, often referred to as the sample rate. And for you audio ADC buffs out there, we're not going to discuss oversampling here and that kind of thing. The samples it produces can be stored in an audio file like a WAV file, or as another example, sent over a USB audio interface to a computer. Those samples can be used later to recreate the same voltage changes over time in order to replay the audio signal over speakers, headphones, or what have you. A digital audio file therefore contains a digital representation of an audio signal, which is made up of samples directly from or derived from the ADC. I qualify derived from because there might be some processing after the ADC before the sample's actually written to the file. Even though there are differing audio formats that people are familiar with, it can be helpful to think abstractly about all common audio formats as being containers of streams of numbers, each of which is an amplitude level at some point in time, that are at least between negative infinity and 0 dBFS. The distribution of these numbers, or samples, over time implicitly embody the frequencies, pitches, and other qualities we hear when the samples are used to drive speakers or headphones to reproduce the qualities of the original sound as captured by the microphone or whatever was used to capture the sound. Internally within a microphone, at the earliest point where it captures sound waves, is a sensing element that produces an AC signal, an electronic signal that fluctuates in an AC fashion in relation to how those sound waves affected the sensing element itself. The overall nature of a microphone's audio signal is directly related to the amalgam of sound waves that come into contact with or are otherwise sensed by the microphone's element over time. The audio signal from a microphone is therefore an electronic signal that exhibits changes in level or loudness or amplitude at one or an amalgam of frequencies over time. It is essentially a fluctuating electrical voltage whose changes in level have a relationship with the changes in air pressure as experienced by the microphone's element. These voltage changes occur at different rates or frequencies, which we hear as different pitches, and with different strengths or amplitudes, which we perceive as variations in loudness. To recap, a microphone's element converts sound waves into an electronic signal that changes over time. That electronic signal is initially very weak, so requires amplification before it's processed further. After amplification, the signal eventually reaches an analog to digital converter, or ADC, which takes measurements of the signal's level or amplitude as it changes over time, converting those measurements at the sample rate into a digital audio format such as 24-bit integer or 32-bit floating point. In this video, we focus on 24-bit integer PCM and 32-bit floating point PCM digital audio formats. These will often be referred to as just 24-bit or 32-bit or 24-bit integer or 32-bit float. As mentioned earlier, it can be helpful to think of all common audio formats such as 24-bit integer and 32-bit floating point as at least representing values between the ranges of -1.0 to +1.0 floating point. Now we know floating point can represent values far beyond that range. Contrast that though with 24-bit, which can only represent values within that range. For simplicity, we'll focus on the positive portion of the range from 0 to +1.0. Generally speaking, sign-related and polarity differences aside, whatever can be said about the positive portion of the range from 0 to +1.0 can also be said about the negative portion of the range from 0 to -1.0. Therefore, some of the diagrams will be simplified and just show that positive portion, and we'll focus on talking about that. From this point forward, you might see some references to 24-bit audio samples or block diagrams in a floating point format. That is, you'll see 0 to 1.0, for example, representing 24-bit audio samples in relation to some discussion of 32-bit float. This is done to make clear the relationship between the two formats and to discuss apples with apples in certain contexts rather than apples with oranges. Really, beyond the parts of this video that discuss the technical bit layout of 24-bit integer audio, it really makes sense to just simply refer to those audio samples as being between -1.0 and 1.0 because ultimately that's what they become once they are brought into an audio system. And even if the raw samples are used in some contexts, it doesn't negate the value of us using negative 1.0 to positive 1.0 for many of the discussions in this video. Just keep that in mind when you look at anything that says 24-bit audio and you see a scale going from 0 to 1.0 or negative 1.0 to positive 1.0. And this will become clearer as we move forward. Another point is you'll notice on some of these rulers there is an amount figure that is between some of the tick marks. For example, you see approximately 0.8 M or 0.8 million between the tenths sections in the 24-bit format scale. That's to show the resolution within those portions of the range. You can then compare those with how much resolution is between the same range for 32-bit float. And this is not to say that resolution necessarily makes audio sound fantastic when it wasn't recorded properly. We know that that won't happen. But there are some benefits to higher resolution. And also, generally, we're just trying to learn about the two different formats and their magnitudes. And I think part of what allows us to do that is to see the values visually and to just get a sense for their size, these ranges. So hopefully that's helpful and what I'm saying here makes sense. Let's discuss the 24-bit signed integer format, which is the same format used for 24-bit signed integer PCM audio samples. A 24-bit signed integer value has a total of 24 bits, of which the lower 23 bits determine the value of the number, and the highest bit, designated as the sign bit, determines the sign of the value. The 23-bit portion of the 24-bit signed integer has, of course, 23 bits, so therefore has 2 to the 23 different possible values. That would be about 8.4 million different possible values. The sign bit can either be 0 or 1, where 0 indicates a positive value and 1 indicates a negative value. The overall 24-bit integer value uses 2's complement, as we discussed in an earlier section. Given the 23-bit integer portion of the number can have about 8.4 million possible values, and given that the sign bit has 2 possible values, well, you have 2 different sign possibilities with 8.4 million possible integer values. That's 2 times 8.4, which gives you about 16.8 million possible values that can be represented by a 24-bit signed integer value or 24-bit audio sample. About 8.4 million of those values have the sign bit set to 0, so are positive values. The other 8.4 million numbers have the sign bit set to 1, so they are negative numbers. So the 24-bit signed integer value has 23 integer bits and a sign bit. That means the integer can have 2 to the 23 different possible values, as we just mentioned. Therefore, a 24-bit signed integer value can have values ranging from negative 2 to the 23 to about positive 2 to the 23. Or we can say negative 8388608 to positive 8388607. Why do we say 8388608 on the negative side? But on the positive side, we have one less value. We have 8388607. Why don't we have 8388608 on the positive side? Well, that's related to 2's complement we discussed earlier. In hex, that would be a range from 800000 to 7f, ff, ff. You can see if you were to increment 7f, ff, ff by 1, it would become 800000, which is the equivalent of the lowest possible signed integer value in 24-bit signed integer. So effectively, that would wrap around to that lowest possible value, which we really wouldn't want. And that's related to the 2's complement anomaly we discussed earlier. 24-bit signed integers are used in 24-bit audio to represent samples in an amplitude range going from negative 1.0 to positive 1.0, where the lowest and the highest amplitude values, or sample values, are the maximum a digital audio system can handle before clipping, or as we might say, exceeding 0 dBFS, where 0 dBFS is the maximum amplitude a digital audio system can handle before clipping. 0 dBFS is equated with an amplitude value of negative 1.0 floating point on the negative side of an audio signal and positive 1.0 on the positive side of the same signal. When the signal exceeds those boundaries, it is exceeding 0 dBFS. In 24-bit audio, when it exceeds those boundaries, there is no choice but to take samples that can't be represented because there's no more values or headroom above the maximum, and to just force them all to be the maximum value. And in many digital audio applications, you end up seeing that visually as a flat top wave. A digital audio system, when it takes in 24-bit samples, will typically scale those samples to floating point, where the lowest possible 24-bit signed integer value or sample becomes negative 1.0 floating point, and the positive most 24-bit signed integer value is equated with plus 1.0 floating point. Technically, that maximum most 24-bit signed integer value is 0.99999, and that's due to the two's complement anomaly we discussed earlier, where the negative side of the signed number has one more extra count than the positive side of the number system. So, for example, 24-bit audio has negative 8388608, and on the positive side, it goes up to plus 8388607, not 8. And given that slight difference, when you scale or convert 24-bit samples to the floating point range negative 1.0 to positive 1.0, that maximum 24-bit audio sample really translates to 0.9999, but effectively it's 1.0 in the amplitude range. And really, this is negligible because we're talking about 16.8 million possible values in 24-bit signed integer. And so missing one little step at the top end there is largely negligible. Most people aren't really thinking about it. But if you're looking at it in fine detail, as we're discussing here, this clarification might be helpful in case you're looking at it and wondering, like, well, why isn't this translating exactly to that or whatnot? Just keep that in mind. When audio applications or DAWs scale 24-bit audio samples to floating point, they might use a formula like the one shown here. This should look familiar if you remember from our earlier sections when we were translating from one system to another. So we would have source values and a destination binary system that we were converting to, and we would use a formula similar to the one you see here. Now we know because of 2's complement on the negative side, there's 8388608 possible values. On the positive side, we know there's 8388607. It's one less possible value on the positive side. Let's forget about that. So totally forget about that for these calculations. It actually doesn't matter because the calculations will come out correctly, and they will be consistent on the negative and positive side. You'll see what I'm talking about. If you divide 1.0 by the maximum number of possible 23-bit counts, which is 8388608 or 2 to the 23. When you do that, you find out how much each count within that 8388608 contributes to the range 0 to 1.0. And that value, that fractional value that we arrive at with that division, is what we can use to scale samples from the 24-bit integer sample to the floating point sample with a range of 0 to 1.0. Now, 24-bit integer audio can have a sign bit set or cleared. If it's cleared, it's a positive value, cleared meaning 0. If it's set, it's negative. So the source sample is going to determine the sign of the result of our scaling. So it's going to put the result either in the range of 0 to positive 1.0 or in the range 0 to negative 1.0. For example, if you take the positive 24-bit sample value 4194304, which is halfway between 0 and the maximum possible positive 24-bit integer sample value, or another way to look at it is 4194304 is halfway through the positive possible 8.4 million possible amplitude values that 24-bit signed integer audio samples can represent. If you multiply that by 1 over 2 to the 23, or 1.0 divided by 8388608, when you multiply that by that number, you'll arrive at 0.5. So you can see that scaled the source 24-bit integer sample into a floating point range between 0 and 1.0, and it put it right in the middle there at 0.5. Now imagine if that sample were negative. Imagine if it were negative 4194304. Well, the result would be identical. It would be 0.5, but the sign would be different. You're multiplying a negative sample value to a positive fractional value arrived at by 1 over 2 to the 23, or 1 over 8388608, which is that fractional value that will allow us to translate those samples into the destination floating point range. And in this case, it's a negative 4194304. So we arrive at 0.5, but it's negative 0.5. And so you can imagine these positive and negative samples in 24-bit signed integer being applied to this formula, ultimately creating floating point samples that have the same exact wave representation, but it's put into floating point, which is better and more efficient on many levels for the audio application to use. Plus, when you're bringing in multiple formats and you convert them to this common floating point format, it really lets you talk about apples to apples and write code within the audio app, actually, that can deal with apples and apples because everybody's kind of in the same language, if you will, or the same kind of sample format internally. Let's go through a couple of examples of how an analog to digital converter, or ADC, might detect and translate particular amplitude levels over time into 24-bit samples. For each example, we will also translate the 24-bit sample into its corresponding floating point sample, which is what an audio app such as a DAW might do when it receives the sample either directly from an audio interface or indirectly, such as from a WAV file previously recorded with an audio recorder. This is by no means an ADC deep dive. The world of ADCs and their interactions with other components such as digital signal processors and other processors and components is a vast subject, and one which can vary in a multitude of ways from one ADC to another. For example, a single ADC itself might have various what we might call operating modes, and different operating modes might provide different levels of error feedback to the connected components, such as the DSP itself, during its overall processing of the audio signal. We are not going to delve into such details, but we will instead stick with the high-level fundamentals. Generally, an audio ADC has a signal input, which receives an audio signal from whatever is capturing sound or otherwise delivering the audio signal to the ADC. So, for example, the signal could be coming from a microphone that has already gone through preamplification and initial conditioning, or it might be coming from some external device that has a line output, so it's like a line input signal that's coming into the unit where the ADC resides. And regardless, all those signals might go through some kind of conditioning and filtering and whatnot before they actually reach the ADC. For the following discussion, the details of what it goes through before it gets to the ADC are not really that important. Just assume some audio signal has already gone through whatever conditioning or preamplification is required, and it has reached the ADC, and the ADC is observing its signal input, and over time, as it observes its signal input, it creates samples at the configured sample rate. Imagine an ADC accepting an audio signal within a particular range. Anything outside of that range would be clipped. And we'll get into that in a second. The audio signal, being an AC signal, fluctuates between negative and positive voltages or amplitudes over time. For example, a person speaks into a microphone and the voice creates the sound waves and vibrations which affect the microphone element. That causes the microphone element to fluctuate in some kind of manner, depending on the microphone's construction. Those fluctuations generate an AC signal. An AC signal being alternating current. You can think of that as fluctuating in a positive and negative direction. The input to the ADC will have a limit on the positive and negative voltage that it will accept before clipping. We'll refer to the positive limit that the ADC will accept as VREF plus, and the negative limit will be referred to as VREF minus. These two values, vref plus and vref minus, together represent a range, or as we discussed earlier, a source range of potential input values, or a potential input value range. Generally speaking, the audio ADC's job is to produce a sample that is related to or translated from the input signal that it reads over time. Conceptually, the ADC accomplishes this by knowing the potential range of that input signal. In these examples, that range is defined by vref minus to vref plus. Therefore, the ADC expects to see a signal within the range of vref minus and vref plus. The ADC can use the range defined by vref minus and vref plus in connection with a reading of the audio input signal at a given point in time to produce a ratio, which is that signal reading at that point in time over the source potential range, or that source range, or the range defined by vref minus to vref plus. That ratio can then be multiplied to the destination sample range, in this case to the 24-bit sample range, which itself will produce the 24-bit sample that is related to that source input signal at that given point in time. Our examples will use a vref minus and a vref plus of negative 2 volts and positive 2 volts respectively. That means the ADC expects an input range of negative 2 volts to positive 2 volts as part of an AC signal, meaning this fluctuating signal connected to the sound waves should fluctuate within that range of negative 2 volts to positive 2 volts and should not go beyond that range or it will be clipped. So in brief, the ADC's job is to relate the input signal range to the destination 24-bit sample range for any audio signal reading at any given point in time. So it reads an audio signal at a given point in time. It uses that reading with its source range, vref minus to vref plus, to produce that ratio of the signal reading over the range, and so can be applied to the destination 24-bit sample range, which will give it the sample to relate to that source reading in the 24-bit sample range. You can think of a 0-volt audio signal reading as equivalent to the 24-bit sample 0, and a plus 2-volt reading as roughly equivalent to plus 8388607, or 2 to the 23 minus 1, given the 2's complement anomaly that we discussed earlier. Don't let that throw you. Likewise, a negative 2-volt reading would be equivalent to the 24-bit sample negative 8388608. Keep in mind that any voltage readings of the ADC that are below vref minus, or below negative 2 volts, or above positive 2 volts in the AC signal are simply going to be given those topmost and bottommost sample values as a way of handling that error condition. With all that stated, let's go through a few examples. For this first example, we see the ADC observes an input signal with a level of 1.5 volts. We can view that positive 1.5 volts as 1.5 of the potential 2 volts of the range from 0 to plus 2 volts. That ratio gives us 0.75. If we multiply that 0.75 to the destination sample range from 0 to its maximum, which is 8388608, we end up with a sample value 6291456. Or in hexadecimal, we see it would be 600000. Hopefully you can see how the ADC can relate its source range potential to the 24-bit sample range potential output, and how it can do that on a sample-by-sample basis by using a reading of the current input signal in combination with what that potential signal range is, meaning the vref minus to vref plus. Now, once this sample is produced, if an audio app or a DAW immediately needed to use the sample, or if the sample had been saved to like a WAV file and was being read by the audio app could convert that sample from the 24-bit sample into a floating point sample before it would use it internally. And it could do this by taking 1 and dividing it by 2 to the 23, which is that maximum 24-bit sample value of 8388608. So if it takes that range between 0 and the maximum or 0 and the negative, which is 8388608, and if it divides 1 by that, it produces a ratio that can be then multiplied to a 24-bit sample to derive the related floating point sample. And in this case, that related floating point sample would be 0.75. Next, the ADC reads a 2.5 volt level signal. That's beyond the VREF plus range. It goes over the top of the VREF plus range. That's an error condition which doesn't have an equivalent 24-bit sample value because it's going past the top of the range that's defined for the ADC. In that case, the ADC is going to choose the maximum value and simply use that as part of the error handling. And so in that case, it produces a sample 8388607. So when that kind of error handling takes place, in a sense, anything that's over that VREF plus range or below the VREF minus range is going to get the highest sample number or the lowest sample number respectively. And as we discussed in the prior section, when that kind of handling takes place, when a DAW or audio app reads in that sample, it ends up sort of producing this like flat top looking wave when you see it visually in the app. At least usually that's what you'll see. And really what that amounts to is a huge quantization error, if we even want to really call it that. The detail of the signal is lost. All you're able to do is represent it as the maximum amplitude value that the system is designed to represent, and that's not really connected to the original signal, and so it's not really going to sound great on playback. Now, it may well be intermixed with parts of the signal that did not clip, and so you'll hear it intermixed in that sort of distorted kind of way where some of the signal will be intelligible, but a good portion of it will sound like garbage. And in this last example, it's 2.8 volts. That's over VREF plus again. And this is just simply to show that even though it's a different value that's over the top there, it's going to amount to the same sample value, which is the maximum positive value, which is 8388607. So what you're seeing here is two voltage readings or amplitude readings that are above the VREF plus line, above that maximum, and they both end up producing the same destination sample value, which is essentially a loss of signal detail. Now you can imagine, what if this were a signal that could have been captured correctly if the gain had been adjusted at the input? Let's say the original signal was fine, but the gain was so high that it just pushed the signal above the maximum that the system could handle when reading the samples. Had that level been adjusted properly, then that 2.8 and 2.5 sample would have been lower down and below that VREF plus range. And so they wouldn't have ended up being clipped. The detail of those, especially with respect to the other samples, all the samples together and their relative, distance from one another, produce the detail of the signal overall. And so the gain typically should be adjusted where that overall detail can be maintained, without the signal being so low that it's kind of intermixed with the noise so much that it becomes a prohibitive thing to have it so low. And that's the thing with 24-bit audio, is you want to adjust it in the right zone there so that you're not exceeding that maximum. You also don't want to be too low where you're, intermixed with too much noise. Now, everything that we're mentioning here is different than the notion of, for example, a microphone being overloaded with more powerful sound waves than it's rated to handle, which can happen if you speak or sing too close to certain microphones. In a case like that, the mechanics or electronics of some device that's meant to sense the sound and turn it into an electronic signal for the system is itself being taxed. And when it itself is being taxed, that doesn't necessarily mean the electronic signal that it will propagate to the system recording it will be exceeding the maximum of that system. The ADC itself could get a signal that's within that VREF minus and VREF plus, so it looks perfectly normal and it can get a nice, set of detail to capture that sample. But the detail that will be captured, while it won't be clipped, might be something that was distorted by too much power hitting a microphone because somebody was too close to the microphone, or some other anomaly that was taxing the actual system long before the signal reaches the ADC. So keep that in mind when folks are talking about clipping at different points in time. We're kind of focused on sort of general fundamental concepts of an ADC. We're not really talking about particulars of like a microphone being taxed beyond what its capabilities are, which is really a different thing than the signal it would produce even when being taxed that the ADC might see, which could be a totally normal signal, but it might be be itself messed up because the microphone was overloaded in a physical sense, not in the sense where it produced too much of a signal for the recording, but where physically, let's say the membrane was being overloaded in a way where the sound quality is just not that great, right? Where it's not really maybe capturing the particulars of the sound wave because it's kind of being overloaded in some way, like being too close to it or yelling into it or something like that. So if you're interested in learning where like a quality issue is occurring in something you're using, try to really think of those different parts. It may not always be gain. It may be something else. Let's go over the fundamentals of the IEEE 754 single precision floating point format, sometimes referred to as binary 32 or float 32, or sometimes people say 32-bit float, or sometimes just floating point where people know you're talking 32-bit. Unlike the 24-bit format, which is only 3 bytes, the 32-bit format is of course 4 bytes, so adds an extra byte of bit space or magnitude. As well, its format, being floating point, is a bit more involved than the 24-bit signed integer format we've been focused on. In an earlier section, we introduced the concept of a more involved encoding format. That format showed how we could use bits to express the overall value of a number by interpreting the bits in a manner that was different than the standard signed or unsigned integer usage of bits. For example, some of the bits could act as a multiplier, and the nature of that multiplier would depend on the settings of other bits. While that example was small, simple, and unrelated to the floating point format in a direct sense, some of the encoding concepts discussed in that small example were meant to resonate with or have a feel similar to the ones found in the 32-bit floating point format. Given this, if you haven't seen that section, and depending on where you're at, you may want to go catch that example because it could help provide a little bit of a foundation that might be helpful here. The float 32, binary 32, or the 32-bit floating point format carves its 32 bits or 4 bytes into 3 general sections. Those sections are the sine bit, the biased exponent, and the mantissa. First and foremost, the simplest way from a high level to explain the 32-bit floating point format is to say that it is simply a format that expresses 3 separate factors that you multiply together to arrive at the number's overall value. Those 3 factors are derived or come from the 3 components I just mentioned: the sine bit, the biased exponent, and the mantissa. So just keep in mind from a high level, that's the name of the game. You've got these 32 bits and they're broken down into 3 parts: a 1-bit sine bit, an 8-bit biased exponent, and then you have the remaining 23 bits, which we refer to as the mantissa. And there are rules for deriving the value that each of those sets of bits ultimately represents. And once you have those values, you just simply multiply them together and you've arrived at what the value is of the floating point number at that point in time when the bits are set the way that they're set, the bits that you're interpreting as you go through the exercise of learning to calculate the number. And we'll go into some examples coming up. The mantissa can represent 2 to the 23 or 8388608 different possible values. The biased exponent is a byte in length or 8 bits in length. Therefore, it can represent values from 0 to 255. The values 0 to 254 are related to actual exponents that can be derived from the biased exponent. The remaining value 255 has special meaning and is used to flag things like an error condition, which, while not the topic of this video, will be touched on briefly. So in short, you can think of the biased exponent as really ranging from 0 to 254 for the sake of our discussions in this video, although 255 has special meaning we'll touch on. And of course, the biased exponent is not the exponent itself. You have to subtract 127 to arrive at the actual exponent. And if you want to take an actual exponent and arrive at the biased exponent, you add 127. So if you want an actual exponent of 0 to be encoded into the format, you would add 127 to 0. That would give you the value 127. So the biased exponent 127 is really equated with the actual exponent 0. The sine bit, of course, has 2 possibilities, 0 or 1, which we've already touched on. Combining the possibilities of those 3 portions of the 32-bit floating point format Together, we see there's a total of about 4.3 billion possible values that the 32-bit floating point format can represent, significantly more resolution than the 24-bit signed integer format. And the range of actual values that can be expressed with the 32-bit float format goes far beyond the values that the 24-bit signed integer format can represent. In prior sections, we covered the audio floating point range at and below 0 dBFS, which is expressed as a range from -1.0 to +1.0 in floating point. For that range, 32-bit float has about 2.1 billion possible values, significantly more than 24-bit signed integers' roughly 16.8 million possible values. Those 2.1 billion possible values of the floating point range represent only about half of its total, about 4.3 billion possible values. This generally means that signals that go above 0 dBFS can have their detail captured, and if captured, can have that detail recovered or restored or brought into range, meaning below 0 dBFS, in post-processing as desired or needed. We will touch on recoverability later. So revisiting the sine bit, it can either be 0 or 1. But when we want to use the sine bit to create a factor that we can multiply with the rest of the other components, those two other parts, the factor that gets created from the biased exponent and the factor that gets created from the mantissa. So if we want to create a factor from the sine bit that can make the number either positive or negative, what can we do? Well, what the format says is that you take the number -1 and you raise it to the power of the sine bit. And that works out quite elegantly. If you take -1 and you raise it to the power of 0, well, any number raised to the power of 0 is 1. So in a sense, when the sine bit is 0 and you're raising -1 to 0, that factor becomes just simply 1. And when you take 1 and multiply it to anything, you're just basically not going to change the number. It's going to remain itself. And in that sense, if you multiply 1 to the exponent and to the mantissa, the factors that you derive from those portions, you'll end up not changing those factors, and they default to being positive, so the number just remains positive. However, if the sine bit is 1, you then raise -1 to the sine bit, which is 1, and any number raised to the power of 1 is going to be the number itself. And in this case, the number is -1. So -1 raised to the sine bit when the sine bit is 1 is -1. And as a factor, what does -1 do when it's multiplied to any number? Well, it negates the number. If you take -1 and multiply it to 100, you get -100. So in a sense, an elegant way to express what the factor is associated with the sine bit, you just simply say that that factor is -1 to the sine bit. So basically that acts as a toggle. If the sine bit is 0, you have -1 to 0, which is 1, which means don't touch the number, just keep it the same when it's multiplied to the exponent and the mantissa. However, when the sine bit is 1, you're taking -1 and you're raising it to 1, which gives you -1, in which case you're keeping the number the same, but you're going to make it negative. So let's refer to the biased exponent as bx and the unbiased exponent, or the original exponent, as x. The original exponent is the biased exponent -127, and the biased exponent is the original exponent plus 127. And if you're looking at a biased exponent and you want to know what the formula is to derive the value that you can use as a factor to multiply with the other factors in the 32-bit floating point format, you basically raise 2 to the biased exponent minus 127, meaning the power is the biased exponent minus 127. And the minus 127 is just simply the value you subtract from the biased exponent in order to arrive at the original exponent. So you're simply raising 2 to the power of some original exponent that represents what that factor should be when it's multiplied to the other components of the 32-bit floating point value. For example, if the biased exponent is 127, we subtract 127 to arrive at the actual exponent of 0. Given the actual exponent of 0, we raise 2 to the power of 0, and that gives us 1. So when the biased exponent is 127, the factor that we derive from the exponent overall is 1. For the next example, let's use a biased exponent of 1 less than the prior example. So instead of 127, we'll say it's 126. Well, if you subtract 127 from 126, you get -1. So -1 is our actual exponent that we're going to use. And so we raise 2 to -1, and we end up with 0.5 or 1/2. Let's go to the highest biased exponent of 254. I say 254 because remember, 255 is a special case value that's used for error conditions and whatnot. From the biased exponent of 254, we subtract 127. This gives us 127 as the real exponent. And so we take 2 and raise it to the power of 127, and that gives us the ginormous number, which is approximately 1.701 times 10 to the 38. That's taking the decimal point and shifting it over to the right 38 times. Imagine a large number, 1.701, with that decimal point moved over 38 times. Quite a large number. Let's go down to a biased exponent of 1. So we subtract 127 from 1. That gives us the real exponent of -126. So we take 2 and raise it to the power of -126. And that gives us an incredibly small number of 1.175 times 10 to the -38. So that's taking the decimal point and shifting it 38 places over to the left. So you have dot and a bunch of zeros and this 1.175. And this value itself is actually truncated from the precision that was available to me. If you go do it on your scientific calculator, you'll see you'll get many more digits than what I'm showing here. So you can see that this exponent field or biased exponent field is one that determines the power to which we raise 2. And when we raise 2 to a negative power, we get a fractional multiplier. And raising 2 to a positive exponent creates a non-fractional increasing multiplier. And if you raise 2 to the power of 0, and 0 being right in the middle of those negative exponents that are fractional, and those positive exponents which end up being increasing multiplying factors, right in the middle of all those is 0. And 2 to the power of 0 is 1, because any number raised to the power of 0 is 1. And so that middle exponent of 1 means that the exponent has no effect on those other factors. So the exponent has this ability to not do anything to the mantissa and the sine being multiplied together, or it has this ability to make the number's overall value smaller in a fractional sense, or much larger in magnitude as well. There's a special case when the biased exponent is the value 0. When the biased exponent is the value 0, you don't subtract 127 to arrive at the actual real exponent. Instead, what you do is you simply assume that the real exponent is -126, as if the biased exponent were 1. So when the biased exponent is 0, you behave almost like the biased exponent is 1. So when the biased exponent is 0, you don't need to subtract anything to arrive at the actual exponent. You just know right away that the exponent is -126. And you might think, why do that for a biased exponent of 0 if you already have a case where the biased exponent being 1 would yield the same real exponent of -126? And the reason why is in that special case, something else happens. And that something else is a special condition, which we'll discuss in a second. But a little preview is that it affects how we interpret the mantissa. And now moving on here to the mantissa has 23 bits, which are used as fractional bits. These 23 fractional bits are assumed to be to the right of an implicit binary point. So immediately to the left of bit 22, there's an implicit binary point. And to the left of that binary point is an implicit number, and it's either 0 or 1. And whether that implicit number is 0 or 1 depends on the value of the biased exponent. If the biased exponent is anything but 0, the implicit prefix to the mantissa is 1 dot. When the biased exponent is 0, the mantissa is prefixed with 0 dot. So to recap, if the biased exponent is anything but 0, the mantissa is 1 dot and the mantissa in binary point. If the biased exponent is 0, the mantissa is 0 dot and the mantissa in binary point notation. So that should tell you what the difference is between a biased exponent of 1 and a biased exponent of 0. Both biased exponent of 1 and biased exponent of 0 yield an actual exponent of -126. Recall just now that the biased exponent of 0 is to be assumed to be the real exponent -126. In other words, you don't subtract 127 from the biased exponent when it is a value of 0. You just assume that the real exponent is negative 126. And this is a way of using a biased exponent of 0 to not only have an actual exponent of negative 126 being used again a second time, but for this second usage of it, in a sense, the mantissa is different. It begins with a 0 dot. And this is a way of getting to extraordinarily small numbers, what might be referred to as subnormal numbers. These are numbers that are extremely small. Except for an example coming up, we're not going to focus too much on subnormal numbers, but just keep in mind at the very low end, the 32-bit float format is capable of representing these very, very small numbers. Now, there are some interesting precision anomalies around all this, and we're not going to get into that here. The purpose of this here is to introduce this format and to talk about it in connection with audio sample formats such as 24-bit audio formats and the use of 32-bit float as an audio format as well. But we're going to call out these various aspects of the 32-bit float format, at least in brief here. So here's a little recap on how to interpret the 32-bit float format. If the biased exponent is not 0 and it's not 255, the number is normal, meaning it's not subnormal and it's not an exceptional error condition, and it's calculated with the formula shown here, which is f for floating point equals negative 1 raised to the sine bit times 2 to the biased exponent minus 127 times 1 dot and the mantissa bits in binary point. If the biased exponent is 0 and the mantissa is 0, the number is 0.0. If the biased exponent is 0 and the mantissa is not 0, the number is subnormal and is calculated as follows. F for the floating point number equals negative 1 to the sine times 2 to the negative 26 times 0 dot and the mantissa in binary point. Essentially, the exponent negative 126 can be used with 1 dot mantissa for the normal case and 0 dot mantissa for the subnormal case. If the biased exponent is 255, an exceptional state or error condition exists. If the biased exponent is 255 and the mantissa is 0, the number is plus or negative infinity. If the biased exponent is 255 and the mantissa is not 0, the number is NaN or not a number. Okay, now let's go through some examples. So we're going to go through several float32 values. In the upper left here, we have the bits for the 32-bit float value. In the upper right, we have the human-readable typical decimal representation of that floating point value. And just below it, we have the hexadecimal value of the 4 bytes that make up the 32-bit floating point number. Probably for this section, the biggest focus will be the bit patterns as well as the decimal human readable variation of the number. But the hexadecimal number is provided in case you have an interest in relating that to the binary patterns. So let's start with the formula. We have f for the floating point value equals negative 1 to the sine bit times 2 to the biased exponent minus 127 times 1 point and the mantissa in binary point. So remember that 1 dot mantissa is binary point, not decimal point. But the one in the upper left is decimal point of the floating point number. So you can see in the upper left the human readable decimal point, but as we go through solving these, we will be using binary point for the mantissa. So we have a sine bit of 0, that's negative 1 to the 0, which is going to end up being 1. We have 127 for the exponent, so that's 2 to the 127 minus 127. So that's 2 to the 0. And then our mantissa bits are 0, but there's that implicit 1 point and then the mantissa. So our total mantissa value is 1 point and all zeros, or just 1. Therefore, we end up with 1 times 1 times 1. Essentially, we have that mantissa 1 point and all 0 bits, and the other multiplying factors are both 1, so there's no shifting around going or anything like that. The number is just 1.0. And you can see the bit pattern here with the 0 sine bit and 127 in the biased exponent. And remember, we subtract 127 from that in order to get to the real exponent, and then we raise 2 to that real exponent. In this case, it was 2 to the 0, and in a sense, that yield a exponent factor of 1. So we had the sine of 1, the exponent of 1, and those kind of are a wash, right? They don't affect anything. And then we're just left with the mantissa, which is 1 point and all zeros, which is just 1, and that's 1.0. And so that's a fairly simple starting example. Okay, for the second example, let's get fun with some fractional bits. So we'll say that the number is 1.5 in decimal. And we can see the bit pattern is almost the same as 1.0. You can see 127 for the biased exponent, but if you look at bit 22 of the mantissa, you can see it's set, where in the prior example, it was not set. So we've changed one bit here, and that's that highest bit of the mantissa. The formula that we're going to use here is the same, so we won't go through that again. And so we bring those values down. The sine bit is 0, so that's -1 to the 0, which is a 1. The biased exponent is the same as the prior example. That's 127 minus 127. So our real exponent is 0. 2 to the 0 is 1. So we got 1 times 1 with the sine and the exponent. And in a sense, that 1 times 1 is sort of a wash. We don't really care about it. We can just push it aside. And we're simply left with the mantissa. Because the biased exponent is not 0, which would be that special case that causes the mantissa to be 0 dot, but that's not what this case is. This case is the more typical case where the biased exponent is non-zero, and so the mantissa has that implicit prefix of 1 dot, and then the highest mantissa bit, which is actually part of the format, has been set to 1 at bit 22. That gives us a resulting mantissa value of 1.1 in binary point. And so for the mantissa, we have 1.1. Well, 1 is the whole number 1, and then we have .1, and if you recall from our earlier binary point discussion, .1 is a 1 in that first fractional place, which would be the place that represents 2 to the -1, and it represents a count of 1 value of 2 to the -1. And 2 to the -1 is 1/2, so 1/2 is just 1/2. That's kind of a long way to say it, but essentially that first binary point position, .1, is the halves place. And so we have 1 in that place, so that's 1 of a half, if you will. And so what is that whole number 1 plus the half? Well, that's 1.5. So the floating point value f equals 1.1 in binary point, or 1.5 in decimal. Okay, for the next example, let's use 2.5. So the prior one was 1.5. This is going to be 2.5. So the formula is the same, so I'm not going to go through that again. And so the sine bit is 0, so we have -1 to the 0, which is a 1. The biased exponent in this case is 128. So 128 minus 127 leaves us with 1. So we have an unbiased exponent of 1. And so if we raise 2 to the unbiased exponent of 1, or just more simply 2 to the 1, any number raised to itself is itself. So in this case, the resulting value is a 2. So we have a factor of 1 for the sine, and we have times 2 for the exponent, and then all that gets multiplied to the mantissa. This time the highest bit of the mantissa is 0. That bit 22 is 0. Bit 21, however, this time is 1. So this results in an overall mantissa value, if you will, of 1.01. So the sine factor, if you will, is a 1. The exponent factor, if you will, is a 2. And the mantissa factor is 1.01 in binary point. Well, we multiply 1.01 by 2. And you know what happens when we multiply by 2? We end up shifting bits. And which direction do we shift them in? We shift them to the left. We're multiplying by 2, and so we shift to the left 1 time. When you take binary point 1.01 and you shift it to the left once, what do you end up with? You end up with 10.1 in binary point. Let's take the whole number portion first. What's 10 in binary? Well, there's a 1 in the 2's place and a 0 in the 1's place. So that's a value of 2. And what's 1 in that first fractional place, .1? Well, we know that's a half. So what do we have here? We have 2.5. So 10.1 in binary point is equal to 2.5 in decimal point. All right, let's go to the next example. Okay, for this next example, let's use the same value as the prior example, but let's change the sign bit so that it's negative. So for this example of -2.5, we pretty much have the same bit pattern, except the sign bit has changed from a 0 to a 1. And this ends up changing the exponent that we raised -1 to. In the prior example, the sign bit was 0, so we raised -1 to 0, which yields 1. In this example, the sign bit is 1, so we raise -1 to 1, which yields -1. And that value gets multiplied to the exponent and the mantissa, and those are the same values as the prior example. So we still end up with 10.1 in binary point, or 2.5, except this time the factor created by the sign bit is -1 instead of 1. And because it's -1, it negates the value, creating a negative floating point value. So you can see how negative 2.5 in this example compared to positive 2.5 in the prior example uses the same bit patterns, except that the sine bit has changed from 0 to 1, and that change affects the factor that gets derived when you raise negative 1 to the sine bit, which in this case is 1. And raising negative 1 to that 1 yields negative 1, whereas in the prior case of a positive number, raising negative 1 to 0 yields a value of 1 as that factor, which has no negation properties at all, and it essentially is like a wash, right? It kind of just leaves the value whatever it is. All right, let's go to the next example. All right, this next example is going to be 0.5 in decimal. So the biased exponent is not 0, so we're going to use the same formula we've been using. The sine bit is 0, so negative 1 to the 0 is 1, and so that means we have this factor of 1, so we're not going to really worry about that because it's not going to negate anything or change anything, so we push that aside. Then we have a biased exponent of 126. We subtract 127 from that, and that gives us a final or actual exponent of negative 1. 2 to the negative 1 is 1/2, or 0.5 in decimal. And all the mantissa bits are 0, so we have a resulting mantissa factor, if you will, of 1.0. And 1.0 is 1. It's 1 whole, 1.0. So our factors are 1 for the sine bit, and we don't really need that because it's just a 1, right? So it's not going to change anything. The exponent is 1/2 or 0.5 in decimal, so that will affect the resulting value. We multiply that by the mantissa, which is 1 point and all those zeros. 1/2 of 1 whole is 1/2. Another way to look at it is 1/2 times 1.0 in binary point shifts those bits over to the right by 1. Shifting 1.0 over to the right by 1 yields 0.1 in binary point. 0.1 in binary point is 0.5 in decimal. All right, let's move on to the next example. All right, let's get kind of gnarly here and use something that's a little more involved. This number in decimal is 0.65625. The sine bit is 0, so negative 1 to the 0 is 1. And with that factor of 1, we just kind of put it aside because it's not going to change anything. We have a biased exponent of 126, so 126 minus 127 is negative 1. So that's 2 to the negative 1, or 1/2. So we have an exponent factor of 0.5 in decimal, or 1/2. Our mantissa begins with 1 dot, and the actual mantissa bits have 0, 1, 0, 1 all the way over to the left. So our resulting mantissa value is 1.0101 in binary point. So the exponent factor, if you will, is 0.5 in decimal, or we know 1/2 like that in decimal is 0.1 in binary point. This is showing 0.5 in decimal for the exponent portion. And so we're multiplying the mantissa bits by 1/2, which is equivalent to multiplying them by 0.1 in binary point. Effectively shifts those bits over to the right. Remember with binary that shifting to the right is dividing by 2. These mantissa bits are effectively halved by shifting over to the right. And when you shift them over, the 1.0101 in binary point becomes 0.10101 in binary point. So the floating point value is 0.10101 in binary point, or 0.65625 in decimal. All right, let's go to the next example. This example is using a biased exponent of 4, and the lowest mantissa bit is set to 1. Now notice in the upper right corner, we see 0 point and all zeros. We don't see a value there. And that's because until this point, we've been showing fixed point decimal up in that corner. And we're only showing 9 places of precision there. And that's not enough to show what the value of this number is. So we're going to have to introduce scientific notation. So let's do that. Oh, very good. Now we can see the number's value. It's 9.4039555928 times 10 to the negative 38. So you can calculate 10 to the negative 38 and multiply it times 9.403955,928. Now you know when you multiply a decimal number by 10, you can shift that decimal point around. And in this case, we're multiplying it by 10 to the negative 38, which is an extraordinarily small fractional number. And effectively, it's shifting that decimal point over to the left 38 times. all the way out, and then you have 9, 4, this number that I just read. All right, in this case, the biased exponent is not 0, so we're going to use the same formula. The sine bit is positive, so that's -1 to the 0, and again, that's a 1, so we don't really care about that. We're just going to put it aside because it's a factor of 1. It's not going to change anything. We have a biased exponent of 4, so we subtract 127 from 4, and that gives us an actual exponent of -123. We raise 2 to the -123, and that ends up creating an extraordinarily small fractional number. That mantissa starts with 1 dot and then has all zeros, and then the last bit is set to 1. And that's binary point. So we have 1 point and all zeros to the last mantissa bit, which is 1 in binary point. So 2 to the -123 is 1 over 2 to the 123. And if we take that and multiply it by the binary point, 1 point and all zeros and that 1, so now I did this in a calculator, so I'm just going to show the result of that. And that comes out to 9.4 blah, 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 times 10 to the -38. So for these kinds of examples, we won't show that full binary point number and whatnot. We're just going to show the resulting calculation. All right, let's go to the next example. All right, for the last example, we're going to do one subnormal example here. So this one's going to have a 0 sine bit, a 0 biased exponent, and all 0 mantissa bits except for that lowest mantissa bit, which will be 1. And in this example, since the biased exponent is 0, that's the special case that indicates that our exponent is not only -126, but the mantissa begins not with 1 dot, but with 0 dot. So in this case, the formula is slightly different. In this case, the formula is -1 to the sine times 2 to the -126 times 0 dot and the mantissa in binary point. So for the sine bit, we have -1 to the 0, which is that 1 that we don't care about because it's a factor of 1. It's not going to change the number when we multiply it, so we can just put that aside. The biased exponent is 0, which means our real exponent is -126. So 2 to the -126 is 1 over 2 to the 126. And then we multiply that value to 0 dot and all zeros except for that 1 mantissa bit. And that's in binary point. So this number in 32-bit float is a very, very, very small number. And it's within that so-called subnormal range. And so the result is 1.4 and a bunch of numbers here times 10 to the -45, which is an extraordinarily small number. So it ends up shifting this decimal point all the way over to the left 45 times. So you can imagine all these digits way out after a bunch of zeros past a decimal point. Very small number. I'm not going to even bother putting the binary point here, just as with the last example. All right, that's it for these examples. Just a little dive in so you can see some of the values and how we derive the final value given the different components of the format. All right, let's go on to the next section. In this section, we will cover some fundamental concepts about how 32-bit float samples are captured and how 32-bit float as a format, when coupled with a capable audio interface implementation, can allow for recovery of a signal that has exceeded 0 dBFS or 1.0 in floating point. The 3 examples in this section will use the same 3 signal amplitude levels that we used in the 24-bit ADC section earlier in this video. In that earlier section, the first sample was not clipped, but the second 2 examples showed samples that were clipped. When we approach the same 3 example amplitude levels in this section, all 3 samples will be successfully captured. That is, they won't be clipped, despite 2 of them exceeding 0 dBFS. We will approach the examples in this section by using a simplistic conceptual dual-ADC floating point audio interface design. This is mostly to convey or to show some general concepts through the use of 2 ADCs and a DSP processing the same example signals that we went through in the earlier 24-bit ADC section. In this section, our simple conceptual 32-bit floating point interface made up of 2 ADCs and a DSP will be able to produce a 32-bit floating point sample for each of those 3 readings, and will be able to retain the full signal detail relating to those 3 readings. It will do this despite the signal level exceeding 0 dBFS for 2 of those 3 readings. This section uses a simplistic, very conceptual design for a 32-bit floating point audio interface. It does not express or cover the multitude of detail one might find in a real-world design of such an interface. Our conceptual illustrative dual-ADC audio interface consists of a sound source fed to its input, so the sound source is like a microphone, a preamplification and conditioning stage, which will split the signal to two ADCs, ADC1 and ADC2. ADC1 and ADC2 receive the same signal, except the signal going to ADC2 is attenuated or lowered 4 times than that of the signal going to ADC1. We might say that the signal going to ADC2 is about 12 dB lower than the signal going to ADC1. Therefore, ADC1 is meant to handle what we can generally refer to as normal signal levels, and ADC2 is meant to handle what we might refer to generally as loud signals, or signals that might be too loud for ADC1, causing it to produce a clipped sample. Both ADCs will observe the same signal, but at different levels. The DSP will receive a sample from each ADC for each sample period. The DSP will use those two samples to ultimately produce a floating point sample output for the sample period. The DSP will figure out which sample to use, if not both, perhaps perform some other processing, maybe managing overlapping ADC coverage, and so on and so on. In this simple conceptual overview, we're going to keep things very simple. In these following examples, the DSP will basically use ADC1's sample if it's not clipped. If ADC1 provides the DSP with a clipped sample, the DSP will use ADC2's sample. There will be no advanced processing or anything like that discussed in these examples. The point is to follow some of the concepts from sampling the voltage of the signal through the two ADCs, through the DSP, and to a floating point sample. At the very least, this section should convey some of the notions or concepts relating to the different values at different stages in this sort of pipeline here. You have voltage readings, you have 24-bit samples, you have floating point samples, and then you have a final sample that's output. Of course, this is a very simplistic overview, but it should be good enough to convey some general concepts, and will allow us to apply some of the concepts discussed in earlier sections of this video, such as using sample ranges, producing ratios, and using those ratios as part of converting from a source to a destination format. The real-world subject matter in the area of ADCs, audio, noise, all that kind of stuff, quite involved, quite vast, not the subject of this video. So treat the ADC and DSP design stuff here as very simplistic and conceptual to give us that framework to play around with the audio sample formats that we learned about in earlier sections. Our focus in this video is the binary formats themselves, 24-bit signed integer, 32-bit floating point, and kind of understanding the formats themselves and how we might look at them from, let's say, a software perspective. Let's replace our 24-bit ADC audio interface with our conceptual 32-bit floating point audio interface. The interface will use two ADCs, with ADC1 being given the normal or unattenuated signal, and ADC2 being given the attenuated or lowered or reduced level signal. ADC2 is attenuated 4 times, or is given a signal that is 4 times lower than the signal being given to ADC1. ADC2's signal is about 12 dB lower than ADC1's input signal. The signals are otherwise the same. ADC1 will therefore handle normal level signals, while ADC2 will handle signals that are clipped by ADC1. The DSP will receive a sample from each ADC for each sample period. The DSP will then use those samples to produce a 32-bit floating point sample. We assume that each sample output by the DSP for each sample period is used immediately by an audio app, or it's written to a WAV file for later use by an audio app. In this section, both ADCs will have the same VREF minus and VREF plus as we saw in the earlier sections. That's negative 2 volts to positive 2 volts. Note that each ADC in this section is limited by that plus and minus 2 volt limit. Both ADCs in this section will clip if a signal exceeds the 2 volt VREF limit. That is completely unchanged from our previous 24-bit ADC example. However, in this example, since ADC2 is attenuated or lowered 4 times compared to ADC1, any level going to ADC1 will be 4 times lower when going to ADC2. Therefore, we assume ADC1 and ADC2 are the same type of 24-bit ADC, but that the gain reduction applied to the signal sent to ADC2 allows for it to properly sample far above the limits of ADC1. A key point here is that the samples produced by ADC2 are 4 times lower than what the actual signal is with respect to ADC1. We know that ADC1 will clip for many of the samples successfully captured by ADC2. For simplicity, the following examples will focus on the positive voltage range from 0 volts to plus 3 volts. We see here that ADC1 detects a 1.5 volt signal level at its input. At the same time, ADC2 detects a 0.375 volt signal. Since ADC2's input is attenuated 4 times, you can arrive at that 0.375 volts by taking the signal level going to ADC1, which is 1.5 volts, and dividing that by 4. You'll get 0.375. That's 1/4 the level of ADC1's input. Or we might say that ADC2 is reading the same signal at 1/4 of the amplitude when compared to the input going to ADC1. ADC1 observes 1.5 volts of a 2 volt max. That's 1.5 volts over 2 volts, which is 0.75. This means ADC1 detects a signal at 0.75 or 75% of its potential range. 0.75 of 2 to the 23, or 0.75 of the maximum 24-bit sample value, is a 24-bit sample value of 6291456, which, by the way, is the same sample value from the earlier section in this video where the 24-bit ADC observed a similar 1.5 volt input signal. I'm trying to draw some parallels with that section because it was depicting a 24-bit audio interface using a 24-bit ADC. This example is using 2 24-bit ADCs and a DSP to ultimately create a 32-bit floating point audio interface. And so seeing those relationships and being able to compare the two sections might be something you find interesting. ADC2 observes 0.375 volts of a 2 volt potential, which is 0.1875 or 18.75% of that 2 volt potential. Using that ratio of 0.1875 or 18.75%, if we take 0.1875 of 2 to the 23, we get a 24-bit sample of 1572864. As part of processing for this sample period, the DSP will obtain both of these samples that were just created by each ADC. As part of its initial processing, at least for its own internal use, the DSP can convert those two samples into floating point. It does this by creating a ratio with the sample value over 2 to the 23. Our example will be simple in how it uses these two samples from the ADC, but the ADC could use these floating point samples to engage in more advanced processing that we won't discuss here. The point of mentioning this is that the DSP can work in floating point as part of its internal processing leading up to producing the needed samples. The DSP can work in floating point, and it can take samples it gets from both ADCs and use them with internal floating point operations as part of its overall processing and decision making. In this simple example, the DSP sees that ADC1's sample is not clipped, so it uses the floating point value derived from ADC1's sample as the floating point sample it outputs for this period. To recap, both ADCs observed a signal, one 4 times times lower in amplitude than the other. The unattenuated ADC signal was not clipped, so the DSP used that to produce a floating point sample that it output for this sample period. Okay, now for the next example. ADC1 detects a 2.5 volt signal at its input. ADC2 detects 0.625 volts for the same signal at the same point in time, albeit the signal it's seeing is 4 times lower than the one that ADC1 sees. You can calculate this on your own by taking 2.5 volts and dividing it by 4, and you'll come out with 0.625 volts. Right off the bat, we can see that ADC1's signal exceeds the VREF limit of 2 volts. So ADC1 will provide the DSP with the highest possible sample value, which is 2 to the 23 minus 1. And remember, the minus 1 is because of the 2's complement anomaly, and ADC1 has no choice but to provide that maximum sample value because the input signal has exceeded its maximum range. Therefore, the DSP will receive from ADC1 a sample of 8388607, or in hex 0x7f FF. The sample provided by ADC1 to the DSP in this case is worthless beyond conveying the error information that clipping has occurred, and the DSP can use that information. In contrast to ADC1, ADC2 detects a signal of 0.625 volts. 0.625 volts is well below the 2 volt limit. 0.625 volts over 2 volts yields a ratio of 0.3125. This reading is therefore at 0.3125 of the 2 volt range. Multiplying the maximum 24-bit sample, 8388608, or 2 to the 23, to that ratio, 0.3125, yields a 24-bit sample of 2621440. The DSP receives both samples from both ADCs. It observes that the sample from ADC1 is the maximum 24-bit sample value. This causes the DSP to assume that sample is clipped. Therefore, beyond that observation by the DSP, it puts the sample from ADC1 aside and focuses on using the sample from ADC2. The DSP converts ADC2's 24-bit sample into a floating point sample. It does this by taking the sample value and dividing it by 2 to the 23, or 8388608, which is the maximum 24-bit sample value. So 2621440 over 8388608 equals 0.3125. Does that ratio look familiar? The DSP's design is aware of the attenuation applied to the signal input of ADC2. The DSP therefore multiplies that sample of 0.3125 by 4. In a sense, you can think of that as undoing the attenuation that occurred earlier. Take note that multiplying the sample by 4 also multiplies any noise induced by the ADC itself, including any self-noise, any noise from quantization errors, and so on. As mentioned earlier, we're not going to discuss details at that level, nor will we discuss real-world dual-ADC audio interface design details. 0.3125 times 4 is 1.25. So the DSP now has an effective, unattenuated floating point sample from ADC2. That sample value is 1.25. You might note that that sample value of 1.25 is what you will obtain with the ratio of the input voltage for this sample to ADC1 over 2 volts. If you take 2.5 and divide it by 2, you'll arrive at 1.25. We might also observe from this that the input signal to ADC1 was about 25% over the VREF limit. So for this sample period, the DSP outputs a floating point sample of 1.25. All right, for the next example, ADC1 detects a 2.8 volt signal at its input, while ADC2 detects 0.7 volts for the same signal at the same point in time. And as with the prior examples, we can take 2.8 volts, which is what ADC1 detects, and we can divide that by 4 to arrive at the attenuated signal that ADC2 detects, which is 0.7 2.7 volts. ADC1's reading of 2.8 volts exceeds the 2 volt maximum, so the reading is deemed clipped, causing ADC1 to send the max 24-bit sample to the DSP. Given 2's complement, that would be 2 to the 23 minus 1, or 8388607. ADC2's reading of 0.7 volts is 0.35 of the 2 volt range. 0.7 volts over 2 volts produces a ratio of 0.35. 0.35 times 2 to the 23, or 8388608, yields a 24-bit sample of 2936013, which it sends to the DSP. The DSP receives each ADC's sample. It observes that the ADC1 sample is the maximum sample value, and so rejects that sample and moves on to the sample from ADC2. It uses ADC2 sample 2936013 to produce a floating point value, 2936013 over 2 to the 23, or 2936013 over 8388608. That produces the attenuated floating point sample of 0.35. Therefore, ADC2 has effectively been able to provide the DSP with a floating point sample of 0.35. And like with the prior examples, the DSP's design is aware that ADC2's samples are attenuated 4 times lower than those from ADC1. Therefore, the DSP can effectively remove that attenuation by multiplying the sample value by 4. 0.35 is the attenuated sample. Multiplying it by 4 produces a floating point sample of 1.4. You might have noticed the actual ratio produced by the DSP is not precisely 0.35, nor is the scaled result precisely 1.4. Each has more digits of precision. The final 32-bit floating point sample will express as much precision as allowed by the 32-bit float format itself. In this case, the final floating point sample will be the floating point number expressed with the full 32 bits shown here. And you can see ADC1 observed the unattenuated signal at 2.8 volts. It clipped at that level. But we know for ourselves in this example scenario that its reading was 2.8 volts. And 2.8 to 2, or 2.8 over 2, produces a ratio of 1.4. So one way of looking at this is that ADC1 could not handle that 2.8 volt reading. However, ADC2 could handle that 2.8 volt reading so long as it was attenuated to 0.7 volts. That attenuation allowed ADC2 to obtain a sample of it and to provide that sample to the DSP. The DSP, having knowledge of the design, used its knowledge of the attenuation to effectively remove that attenuation by multiplying the attenuated floating point sample by 4. So for this sample period, the DSP outputs a floating point sample of 1.4. Now, these examples don't get into the details of the preamp, any kind of conditioning, filtering, any sort of ADC build quality issues, noise floor related issues to the build quality of the ADC, and relating to the signal coming into the audio interface. We didn't discuss any analog chain issues and so forth. And we're also performing the simplest form, most rudimentary form of calculations in a very simplified example. The idea is to not only introduce the 24-bit sample format as we did, but also the 32-bit sample format, and to kind of show some interrelationships between those two in this simplified version of what might take place conceptually. Even without all those details discussed or, the many deep dives you could take, which would be so many different videos, most likely, hopefully you get a hint, at least from these very simple examples, on the nature of some of the relationships between these formats, converting from one format to the other, how ratios can be used to help with those conversions, and that the floating point sample, in a sense, is a ratio. And how that ratio is very useful at finding out what a sample's value might be in some other format. And given a lot of the discussion about dual ADC arrangements, hopefully you found these examples to act as a little bit more of an overview than some of the simple diagrams that might be shown. However, even without all those details, and even though these examples were relatively simple in a rudimentary, very sort of basic conceptual, sort of illustrative example, hopefully you found it useful to appreciate some of the different formats and converting from one format to the other and the various ratios involved. And it's kind of interesting to see that 32-bit floating point samples are by themselves, in a sense, ratios. I mean, you could say that even the 24-bit sample represents a ratio, but given its relatively lower precision compared to floating point, it's not naturally as precise of a ratio as a 32-bit float sample. And not to say that a 32-bit float sample means you have great audio. We know it doesn't, but given the precision of that format, it becomes very useful when you need a ratio to express something about an audio sample with respect to maybe some other system that you're converting to, or in relation to some other processing you're doing with audio data. All right, that's it for these examples. Let's go on to the next section. One thing that can be helpful when learning about or otherwise examining large ranges or large magnitudes is to find ways to look at or visualize the information. The following are various ways we can view a comparison of the resolutions of the two different number systems, 24-bit signed integer and 32-bit floating point. First, let's clarify that both 24-bit audio samples and 32-bit floating point audio samples each express the ratio of an audio signal with respect to 0 dBFS. 0 dBFS being the maximum signal a digital audio system can handle before clipping. 24-bit signed integer samples, or 24-bit samples, can only express a ratio from -1.0 to 1.0. Or if we're sticking to just the positive portion of the range just for simplicity in discussing this, we can say that 24-bit samples express a ratio from 0 to 1.0 of the whole of 0 dBFS. In other words, the maximum value of a 24-bit sample is 0 dBFS, is that clipping point. 24-bit samples, therefore, don't have any values above the clipping point, even if you have an audio interface that can somehow capture audio signals above 0 dBFS. If the 24-bit sample format is being used in the normal way, it doesn't really have any room to hold any such samples like that. Now, the 32-bit floating point format can certainly represent values from 0.0 to 1.0, the same as the full range of the 24-bit sample format, but the 32-bit floating point format can express values much higher than 1.0. And values higher than 1.0 are beyond 0 dBFS. So if you have a way of capturing a very wide dynamic range of audio, you can spread the representation of that out over 0.0 to 1.0 or within the range up to 0 dBFS, but you're also free to capture higher amplitude signals and maintain those in higher values. Now, in the following comparisons, we're going to focus on the range from 0.0 to 1.0 of both the 24-bit signed integer format and the 32-bit floating point format. So for the portion of the audio signal that 24-bit audio can represent, which is up to 0 dBFS, we're going to compare the resolution of that range with the same value range of 32-bit floating point. And for the sake of resolution comparisons, we're going to ignore the negative ranges. So we're not going to include 0.0 to -1.0 in our comparisons. And this is because the negative range won't add anything to the comparisons, as it's just a mirror of what we'll be discussing in the positive range. The following shows each tenth increment from 0.0 to 1.0 for both formats. Notice how the 32-bit format has much more precision for each tenths increment than does the 24-bit signed integer format. Next, we see a graph showing the general relationship of resolutions of both formats across each tenths segment from 0.0 to 1.0. The plots showing exponents are approximations since some exponents span multiple tenths sections. You get a sense for the number of exponent ranges, if you will, of the 32-bit format that are used across the range from 0.0 to 1.0. Notice how the 24-bit signed integer has a flat line indicating its linear nature in terms of the distribution of its steps along the way from 0.0 to 1.0. That compared to the logarithmic-like nature of the distribution of the 32-bit resolution across the range from 0.0 to 1.0. Next, we have another comparison of the 32-bit and 24-bit resolutions. Again, for the value range 0.0 to 1.0. This graph emphasizes the use of the exponent ranges of the 32-bit floating point format across that range and in relation to the usage of the 24-bit format's resolution. Looking at this graph more closely, we see that the 32-bit range from 2 to the -1 to 2 to the 0, 1/2 of the entire available resolution of the 24-bit format is used to represent that same range. Similarly, for the 32-bit floating range 2 to the -2 to 2 to the -1, we see that 1/4 of the available resolution of the 24-bit format is used. Or you might look at it as 1/2 of the remaining amount after that first half was used for that other range we just talked about, and so on and so on. And watch as the Y resolution axis animates to stretch itself out, which emphasizes the relatively low resolution available to represent lower end values when compared to the resolution available in the 32-bit format. With regards to the value range 0.0 to 1.0, the resolution of the 32-bit floating point format breaks down as follows. You have the exponent ranges 2 to the -26 to 2 to the 0. That amounts to 127 exponent ranges as follows. 2 to the -26 for the subnormal range. That's when that BIOS exponent is 0. Then we have 2 to the -26 to 2 to the -1 for the normal range. And we're going to exclude 2 to the 0 since it's really only used for the value 1.0. Now you can use values above that in 32-bit floating point, but keep in mind we're comparing 24 and 32-bit float for the value range 0.0 to 1.0. And for this reason, we're not going to include the entire 2 to the 0 exponent range because its entire range is not used to represent values that are available in the 24-bit range, if that makes sense. Each exponent range is made up of 23 fractional bits. That excludes that implicit mantissa prefix that's either 1 point in the mantissa or 0 point in the mantissa. Therefore, we have 127 exponent ranges, each consisting of 2 to the 23 different possible values. That's about 1 billion possible values for the range 0.0 to 1.0 in the 32-bit floating point format. The resolution for the 24-bit format for the value range 0.0 to 1.0 is a little more simple. It's basically 2 to the 23 different possibilities for that positive range from 0.0 to 1.0. That's about 8 million different possible values that the 24-bit format can represent when expressing values in the range from 0.0 to 1.0. If you want to compare the resolution of both of these formats, well, one way to think about this, there's a 23-bit mantissa in the floating point format and a 23-bit integer representation in the 24-bit format. However, you get 127 of those in the floating point format and only one of those in the 24-bit format. Again, for the range 0.0 to 1.0. So we can see for the value range 0.0 to 1.0, the floating point format has 127 times the resolution that the 24-bit format has. And this doesn't even begin to speak of the resolution and bit space that it has above or outside the range of the 24-bit format in order to maintain a wider dynamic range of audio. All right, let's go to the next section. In this section, we simulate recording a live event 3 times with a Zoom F6 recorder. Once in the 24-bit format, another time in the 24-bit format, but with the limiter enabled, and a final time using the 32-bit floating point format. Each recording will start at normal audio levels, or below 0 dBFS, or below the clipping point, and will gradually increase in level until it goes above the clipping point, or above 0 dBFS. We do this to intentionally see how each format handles the supposedly clipped audio. I qualify this with the word supposedly because the audio will end up not being clipped in some of the recording. After capturing each recording, we'll compare the results. The source audio will be played through headphones and recorded by a nearby microphone in order to ensure the recording of the live event is consistent across all tests. This ensures a reasonable baseline comparison for the goals of this section. The full length of each recording is presented, but you can skip to the results if preferred. We place the microphone next to the headphones, which simulates our live recording. We didn't have to use a live recording like this, but for certain viewers, it could emphasize the nature of the test by actually performing a live recording. What you hear right now is the camera's audio with ambient room noise and is not part of the test. This recording will be captured without a limiter and written to a 24-bit audio file. And we'll begin recording. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1. The quick brown fox jumps over the lazy dog. 2. The quick brown fox jumps over the lazy dog. 3. The quick brown fox jumps over the lazy dog. 4. The quick brown fox jumps over the lazy dog. 5. The quick brown fox jumps over the lazy dog. And now we're back to the camera audio, which is not part of the test. And we'll stop recording. And now let's prepare the recorder to record in 32-bit audio. And let's start the recorder and begin the 32-bit recording test. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1. The quick brown fox jumps over the lazy dog. 2. The quick brown fox jumps over the lazy dog. 3. The quick brown fox jumps over the lazy dog. 4. The quick brown fox jumps over the lazy dog. 5. The quick brown fox jumps over the lazy dog. And now we're back to the camera's audio, which is not part of the test. And we'll stop the recorder. Now let's prepare the recorder for 24-bit recording with the limiter enabled. Start recording 24-bit with the limiter enabled. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1. The quick brown fox jumps over the lazy dog. 2. The quick brown fox jumps over the lazy dog. 3. The quick brown fox jumps over the lazy dog. 4. The quick brown fox jumps over the lazy dog. 5. The quick brown fox jumps over the lazy dog. Stop the recording. We're going to load all 3 recordings into Reaper as separate side-by-side tracks useful for comparing recordings. For those not familiar with Reaper, it is a digital audio workstation, or DAW. If you're not familiar with what a DAW is a professional-grade audio processing and production application useful for a wide variety of tasks, including analyzing and comparing test results, as we will do here. Next, we're going to normalize all 3 recordings to 0 dB. And when I click OK, watch the peaks. The bottom one is 32-bit. Okay, track number 1 is 24-bit without the limiter. Track number 2 is the 24-bit recording which had the limiter enabled. And track number 3 is the 32-bit float recording. Now, let's zoom into the tracks a bit. Let's find an area of the recordings that has relatively significant variations in amplitude. Okay, this is a good area here. It looks like we have clipped, limited, and recovered audio. All right, let's solo the first track, the 24-bit track without limiter. And for those not familiar with the term solo, it means we're going to listen to that one track alone. 9, 10, 1. The quick brown fox jumps over the lazy dog. 2. The quick brown fox jumps. And you'll notice this 24-bit recording without limiter has non-recoverable clipping indicated by the flat tops. As well, it has that distortion indicative of clipping. Over the lazy dog. 3. The quick brown fox jumps over the lazy dog. 4. The quick. Next, we solo track 2, which is the 24-bit recording with the limiter enabled. 8, 9, 10, 1. The quick brown fox jumps over the lazy dog. 2. The quick brown fox. And you'll notice the 24-bit recording with limiter is not clipped and has no flat tops in the waveforms. And it definitely sounds better than the 24-bit recording that is clipped, but it has still lost something. And we'll outline that in a second. Jumps over the lazy dog. 3. The quick brown fox jumps over the lazy dog. 4. The quick. All right, now let's solo the third track, the one with the 32-bit float recording. 9, 10, 1. The quick brown fox jumps over the lazy dog. 2. The quick brown fox jumps over the lazy dog. 3. The quick brown fox jumps over the lazy dog. 4. The quick brown fox. And you can see the 32-bit float recording retained the relative amplitude detail throughout the recording. We not only don't see clipped samples, but all the samples are not peaked at the top as happened with the limited 24-bit recording. What you can see is lots of peaks and valleys that represent the original texture to some reasonable degree when compared to the other two recordings. Jumps over the lazy dog. 5. The quick brown fox jumps over the lazy dog. Let's go back to track 2, the 24-bit recording with the limiter, and notice the lost amplitude detail compared to the 32-bit float recording. The quick brown fox jumps over the lazy dog. 4. The quick brown fox jumps over the lazy dog. 5. The quick brown. And back to the 32-bit float recording. The quick brown fox jumps over the lazy dog. 4. The quick brown fox jumps over the lazy dog. 5. The quick brown. With the 32-bit float recording, you can see and hear the retained amplitude detail. This is all to say that a limiter does not replace 32-bit float recording. And to the extent you use 24-bit recording, a limiter is not replacement for proper setting of your levels. But going back to the 24-bit recording without limiter, the clipped 24-bit recording, the quick brown fox jumps over the lazy dog. We can certainly see that having the limiter is much better than without the limiter. Okay, enough of the distortion. Let's turn this off. In the following section, I outline the steps I generally use when I set up a Python development environment on Windows using VSCode as the Python editor debugger. All right, the first thing we're going to do is navigate to python.org. And then on python.org, we're going to go and click on downloads. Now, I'm not going to download the default download, which is 3.13. And the reason why I'm not going to do that is I actually know that I'm going to be using some packages that last I checked, they were only compatible with Python 3.12. Now that may have changed, but it really doesn't matter. We can just use the latest 3.12 and that'll just be fine. And I'm going to scroll down here to the bottom of the page here where we'll see this Windows installer 64-bit, and I'll click on that. And once that's finished downloading, I'm going to click to install it, and the installer will start up. I'm going to click to close the browser so we can just keep the real estate kind of clear on the screen. Okay, next I'm going to click install, and it's going to install. Great, setup was successful. All right, great, Python's been installed. So I'll close the window here. Okay, now I'm going to hold the Windows key and press X, and then I'm going to go and click on Terminal to open up Terminal. You'll notice my terminal says PowerShell 7.5.0. That's because I do the side load of the latest version of PowerShell rather than rely on the default one that comes with Windows. So for the commands that we're going to run here, you probably shouldn't notice any difference. But just in case you do and you wanted to try out the other version of PowerShell, I just wanted to let you know. Okay, so I'm going to move my mouse here, wheel to just make the fonts a little bigger here. I may adjust this throughout depending. And also you might see this little shaded square here. That's because I have the keystroke, window thing down here. And so if you see that shaded thing down here, FYI. As we work on things throughout the video, I'll be putting those in demo. So from PowerShell, I'm going to use makedir mkdir, the name of the folder, and -force. And -force will basically create the full path even if some of the subdirectory components don't exist. And if any directories already exist, it won't show me errors that they already exist. So I'm going to press Enter. Okay, great. We have a directory. I'm going to clear the terminal window, and I'm going to change to that directory. Okay, and I'll just clear the window again so we start with a fresh, clean terminal. So when I installed Python, I didn't check any boxes to add Python to the path. And that's normally what I do because I usually use Python environments, which is what we're going to do here. And when you have a Python environment set up, it puts that version of Python on the path for you when you enable the environment. Okay, I'm going to type in Python -- version to see the version. I'm expecting this not to work because Python is not on the path. And I just wanted to, clarify that, make sure there wasn't some oddball version of Python installed somewhere on the path here. So we see that Python's not on the path. So I'm going to type in clear here to keep that terminal window clear. And after installing Python on Windows, when I want to find out where it's located, I'll press the Win key or otherwise open up the Start menu and I'll type in Python. That'll show various programs that were installed when Python was installed. I'll look for the version that I just installed, which is 3.12, and I'll look for the Python app. And then I'll just right click and choose Open File Location. And that will actually open up the location where the shortcuts are located. Now, the shortcuts are not the apps themselves, but are the things that were actually on the menu that I right clicked on. So we're looking at the shortcuts. So I'll right click on the shortcut and I'll choose Open File Location. And that'll bring me to the path that the shortcut points to, which is the path that we want. And you can see we're here where python.exe is located. So I can highlight the path in the address bar and right click and choose copy. And now I'm going to close the Explorer window and I'll go back to the terminal window. And I'm going to left click in the terminal window to paste the path there in the terminal window. Now with the path there, I'm going to put a slash and then I'll type in py and press tab and that'll complete with python.exe. Now I can type in -- version and let me actually expand out this window because it's a little too small. And actually I'm going to move this up to the top up here. And now I'm going to press enter and we see that it's Python 3.12.10, which is what we expected. So now I'm going to press the up arrow key to bring back that command line. And now I'm going to backspace and leave one dash there. And I'm going to type an M for module and then space and then VENV for VM. VM stands for virtual environment. And that's a module that can be used to create a Python virtual environment. So I have -m VM. And now what I want to do is I want to make a Python virtual environment and I want to put it in a directory underneath the demo directory. And so I'm going to specify the location that I want Python VM to put the virtual environment. And that location is going to be c:\demo. And I think I'm going to call it py 3.12-demo. And this is just something I do when I name my Python virtual environment directories. I prefix it with like py and the version number and then dash and then maybe what its purpose is. Okay, so let me make this window just a little bit bigger here because it's trimming that off there. So I'm going to hit enter. And Python's going to go and create this virtual environment. Okay, great, it's created. So next I'm going to type in the directory where the virtual environment is, and I'm going to add the name scripts. So I typed in scr tab, and PowerShell auto-completes with scripts, and then I'm going to do ACT and press tab, and I'm going to press tab until I see activate.ps1. And that's because I'm in PowerShell right now, so I want to use the activate.ps1, which is the activate PowerShell script. So when a virtual environment gets created, Python's nice enough to create some scripts in the virtual virtual environment that we can run from whichever OS we're in to actually start the virtual environment up for us on whichever operating system we're on. So in this case, we're on Windows with PowerShell, so I'm going to use activate.ps1. And some of this stuff may vary slightly depending on what OS you're on and what shell you're using, what terminal window you're using. There's another activate script in there that's called activate. And on Linux, you would kind of run that a different way by using a source command. It's really out of scope for this walkthrough right now, but I'm just letting you know that if you start using Python or virtual environments, let's say you're new to them, there might be different ways you do what we're doing here depending on the operating system and the shell environment that you have, the terminal window and all that stuff. Okay, I'm going to press enter and this should activate the virtual environment, and it does. And we can see that the virtual environment is activated because the prompt now in the terminal window has a parentheses. Within the parentheses is the name of the virtual environment. And I'm going to clear the window here just to get a fresh terminal window. And you can just see the prompt is always going to have that virtual environment name next to it. All right, so if we want to deactivate the virtual environment, we can type in deac and hit tab, and that's a deactivate command. If I hit enter, it will deactivate the virtual environment. So you can see our prompt is now restored. It no longer shows the name of the virtual environment. Okay, I'm going to use the up arrow to go back to the activate command, and I'm going to hit enter to reactivate the virtual environment. Okay, I'll clear the window. Okay, so we have a virtual environment. Now I'm going to type in Python without any special path prefixes or anything like that, and I'm going to hit enter. Notice it works. Notice it displays Python 3.12.10. Now this is Windows. I can use where.exe to go and tell me where it found Python, and it'll show me that it found Python in the demo virtual environment we just created. It's actually within that scripts folder. And so recall the initial steps I used to kind of bootstrap setting up the environment here had me doing all those steps to go find where the Python executable was actually located. But I don't really have to do that after I set up the virtual environment. All I have to do is know where the virtual environment is and run the activate script. And after that virtual environment is activated, Python of that virtual environment will be on the path. All right, so I'll clear the window here. So we're going to go through some walkthroughs and perform some experiments. And those walkthroughs and experiments require certain Python packages. So we're going to prepare the virtual environment by installing those packages now while we're here at the command line. So I'm basically going to paste a command line in here, and you can just go ahead and type in this command line as it's written. Now debug py at the end of the command line here, that allows VS Code to perform debugging, and that's what I'm going to use in the walkthrough here. And whether you need to install it as well, it depends on whether you're going to install VS Code. If you're planning on going through the tutorial step by step, you probably want to install debug py. So I'm going to press enter to start installing the packages, and they're going to start installing. They'll be downloaded from the internet, and pip is working on that right now. Now, after you first create a Python virtual environment, and you first use pip, which is the package manager, after pip finishes, you might see a message indicating there's a new version of pip and that you can upgrade it by running this command. Now, you don't necessarily have to go and run it. I actually run it because the message is there, so I just grab this, I copy paste it in, and just hit enter. You know, I don't make a big deal out of it. Sometimes I may not do it if I'm in a rush, or if I know that the Python environment may not be long-lived. It's up to you, but in this case, I'm going to run it. Okay, I'm going to clear the terminal window. Okay, so we've installed Python, we've set up a Python virtual environment, and we've installed the packages that we need in the Python virtual environment. And you know, actually, I'm going to close the terminal window because we don't need that right now. Okay, so next we're going to install Visual Studio Code or VS Code. So I'm going to type in code.visualstudio.com, or you can just search in your browser for VS Code and find the appropriate top link, which should go to a domain code.visualstudio.com. So I'm going to go ahead and I'm going to hit enter here to go to code.visualstudio.com, and I'm going to click download for Windows. And it's going to start downloading. I'm going to click to start the installer, and I'm going to go ahead and close the browser, and I'm going to click accept, and I'm going to click next, and I'm going to click next. And I had Visual Studio Code installed before, so it sees the folder already exists, so it's just asking me. I'm going to say yeah, and I'm going to click next. And you see these two things that say add open with code to Windows Explorer. I like to have those right-click Explorer context menu options, so I'm going to check both of these add open with code boxes, and then I'm going to go here and click next, and I'm going to click install, and we'll let it install. Great, VS Code's installed and it has a checkbox to launch it. So let's just launch it and make sure it starts up and everything looks good. Now when VS Code first starts up or after it's updated, it might show you release notes and you can read through those. I'm just going to click close, and that's it. It looks like VS Code's installed, so I'm going to close VS Code. All right, now that we've set up Python, we've set up our Python virtual environment, and we've set up VS Code, let's give VS Code a test drive in debugging a Python program to just make sure our environment is working well and that the debugger is set up correctly and all that jazz. Great, we've opened a terminal window, we've activated the Python environment, and we see that the Python exe that we're using is from that environment. That's what we would expect. Now let's create a directory underneath demo named testing. So I've got make dir c:\demo testing. I'm going to hit enter. And now let's start up VS Code on that same folder. So that would be code space and the folder name. And when we run that, VS Code starts up. That's great. We see that the testing folder is empty because we haven't put any files there yet. Let's right click and say new file. Let's type in example1.py. And .py is a Python file. Most of you probably know that. Okay, I'm just going to paste in a small little program here. And this small little program imports Numpy, which is one of the packages that we installed. And we imported it as the name np. So if we had just put import Numpy without the as mp, anytime we needed to reference that module within our current scope, within the current file, we would have to type numpy, N-U-M-P-Y. But when we put the as mp, we're basically instructing the Python interpreter, hey, this is the name that we want to call this module within this scope, within this file. And so everywhere in the file that we want to reference NumPy, we can just type in mp and dot and, access something in the module. And you can see we're doing that here with a equals mp array. So we have a small little program in here that uses the NumPy module. So most of you probably know NumPy, but for those of you who are driving along with the tutorial here and you're not really familiar with NumPy, here's a 2-second overview. So NumPy is this extraordinarily popular Python library package, basically, used by many types of applications. And it's also used by many other Python libraries, packages, basically, especially those used in the area of data science and AI and so forth. I mean, NumPy is everywhere, all over the place. It supports really fast array processing, and it includes a robust collection of high-level mathematical functions, which can operate on those really fast arrays. And it achieves this with a carefully thought-out architecture that strikes an impressive balance between use of the extraordinarily useful robustness of Python and the speed of carefully crafted native code living in the native space of Python. Maybe even more of a TLDR, it's a Python library that's very popular and it operates on arrays. It lets you create arrays, operates on arrays, and it does it really efficiently. And we're going to be using it in some of the walkthroughs. So here we're just creating a simple array with 3 integers, 1, 2, and 3, and then we print the array out. So before we move forward, I want to show you something really quickly. I'm going to click on this box up here to restore the window size, and I'm just going to move it out of the way of the keystroke window down here. There's a little keystroke window. So I'm just resizing it so that it's not blocking things there. And I want to show in the bottom right corner here, it has the version number and it says Pi 3.12 demo. If I hover my mouse over it, you can see it shows us the directory of the virtual environment that's being used. And this is a great way to kind of look down there really quickly and kind of see which Python environment you're using, if any. You can see it has the venv name Pi 3.12-demo, and it has VM to indicate it's a virtual environment. And if you click on this status bar location, like if I click on it now, it opens up this select interpreter dialog box. Now, as an experiment, let me just show you something. If I go and click on the global environment, which does not have NumPy installed, watch what happens. You can see that NumPy has squiggles now, and you can see it indicates that, hey, NumPy could not be resolved. If you see little squiggle marks like that, which indicate that the module can't be found, you're either using the wrong Python environment, or it could mean you're using the right Python environment, but you didn't install the correct package. Just keep that in mind. Now I'm going to go back and I'm going to click on the status box again, and it opens up this select interpreter box. Now notice here it has our virtual environment right down here where it's using the folder name that we used where we put our virtual environment. This is our python.exe from the virtual environment that we just created. Now notice how VS Code says global here. I'm not 100% sure, but I think this might be some kind of minor cosmetic bug or something. I may actually report this because I did some testing and I see sometimes it has venv there, and sometimes it has global for my virtual environment. It's always my virtual environment. So I think there's just probably something in the list box code here or something that needs tweaking. So just be aware of that. Sometimes you might see venv for your virtual environment. The best thing to do is go off the path of the interpreter. So if you see that the python.exe here is the one from your virtual environment, then likely that is your virtual environment, and this, if it says global, might not be accurate in that case. I assume that when this says global, it means the global environment or something like that. And when it says venv, it obviously means virtual environment. I'll show you what I mean by this. I don't have NumPy in the global environment, as you can see from the squiggles here, right? So if I go and click here, I can select this environment here, and it resolves the bug. So that's a virtual environment. So it's just probably a minor cosmetic bug, but I don't like to be assumptive about those, even when it looks really obvious. But since that wouldn't feel intuitive to me on some level, I think it's probably some minor thing. Just be aware of that if you're using it. Because if you're new to virtual environments or you're new to Python, that might confuse you if you see global. Frankly, I think if you're new, you might not actually be thrown by that. Maybe somebody who kind of knows that. Maybe somebody who's kind of used to the notion of global versus virtual environment might be more thrown by that. But I just wanted to mention it just in case. So I want to show you one other thing. If you click on this box here, now while we can select that, let's go back to the global environment that does not have NumPy installed. So I'm actually going to go and select this one up here. That's the global environment. And you can see we got that error again. Now, when you see an error like that, let's say you're like, oh, well, this is the wrong environment. I need to change to the right one. And so let's say you click on the status box down there at the bottom, brings up the box. Now, let's say your virtual environment isn't listed in the box. You can click Enter Interpreter Path and then click on Find, and it'll bring up a little dialog box to select the correct virtual environment. And the way you do that is you go to the virtual environment. So I just went up to the demo folder. I'm going to go into the virtual environment folder. I'm going to go into the scripts folder, and I'm going to look for python.exe in the virtual environment, which is in this scripts folder. And I'm going to select that. Where is python.exe? Should be right in front of my face. There it is. And then I'm going to choose Select Interpreter, and you can see it resolves the squiggle error. All right, with the squiggle error resolved, let's go down and click on the status bar again, and you can see it has the environment selected again. Now I want to hit Escape, and there's one other thing I want to show you, and that's the command palette. Most of you who use VS Code probably already know about this, but by pressing on Control, Shift, and P, you can bring up the command palette. And what you can do is you can type in interpreter or some string that's part of the command you want. And in this case, I found Select Interpreter, and you can click on that. And that's another way you can get to the same dialog box that you can get to from the status bar. And in fact, most anything you can do in VS Code, you can do from that command palette in terms of entering commands. Okay, so we have our small little example program, and we have everything set up. Let me save the program. We can see there's a little dot up here that indicates it hasn't been saved. I'm going to press Control S to save the file. Okay, we have our example in here. We have the environment set up correctly. So VS Code knows where to find our Python environment that we set up, and therefore it knows how to find NumPy. And we verified that by seeing that the squiggles are now gone. And now we can just run this program. Now, because I'm in demo mode here with this system, I have it at 1080p, and there's some scaling going on, so all my menus are not visible here. Sorry about that. So you'll probably see a run menu on yours up here without having to click the three dots. Okay, so I'm going to click on the three dots up here. I'm going to go to the run menu, and I'm going to choose Run Without Debugging. By choosing Run Without Debugging, it's just going to run full speed to the end, and it'll put the program output in the console. So I'm going to select Run Without Debugging, and it runs the program, and it outputs the array, which is 1, 2, 3. Okay, what I'm going to do right now is I'm going to hit this trash can here to close out this console window. Now that'll let us get a fresh console when I run the program again. And I may not do that all the time, but I'm doing it right now so we can really see the separate runs, just in case we want to look at something there. Okay, the next thing I'm going to do is I'm going to run the program in the debugger. Now, I'm not going to set any breakpoints the first time. That means it's going to run in the debugger, and it's going to run full speed to the end. Let me click the three dots, go to the Run menu, and click Start Debugging. Now, this is the first time I've debugged this program in this folder, and so VS Code's asking me, how do I want to run this? And there's a lot of choices here, and I've used a lot of these. The debugging is very versatile, and it's really nice to debug Python with VS Code. One of the simplest ways is just to select Python file, just to debug the currently active file. So that's what we're going to do. And you can see it didn't look that much different from the first run we did without the debugger. However, this time it did start the debugger, but there were no breakpoints, so it just ran to the end. And we can see the output here, 1, 2, 3. Okay, let me hit the trash can here to close that console. Okay, I'm going to click on line 2 here, and the cursor's blinking on line 2. While the cursor's on line 2, I can press the F9 key, and that will toggle the breakpoint. The breakpoint was off before, and now it's on. I can hit F9 again, and it'll toggle the breakpoint off. As well, I can go click in the column here, and when I click, it turns on the red dot, and that means the breakpoint's enabled. And I can go there and click to turn it off. And now the breakpoint's gone. As well, if you want to take a really super long time to set a breakpoint, you can put the cursor on the line where you want to set a breakpoint, and then you can go up to the Run menu, and then you can go down to the Toggle Breakpoint option, and it'll set the breakpoint, and so on and so forth. Okay, we're going to leave the breakpoint set, and what we're going to do is we're going to run this in the debugger. So I'm going to click on the three dots, I'm going to select Run, and I'm going to run with the debugger, Start Debugging. And we can see that the cursor has stopped on the line where we set the breakpoint, so the breakpoint has been hit. That's great. Now we can see some state here, like here's some variables, and it has locals and globals, and we can even set some watches here, and so on and so forth. Okay, and what I want to do is show you here, up here, there's a toolbar that can help you debugging, right? This is to run the program. This will step over, step into, and so on and so forth. So we're going to press the button to step over. And when we press the button to step over, you can notice that this variable A has now showed up. That's because we executed this line, and that created the variable A, and it assigned it this new NumPy array with the 3 numbers. And then we can click on this continue button, and it'll run to the end, and you can see it outputs 1, 2, 3. Okay, I'll close the console again, and this time let's run it again, but we're going to use some hotkeys. So I'm going to go to the Run menu, and we see that Start Debugging is F5, so we can get out of the menu, and then I can just hit the F5 key, and that starts debugging and stops at the breakpoint. Likewise, Step Over has a hotkey of F10, so instead of clicking up here, I can just press F10, and it steps over that line, creates the array, and so on and so forth. We see that Continue is F5, so instead of clicking, I can just press F5, and it'll continue to the end of the program. And we can see the output 1, 2, 3. Super, we've installed Python. We've created a Python virtual environment. We've installed packages into that Python virtual environment. One of those packages being Numpy, which is a very popular array processing package. We created a small little example program to verify that everything was installed, and we see it's working fine. So it looks like we're all set to go. Okay, I'll see you in the next section. Before we get started with the actual walkthroughs, if you're interested in viewing the tutorial walkthrough source code or otherwise following along, I recommend that you clone the tutorial source code from GitHub. Okay, before we go through the steps to clone the tutorial source code from GitHub, make sure you have a link to the GitHub repo where the source code is located. You can find a link to the GitHub repo in the description for this video. The general steps to clone this video's walkthrough source code to your local system are as follows. First, I'm going to type the WinX key to bring up the menu, and then I'm going to choose to open a terminal window. With the terminal window open, I'm actually going to expand this, and I'm going to enlarge this a little bit just for the sake of the video. You don't have to do that, so I'm just going to expand that out. So first we need to find and choose a location where we're going to clone the source code. In the walkthroughs, I use C:\demo. However, obviously, you don't need to use C:\demo. I'm just doing that because it's kind of simple and it's right off the root there, so it's very clear and easy. So the first thing I'm going to do is I'm going to make C:\demo, and then I'm going to change right into that folder. I'm going to clear the terminal window. I'm just doing that for the tutorial just to keep it nice and clean. Next, you'll type in git and space and clone, and then you'll paste in the link to the GitHub repository for this video's tutorial source code. And once again, you can find the link to the GitHub repository for this video's tutorial source code. You can find that in this video's description. So I'm going to paste that in here, and then I'm going to press enter, and it will clone the source code. And once it's finished, it will of course return to the command prompt. And at that point, you're all set. You've cloned the tutorial source code. Now I can change into the folder by typing in cd space in and tabbing to complete. And then I'm going to hit enter, and I'll type in ls to look at the contents of that directory. And we see several folders relating to this tutorial source code. In the sections coming up, we're going to use VSCode to load the repo folder. And so we'll wait for those later sections to get into some of the details of what's in the tutorial source code. But just a quick footnote, in this video, we're largely going to focus on what I refer to as the walkthrough source code, which are individual files associated with different walkthroughs. Each file is a small, isolated Python program that relates to the subject matter of the walkthrough. By contrast, audioutil is a little more involved, and we're not going to go line through that program, but we are going to use that program, and we will reference a little little bit of its source in passing in some of the sections in the tutorials coming up. However, you are encouraged to dig into any of the source code, of course. I'm only mentioning that because in this video, I was working to try to keep things as simple as possible. I was debating whether to get into some of the details within audioutil, but I think given the size of this particular video and the walkthroughs we have, they just seemed like good enough for a starting point. And so that's why we're not going to get into all the details of audioutil in this video. In this section, we'll go through several walkthroughs written in Python. The walkthroughs will write audio samples to an audio.wav file, or .wav if that's what you like to say. Merriam-Webster says it's WAV. No, I'm just kidding. I didn't check Merriam-Webster's. I don't think they have .wav in there. Anyway, .wav. Okay. So anyway, the walkthroughs in this section will write to a .wav file. And so we'll be creating .wav files from samples that the Python applications produce and write out to those files. Some of the walkthroughs will write 24-bit integer audio samples to a 24-bit audio file, and the other ones will write 32-bit floating point samples to a 32-bit floating point audio file. And the purpose of this is to get some hands-on manually, in a sense, even though it's programmatically, but it's kind of close to being manual in the sense that we're getting our hands on to see the files. We can choose whatever samples we want to write to those files, and we'll get a chance to see some things about the relationships to the samples and the files and amplitude levels and things like that. And it'll just be a chance for those curious about samples and writing them to a file and then being able to play back the files to hear them, and then kind of getting that connection between the samples that you write to the file and what you hear. And these are very basic examples, but it's a good way to start to get your hands on if you're interested in looking at this. All right, with that said, let's get started. Okay, I'm going to hold Win and press X, and then I'm going to select Terminal to open up a terminal. And then I'm going to change into our demo directory that we created earlier. And then I'm going to type cd space tab until it auto-completes the directory where we cloned the sample files for the tutorial. So in this case, it was the first tab for me, but if you created other subdirectories, obviously you have to hit tab a few times. So I'm going to hit enter to go into the intro 24-bit, 32-bit float PCM directory. And in that directory, I'm just going to type in code and dot. So I'm going to press enter. And it opens up that repository walkthrough and source code folder in VSCode. Now, just a quick word. Sometimes naming and little tweaks change. Maybe even a little bit of the directory structure might change. I doubt that between this time now and the time that the video is published. So just keep that in mind as you're working through things. If you have some questions, usually I will put errata in the description of a video or something like that. Or it might actually even be in the repo or something if it's a significant number of changes. But there really shouldn't be too many changes. Maybe not that many at all, if any. But just in case, since I can't predict what I might change or rearrange at some later time, or maybe some names, I might even insert another file or something like that. Okay, so the first thing I want to do is if your walkthrough folder is not like open and expanded here, just go to that folder and expand that. Ignore the other folders for right now. We're going to stick to the walkthroughs folder because that's where all the Python walkthroughs are. And these are numbered in the order that we're going to go through them in. And so take the first one and click on it, and that will open it up in the editor. Now, the first thing I want to do is I want to see which environment this is using for this project that we just opened, or this folder that we just opened up. So in order to do that, I have this keystroke window down here. In fact, I might move that up so we can see the status bar. Give me 1 second. Okay, I got that keystroke display window thing moved up a little bit. And we can see on the status bar, it says select interpreter. So we can go and click there. And there's a number of things that could happen here. We could try to run it and it would probably tell us to select an interpreter. I'm just going to go with the status bar right now. And so the point of this is there's so many different ways we could explore various things. But this particular video is about the content relating to the audio samples and the Python scripts that we're going to be running right now. And so I have to kind of limit some of the sort of tangential stuff I get into with like the editor and whatnot, but I try to touch on some things here and there. So we see there's no environment selected, and what we want to do is select the environment that we created. So since I don't see it listed, I'm actually going to click on Enter Interpreter Path, and I'm going to click on Find. And it opened it up here in the walkthroughs directory, so I'm going to click the demo directory, which is 2 levels up. And when I click on the demo directory, you can see there's our testing directory. And here's the Python 3.12 and virtual environment that we created. So let's double click on that, and let's double click on scripts. And let's go down to python.exe, and then we can click on Select Interpreter. And we can see it shows the interpreter down there in the status bar. Okay, so this first walkthrough is basically going to create a 5-second .wav file, and it's going to be a 24-bit audio file. It's going to be mono, and all these walkthroughs are actually mono. We're just going to keep it very simple. So it's going to be one channel of data. It's going to be made up of either 24-bit integer samples or the 32-bit floating point samples. So this initial walkthrough is using 24-bit integer. What it's going to do is write samples that fluctuate between -0.5 and positive 0.5. And it's going to do that about 400 times per second. And so that's a 400 hertz frequency. That's going to be a square wave. So when you open up a Python script, it's not uncommon to see the modules that it imports near the top. And these walkthroughs are no different. So this particular walkthrough is using OS, Wave, and Numpy. And notice it's importing Numpy as MP, which is, as we discussed earlier, a very popular high-performance array library for Python. So what I'd like to do is actually scroll down to the bottom here, and we're going to work our way upward. So at the bottom, we see something very typical for a Python script, where it's checking to see if it's being run directly as itself. When a Python script is being run directly as like the first script of the application, it'll be given a module name of main __ main __. I'm not going to say the underscores every time. So in this case, all this is doing is saying, hey, am I being run as a script? If I'm being run as a script, please call the main function. If it's not being run as a script, the main function won't be called. So it's a way for the script to behave like a script when it's invoked with the intention that seems like it's meant to be run as a script. And if the module ever happens to be loaded as a module that's not run as the main script, that main function will be skipped given this if statement here. And I know many of you know this who've used Python before, but there might be people diving in that just want to explore this, and that'll just help them stay up with us here. And of course, there's a wealth of information online with this. You can, search for it and ask the chat bots and all that kind of stuff. So really the main function is main, and that's where we want to go. So let's go, and it's right up here. Here's main. So let's just go down main. So what I'm going to do here is I'm just going to go down in main at a high level. We're not going to go into any functions first. We're just going to go skim down it pretty quickly. That'll give us that TLDR table of contents, that high level view, set our mind up to kind of know where we got to go and traverse after, and then we'll proceed forward with a deeper dive after that. Okay, so the main function at first sets up a couple of variables here. So let's just go down these one by one. The first one is a sample rate, and that's going to be 48 kilohertz. The next one is the frequency of our square wave. That's going to be 400 hertz. The duration of the wave file is going to be 5 seconds. And we want the samples to fluctuate from -0.5 to +0.5. So amp high is the high end, so that's 0.5. And amp low is the negation of that, or -0.5. Okay, so moving further down the file here, we basically just build the file name using the example number and some characteristics relating to the parameters that we just went through. This is so that the resulting wave file has some naming that will tell us what settings we had. So moving further down, we see that a function generate square wave simple is called. And this is a function that produces the values that will make up the square wave. And those get returned and assigned into this square wave variable. Moving further down, we see a function convert wave data to 24-bit PCM sample is called. That's going to take the square wave data and create PCM samples from that data. And then finally, there's a function here called write 24-bit PCM, and that's going to write those 24-bit samples to a 24-bit audio file, which will have the name that we created earlier. Okay, so let's go back up to the top here. Okay, I think this part with the values is pretty straightforward, and the file name stuff is pretty straightforward. The amplitude stuff should be pretty straightforward. And for those who might not be following the amplitude part, that's related to the 0 to 1.0 that we were talking about earlier. Now, a lot of the sections discuss the range from 0 to 1.0 because it makes it easier to discuss things. But we're creating basically a sample that's in the negative range, -0.5, and the positive sample is +0.5. So just in case that wasn't clear. So essentially that's the square wave that's going from -0.5 to +0.5 and so on and so forth, right? So like that. And I'll put a graphic here on the screen or something. All right, so let's get to some meat and potatoes here. We got this create square wave simple. And we're basically giving that function some variables. Let's just go through these really quickly. We've got frequency, that's our 400 hertz. We have the duration, which is 5 seconds. And we have the sample rate, which is 48 kilohertz. We have those two amplitude levels, -0.5 and +0.5. All right, let's go to the function. Now we know this function is further up in the file, but if it weren't, let's say it were in some other file in a large project, or let's just say we want to go up there really quickly, because even in a single file, scrolling up and looking for it can take a little extra time than letting the IDE do it for us. So I'll highlight the function or put the cursor on it, and then I can press one of the shortcut keys that I know, or just right click on here and say go to definition, and that'll take me right to the function. Now I can hold the Alt key on the keyboard and press the back arrow, and that will take me back. And as you notice, the hotkey here was F12, and all I have to really do is highlight the function and just hit F12, and then I can hit Alt and then back arrow and go back, and so on and so forth. In fact, if I'm back here now, I can actually hold Alt and go forward arrow. So you can use this Alt forward arrow and Alt back arrow and F12 and all that stuff to navigate around, as you need to. So here's the function. We've got frequency, duration seconds, sample rate, amplitude low, amplitude high. So we'll skip the comment there and we'll start looking here at number of frames. So there's this concept here, num frames, and that equals the sample rate times the duration in seconds. So what's happening here? Well, the sample rate is going to be 48 kilohertz, and that's a typical audio sample rate, and the duration is 5 seconds. So this is just multiplying the number of samples that will exist per second by the number of seconds. And so num frames is the total number of samples for the entire file. And it uses end here to remove any fractional portion. The next line is going to create a numpy array that's going to have the same size as the total number of samples for the file. Now, if we were doing some large audio processing, we probably wouldn't do things in this way. But when you're working with small audio files or small samples, we can keep the data structures very simple. We don't have to think about a whole lot of performance things when we're dealing with a simple 5-second file's worth of data. So just keep that in mind. Some of the approaches we're taking here is just to keep things simple, because it's a great way to get hands-on and kind of see some of the stuff without burdening yourself with a whole lot of extra stuff that some high-performance app might need, but not a small walkthrough. And by the way, if you haven't had a chance to dig into some data science stuff or NumPy stuff or whatnot, playing with something like this can be a great way to familiarize yourself with NumPy a little bit while learning about some audio samples and whatnot. So moving down, we have this concept here called half-cycle frames. So let's see what that is. That's the sample rate, and that's divided by the frequency. And then all that's divided by 2. So what's happening here? Well, the sample rate is the total number of samples per second. The frequency is the frequency of our square wave. So dividing the number of samples per second by the frequency being the number of oscillations per second of the square wave. If we divide the number of samples per second by the number of oscillations per second, or the frequency, we'll get the number of samples per oscillation period. So that's the number of samples it takes for the square wave to go a full cycle, or to complete one full oscillation, of which it completes 400 per second. So we know the number of samples that are going to be used per oscillation period. If we divide that by 2, we end up with the number of samples that will take up half an oscillation period, 1/2 of the period. And so with the square wave, since 1/2 of the period is spent on the high side and the other half is spent on the low side, essentially what we're getting is the number of samples dedicated to one amplitude level and the number of samples dedicated to the other amplitude level. It's pretty much the number of samples per oscillation period divided by 2. Half of those go to the high amplitude, the other half are going to go to the low amplitude. We're just keeping it very simple. And then we're setting up this count variable here, and we'll see how that works here as we get into the loop down here. And we have a thing that says current amp, that's current amplitude, and we're starting off with the current amplitude equal to amplitude high. And then we're going to loop for the number of frames, or the number of samples, for the entire file, because num frames is the total number of samples that will exist in that 5-second period that the file is going to make up. And so we're going to iterate that many number of times right now. Now we see the first thing that we do here is we take the current amplitude level, and data is that numpy array that's going to hold all the samples that are going to be in the file. So it's all the samples. That data array has num frames elements, which for those of you who don't work with arrays, are places in the array where you can put values. And each place has a number, and that's what that fn variable is doing. That fn variable is starting at 0, and it's going to the maximum number, which is the total number of samples that will end up in the audio file. And it's basically one by one going to set that array to equal the sample value that will exist at any given point for all the samples. So the very first one is going to have whatever current amp equals, or cur amp, I should say. And then we do this countdown -1, and we check to see if the countdown is equal to 0. And if it's equal to 0, we basically reset the counter back to half-cycle frames, and we toggle the current amplitude. So if it was high, it'll now be low, or if it was low, it'll now be high. So hopefully you can can kind of see what's happening here. It basically calculates how many samples do we need for this file. Let's create a big NumPy array to hold all those samples, and let's go and populate that array with amplitude values. And it's basically going to put a bunch that are amplitude high for a certain duration, and then amplitude low for a certain duration, and then high and then low, which effectively create this square wave, because it's going to create the effect of amplitude being held a certain amount of time at a certain level high, amplitude being held a certain amount low. And it's basically going to do that for the entire array. It's just going to create this fluctuating thing where you're going to just have a bunch of entries that are going to have amp high, a bunch of entries amp low, amp high, amp low, amp high, all the way to the last array entry, which is the end of the file effectively, or that's what will eventually be the end of the file in terms of sample data. It's not the physical end of the file, obviously. We can think of it as the logical audio sample end of the file, so to speak. So then once that loop ends, we drop down here and we just return that array. Okay, I'm going to hold the Alt key and press the back arrow to go back to the location that we jumped from when we did the F12, or when we did the go to definition of that function. That brings us back to the place where we called the function from. We can see that data array, which is a NumPy array that's now filled with samples, gets assigned to square wave. Now we're going to go down a little bit here to the next line, and we see that that array square wave is being passed to this function, which is apparently, based on its name, is going to convert those amplitude samples, so to speak, into 24-bit PCM signed integer samples, 24-bit audio samples. And when it does that, it's going to probably, I assume, it's going to return those samples and assign them to this data array here. All right, so I'm going to put my cursor there on the convert wave data to 24-bit PCM samples. I'm going to hit F12, and that's going to jump to that function. All right, so let's go through this function. Well, obviously, we know we're getting a NumPy array here in wave data. So wave data is a NumPy array that has a waveform in the format of amplitude levels. And we happen to know the two amplitude levels and all that because we just went through that. Let's now see how this function processes that array. So we see there's a constant value sort of being created here. I'm calling it a constant. I realize it's not literally a constant, but that's kind of what this is. This value is meant to represent some kind of constant value here. And what is the value? Well, it's the max sample value. And we should be familiar with that now based on the past sections. And then we see a bytes object is being initialized here. Apparently going to hold the 24-bit PCM data. And then this thing is going to iterate through all the stuff passed in wave data. So each sample is going to be one element in the wave data array. So the wave data array is that NumPy array that contains all the amplitude levels that represent the square waveform. And this for loop is going to iterate through that NumPy array where each time it iterates, one sample will be put into this sample variable. So then we scroll down here a little bit. So this first line is going to multiply the sample by the max 24-bit sample value. Now remember, the sample values are amplitude levels, and we know that amplitude levels can be viewed as ratios, where 1.0 is equivalent to 0 dBFS, or that maximum level that a digital audio system can handle before clipping. And so if we take that ratio, or in our case we know it's 0.5 or negative 0.5, and we multiply that by the max possible sample, what we'll end up with is a portion of that maximum that effectively represents the value within that range of sample values that's equivalent to the floating point value of the amplitude levels. In a sense, you can think of the amplitude levels as, floating point values, because that's what they are. And so those floating point values that represent amplitude levels can be used to derive the integer sample. As long as we know what that integer range is, we can use the ratio, in a sense, of that floating point value to say, hey, give me of you this ratio of you, right? Like, I want this amount of you. And that becomes the sample value. Now, this is very simple processing, so I'm not saying it's always so simple, but it's a very good way to kind of get, your hands on this kind of stuff and look at it and learn about it. So F ends up being the 24-bit PCM integer sample, but not quite fully an integer yet. It's now a fractional floating point value, but it's within that sample range. So the next line performs some rounding and clamping and creates our integer for us. And rounding can be an involved discussion. We're not going to get into all the details of that in these walkthroughs. For the walkthroughs, we're going to keep it very simple. We're basically going to round highs away from 0. And so basically here, we're performing some rounding, but then we're making sure that maximum sample on the positive side doesn't go above 2 to the 23 minus 1. Again, that 2's complement anomaly we discussed earlier. And so after all that, we end up with our integer sample. And then that sample is converted into 3 bytes. And then it's appended to the array that we're building up in this function. That's the data 24-bit PCM array. And after we're finished looping through all those amplitude values and converting them into 24-bit PCM samples, we return those 24-bit PCM samples to the caller. Now I'm going to hold the Alt key and press the back arrow. Those 24-bit PCM samples come back and are assigned to data, and then data is passed to the write 24-bit PCM function, which is going to write those out to a 24-bit audio file. So I've got that function highlighted. I'm going to press F12 to jump to that function, and let's go through this one really quickly. We pass to this function the file name, the 24-bit PCM signed integer samples, and the sample rate 48 kilohertz as we know. We have a little validation at the top here just to make sure the amount of data in the past 24-bit sample array is a multiple of 3 bytes. And if it is, it passes down here to this function where it does wave open with the file name. It sets the file as a single channel file, so that's mono. Sample width is 3 bytes, that's 24-bit. It sets the sample rate to 48 kilohertz, and it writes all the 24-bit samples. When it's finished doing that, it'll exit this width block here. And when this width block is exited, the WF, the file that's represented by WF, will be closed. And then we'll return to the caller. I'm going to hold the Alt key and press back arrow, and then it prints a message that it generated the file. So why don't we give this a run and see what it produces and maybe hear what it sounds like. So for this first run, I'll go up here to the Run menu and say Start Debugging. And I'll choose the Python debugger, and I'll choose Python file. And there we go, it's finished. I didn't have any breakpoints set, so it ran it in the debugger, but it didn't stop, it just went right to the end there. So because it was debugging, it activated the debugger like sidebar tab thingy here in VSCode. So I'm going to go and click up here to get back to the Explorer. All right, so I'm going to make this a little bit wider here, and we can see that's our 24-bit audio file. So what you can do in VS Code is you can right-click on a tab where your source file is, and you can choose Reveal in Explorer. And that'll open up Explorer for the current directory of that source file, and you can actually get direct access from your Explorer. So I'm actually going to first do a right-click on this and choose Properties to look at the Explorer properties of the file. So here I am in the Details pane, and we can go and look here and see that this is the audio sample rate here, and it says that it's 24-bit, and it says that there's one channel and that it's mono. So we see that the File System Explorer is seeing the file as a valid audio file. So I'm going to close that. All right, let's double click on the file, hear what it sounds like. Well, there we go. We've got our tone. And so we've just used Python to create an audio file that makes a steady tone using a square wave in a simplistic manner there in this Python walkthrough. Okay, so that script created a wave file that had a square wave that was going from negative 0.5 to positive 0.5 and back and forth and back and forth. So the next walkthrough is similar, but there's a slight change. So let's go check that out. Okay, so we'll close the Explorer window. Okay, so I'm going to slide this back over, get some real estate back for the files. And now let's load in walkthrough number 2. Now walkthrough number 2 is identical to walkthrough number 1, except we're going to change the amplitude levels. So the amplitude levels in this case are going to be going from 0.5 to 1.0. So it's 0.5 to 1.0, then back down to 0.5, back up to 1.0. Now, while this is a manufactured situation in a sense, I'm doing it on purpose. So we're forcing these high amplitude samples here, right? 0.5 to 1.0. And what we're going to do is we're going to hear what that sounds like in comparison to the prior walkthrough. So I'm going to scroll in here and go down here to the bottom, and we can see everything's pretty much the same in here, except these two have changed. So you'll notice that the distance between here and here is less. So you'll notice that this value is higher than any of the values in the other example. And that this value is the lowest value, which is equal to the highest value of the other example. However, unlike the other example, the distance from this low to this high is less than what the other file had. The other file had a 1.0 distance, negative 0.5 to positive 0.5. This file will have a distance from 0.5 to 1.0, which is a distance of 0.5. Let's run this program to create the wave file, and let's see what happens. So I could go to the Run menu and do Start Debugging, but since I know that Start Debugging is F5, what I'll do is I'm just going to stay here in the editor, and I'm just going to press F5. Now we haven't run this yet, so it's going to prompt me. I'm going to say Python Debugger. And it looks like it's finished. So now we're going to open this up here to see. And yep, there's the WAV file. I'm actually just going to, yeah, no, we can keep this open here. I'm going to right click on the tab for the source file, and I'm going to choose Reveal in Explorer. And that's going to open up the operating system's file explorer. And we can see the new WAV file is here. All right, so I'm going to double click on that. It sounds pretty much like the other one, but without changing any levels or anything like that. Let me close this and just simply run the other file. Now, depending on your streaming application and its audio settings, it may perform some leveling of the audio, so you might not hear the differences. But the first file that we created is a little bit louder than the file that we just created. Let me close this and we'll run the other one again. And then I'm going to stop and I'm going to play the other one, the first one, louder. I installed Audacity, which is an open source audio processing application, and that will let us look at these waveforms side by side. So you don't have to download and install Audacity if you don't want to. You can just look visually what I do here, but I highly recommend you explore it if you have an interest. It's really easy to install it and use it and stuff like that. So I'm choosing Audacity simply because it's open source. It's easily available to folks. I use and like a number of other digital audio workstations, and so this is not to have a preference towards one or the other or whatnot. All right, so here's Audacity. Let me drag and drop these WAV files into Audacity. So I'll take the first one that we created and drag it in here. And then I'm going to take the second one that we created and I'm going to drag that in here. So you can see the first one we created is here at the top, and here's the second one that we created at the bottom. Track 2. So we can see that the track 1 here has the first file we created. You can see the one that we created first is louder. So I think Audacity Zoom here is with the scroll wheel. Oh yeah, there we go. Okay. I don't use Audacity all the time, so forgive me if I don't do everything with Audacity in the most pristine, wonderful way. So as we dig in here, we can see here's a square wave that goes from, we see here -5 up here to +0.5 and so on and so forth. By the way, let me make this dark. All right, I just changed Audacity to use dark theme because the bright one, I was getting a sunburn. So the whole point of this exercise so far with these 2 walkthroughs is to kind of show there isn't necessarily a direct relationship between an individual sample's amplitude level and the overall loudness or level of the file as you're listening to it. And that's because you have to take into account the transitions that take place when going from one sample to the next. So the point of all this is not to get into a lot of deep audio theory and whatnot, because that can get very involved. It's just really to stay at this simple level of software developers looking at these audio formats, 24-bit samples, 32-bit samples, what do they represent? And we know they represent amplitude levels. And there's a lot of stuff that kind of comes together when a lot of these things are played back together. And so the thing I wanted to point out here is that just simply having a higher level of a sample doesn't necessarily mean a louder sound. And actually, we can try playing this back in Audacity. Let me click solo here for the first one. This is the first one we created. And so by clicking solo, we're just going to listen to the first one that we created. That's the louder one. Let me click to play that. Okay, and now let me go and click solo on the second one, and I'll unsolo the first one. Yeah. It's slightly lower. Okay, so let's close Audacity and let's go back to the walkthroughs here. I'm going to close the Explorer window. Okay, great. I'm going to close these source files here. All right, let's drag over walkthrough number 3. So walkthrough number 3 is pretty much the same code as walkthrough number 1 and walkthrough number 2, except again, we're changing only the amplitude levels. Let's scroll down to the bottom here and everything else is the same. All we're doing is changing the amplitude levels. Now look at what we're changing them to. They're both going to be identical. They're both 0.5. Oh, forgive me. This comment is dated here. And let me see. Was that comment dated in the other one? Yeah, they're all just kind of like copy paste things. So let me actually, okay, so I removed that bum comment out of all the files there. Sorry about that. So basically these two amplitude levels are the same. So what do you think is going to happen? Well, if they're all the same amplitude level, there's not really much fluctuation going on there. In fact, it's 0. But let's run this, create the WAV file, and let's examine it. So I hit F5. I'm going to choose Python debugger. And we see a WAV file has appeared here. So I'm going to go and right click on the source file and choose Reveal in Explorer. And it's going to open up the Explorer window. And let's listen to this file. Oh, well, what an incredible sound. So you can see there's nothing really coming out of that at all. There's a little glitch there in the beginning, but other than that, the file was, silent. So let me close the player, and why don't we load all three of these in Audacity, including the silent one. So I'll click to open up Audacity, and let me see if Audacity supports selecting these three WAV files together and dragging them together. I bet you it does. Yeah, there we go. Hey, terrific. Let me drag this down here like this and maybe just make this a little bit bigger. So we can see here's the first wave file that we created. This square wave had the largest span between the two levels of amplitude. The span was 1.0. And our second example used higher sample values, but the only two amplitude levels they used had a smaller span than the first walkthrough. And you can see that's a little smaller. And the one that we just created, which is in track 3 here, that used a high and low amplitude level that was equal, ended up creating this kind of empty sort of looking wave file here. So as I scroll in here and zoom in, we can see here are some waveforms that Audacity is able to recognize in the first two. But in the third one that we created, it just has a flat line. So let's solo again that first one. Fairly loud. I'm going to unsolo, and then I'm going to solo the second one. Okay, that's lower level. And then I'm going to unsolo that and go to the last one and try that. Yeah, nothing. Okay, so point made here with these amplitude levels. Now I want to show you something else. Let me close Audacity down here and let's close Explorer. Okay, if you don't have Hex Editor installed in Visual Studio Code, you can go to this icon here where the extensions are located and click on that. And then you can search for Hex Editor. And if you're interested in installing the one that Microsoft publishes, just make sure that Microsoft's name is here and it shows that they're the publisher. And then you can click Install. Now, I'm not saying there aren't other hex editors or whatever. This is just the one that I use. So let's go back over to the editors here in the Explorer. I'm going to close this Marketplace window. And what I'm going to do is open up the first file that we created. So you can see when I open this by default, Visual Studio will allow me to play it, but that's not what our goal is here. So I'm going to right click on the tab. I'm going to choose Reopen Editor With, and then I'm going to choose the Hex Editor. Remember the amplitude levels we used in the first walkthrough, which is this WAV file that we're looking at here, were negative 0.5 and positive 0.5. So the PCM samples that it produced should be the PCM samples for negative 0.5 and positive 0.5. So without breaking down the format specifically, if you open a WAV file just generally like this, you can see the RIFF header, RIFF. That's the format of the file, the container. You can see the WAV section of that, the format section, the data section. We'll actually cover these a little bit in an upcoming walkthrough. We're not going to deep dive into the RIFF format, but we're just going to touch on it. What I'm trying to point out here is that just by opening it in a simple hex editor, you can eyeball the hex bytes and stuff here and the text representation of the RIFF sections, and you can kind of get an idea for what's being shown here. When you see RIFF, WAV, format, data, you're looking at a WAV file. This data section is going to hold the samples. Now we know we have a lot of repeating samples, so those should be fairly easy to identify. And they are. If you look here, you see 400000 400000, and so on and so forth. So pretty much this right here, these 3 bytes. So those highlighted bytes are one sample, and they're in little endian format, so the low byte is first. The second byte is a 0 as well, and then that high byte is 40. And what is 400000 hex? Well, that's 1/2 of 800000 hex. And what is 800000 hex? Well, that's 1.0. Remember, the positive side can't express that value because that's the lowest negative value in signed integer format. So the highest value is 7f, ff. You know, the 2's complement anomaly that we went over. But despite that, it's still okay for you to think that that maximum possible sample is 800000, even though it isn't, because it's just one count higher than 7f, ff, 800000 or 80,000 hex. Well, what's half of 80,000 hex? 40,000 hex. It's pretty simple to do that, and that is a valid sample. So when the program calculates it, it basically is taking 0.5 of the maximum possible, which is the 80,000 hex, and it comes out with 40,000 hex. And so you see we have 40,000 hex here until we see a different value. The different value we see, since we created this WAV file, we know it's negative 0.5. So we pretty much know that this 0000C0, so that's one sample there on the negative side. That's C00000. So we can bring up the calculator here, and let's just start with 2 to the 23. Okay, so this is our maximum sample on one side. And then you have the negative side as well, right? So 2 to the 23, that's 23 bits there. So this is the maximum value. So 2 to the 23 is the maximum number of values the 23 bits can represent. So if we divide that by 2, that's 1/2. We have 4194304. If I take this value and I copy that, let's go over to the programmer calculator. We'll just paste this right into here. Now I have D word selected here, and we can see that comes out to 40,000 hex. Now, if I go here to the hex value, since the calculator doesn't allow you to have a 3-byte signed integer, I choose D word, as you see right here. There's D word is chosen. So you can hit this and go from quad word to D word to byte. So I go to D word, and that's a 4-byte integer. But we can still express 24-byte integers in there, signed integers. So the way we can do that here is we just put leading ones there for the negative side. So you can just say FF to fill those bits up in that high-end byte that we're not concerned with. Now you have 3 bytes remaining, so you can enter in the 3-byte signed integer. So you can type in C00000. And you'll see the decimal value shows you negative 4194304, which is that value we just saw. That's a negation of 2 to the 23 divided by 2, or 1/2 of the number of different values that you can represent there in the 23-bit space. Closing the calculator, point being here is we can easily eyeball these repeating samples. And by the way, that can be a nice benefit of working with a very simplistic example. Basically, you're creating a WAV file with a very simple waveform, repeating samples. You can open it up in a hex header and actually recognize where the samples are located. And if you wanted to learn the RIFF file format, for example, this might be a good ingredient to sort of add to that learning process, because you could look at the definition for how a RIFF file is structured, and you can kind of see some of the layout here, and you can see where these samples are located, and it can just kind of help to get you up to speed on that if that's something you're interested in. All right, so now I'm going to close this wave hex editor thing and this source file. Okay, now let's drag walkthrough number 4 over. And that one's going to create a square wave, which is going to go to a 32-bit floating point wave file. All right, as with the other files, I'm going to skip all the way to the bottom on this one. So let's go all the way to the bottom. And I'm actually going to move this sidebar thing over. I accidentally set a breakpoint there, so let me remove that. And then I'll just set this to be, right about here. And we see the usual if check if this is a directly executed module, which in our case it will be. It will call the main function, so we'll scroll up here to the top of the main function. Now the general layout of all these walkthroughs so far is going to be the same. This will be very similar to the 24-bit PCM sample walkthrough that we just went through, except this one's going to produce a 32-bit floating point audio file. So we see we have a sample rate of 48 kilohertz. We see the frequency is going to be 400 hertz, and the duration's 5 seconds. And we see it's setting the amplitude high and low. And this is the same as the first walkthrough that we went through. It's going to choose a name for the file, and then it's going to call generate square wave simple. This is the same function as in the prior walkthroughs. And then after that, it's going to call write wave float PCM. So we can right click on that and go to definition. And so this is going to accept the file name, the sample rate, and it's going to accept that array of floating point amplitude values. Now notice there's a step that is being skipped here that existed in the integer walkthroughs. So let's actually open, let's say the first one. Let's compare these two side by side for a second here. So let's bring this one over here. Let's see if we have enough room to show them both. Yes, we do. So let's go down to main here in this 24-bit walkthrough. And I'm just going to move this scroll bar over a little bit just to give us a little more room here. So I'm going to go back over here to the walkthrough number 4 that we're currently looking at. That's the first floating point walkthrough that we're looking at. And I'm going to go back down here to the bottom. And if we compare these two, you can kind of see here's a generate square wave simple, right? So this is the floating point example over here on the left. And over here on the right is the 24-bit. This is the first walkthrough we were working on, and this is the fourth one, the one that we're currently looking at. So we can see they both have a generate square wave symbol, but the one for 24-bit audio, which has to convert them to 24-bit integer samples first before writing to file, has an intermediate step here where it actually does that conversion. If you look at the floating point example, you can see it generates the square wave, but then it goes right to writing it to file. And why is that? Because the amplitude values are floating point, and those floating point values are ready to go to be written to the file as the samples themselves. With the 24-bit format, they need to be first converted into integers which effectively represent the floating point values as close as they possibly can. The 24-bit integer format doesn't have the same precision as floating point, so essentially that conversion to the 24-bit samples is a process of not only converting them, but sort of approximating the best choice to make within the fewer choices that you have available in the 24-bit integer format. All right, so let's close that initial walkthrough that we had and go back to the floating point example. So I'll right-click on this generate square wave, and you can see it's pretty much the same here. So I'm just going to go and hold the Alt key and press the back arrow to go back. I'll do it twice actually, since I moved a little bit after I went forward. So I had to hit back arrow twice. And now we see it's going to go and just write those floating point square wave samples directly to a 32-bit floating point wave file. So the real function we probably want to look at here is this. That's the thing that's different with this walkthrough versus the first one. Okay, so let's right-click on this file and go to the definition. So here we are. Let's go through this. So the parameters are the file name to write to, the sample rate, which is 48 kilohertz, and data contains the floating point amplitude values. Those were ones that were created by that create square wave function. So we have num samples, which is the number of samples that are inside of this data array. There's a variable that represents how many bytes per sample, and 32-bit floating point audio requires 32 bits per floating point sample, and that's 4 bytes per sample. And so it's calculating data size, which is the number of samples that we have, and what is the size of each sample. And so data size is the total size of all the samples. And the frame rate is the sample rate, and that's just being done to be simple here. Obviously, we could just use sample rate directly below, but this is just making it clear. And then the number of channels is 1, that's mono, and the bits per sample is obviously 32. Now, the rest of this stuff here is going to be about writing to this RIFF container format. So let me insert this here, that if we go to Wikipedia and we look up the RIFF file format, you'll see resource interchange format, and you can read all about it here. So if you scroll down in here, there's actually some fairly good overview information here. You can just read all of this. We're not going to go into this in great detail in this video, but we'll touch on some of this right now. So another really good article to go to is down at the bottom here where it says some common RIFF file types. You can click on WAV. So if you click on that, it'll go to this article. And this article goes into a bit of detail on the format, and it just has a lot of good discussion here on this. So if we scroll down here, there is a section I did want to point out as we go through this walkthrough, and that's this wave file header section here. So you'll notice that this gives a little bit of an overview of the header, and you'll notice that like it has this identifier RIFF right here, and then it has the overall file size -8 bytes, and it gives all this information here. Like there's this wave section, and these are sections that are going to be written in that walkthrough. So we're going to be looking at that right now. You can see there's an FMT_ section, and then there's a data section where the samples go. So let's go back over to the walkthrough. And you can see right here it's using Python struct.unpack to build this RIFF header. Now, we're not going to go into great detail in this here. Suffice to say, this is writing a valid wave file, and it's setting up the header for it to be a 32-bit floating point wave file. So it has the standard RIFF indicator here and the wave indicator, WAVE, and then it has FMT_, and then there's a data section here, which is built, and and the data section will have data size, and you can see data size is up here. It's num sample times the bytes per sample. And if we go back down to that, you can see it takes the sample data and it puts it in audio data here. And it uses struct.unpack to put this in a packed format in the way that it will be written to the file. And you can see what it does is it just simply opens the file in the binary format, and it writes these items in order here. So first is the header, then there's the format header, the data header, and then the audio data, the sample data. Let's go back up to where we were in this function here. So we have this frame rate, which is the sample rate. This is mono, number of channels 1, bytes per sample is 32. We kind of covered all this, right? But then it gets into these things like the format chunk size and the RIFF size, and you can look at that RIFF article or find your favorite RIFF spec, and you can kind of just see that it's building up this header to just match what the spec calls for. This number 3 right here is actually what makes it a floating point audio file, a 32-bit floating point audio file. So this 3 would be a different number for other audio format types. And so basically it ends up writing the samples out to file, and then the program will exit. We can go down here, we can see it finishes creating that floating point file, and then it's finished and it exits. Okay, so with this in the editor, I'm going to hit F5 to start the debugger. Since this hasn't been run, I'm being prompted, what debugger do I want to use? I'm going to let it know. And it's going to run, and it looks like it's already finished creating that file. So let's actually move this over. And sure enough, there we are. What we can do is right-click on this source file and reveal in Explorer. And I can right-click on this WAV file and bring up the Explorer properties for the file. So here's the details pane of the Explorer properties for the file. And we can see that it says 32-bit right there. I'm going to close the properties. Okay, so I'm going to double-click to run this. Okay, pretty much the same sound as that first walkthrough. All right, let me open up Audacity so we can get a closer look at this. So we can load this in as the first track, and I can do Control and scroll wheel to zoom in, and we can kind of see that similar waveform as we saw with the 24-bit walkthrough, the first walkthrough. So we have 2 different format audio files producing a similar waveform. Okay, so I'm going to exit Audacity. I say no. And I'm going to close the Explorer window. Okay, next I'm going to click on the float wave file that we just created. And you'll see VSCode wants to know if we want to play that back. Instead of playing that back, what I'm going to do is right-click on the tab here that has the file name, and I'm going to choose to reopen the editor. And then I'm going to choose the hex editor. Now we're going to be looking at floating point samples here instead of those integer samples. Now, an interesting thing we can do here is let's go to the terminal window, and I'm going to clear the terminal window, and I want to activate our Python environment on the command line. So I'm going to recall the command line that we used to activate it before, and that's just to run the PowerShell activate.ps1 because we're on Windows and this is PowerShell. So I'm going to use that script to activate the environment. I hit enter, and we can see that the environment is activated because the name is visible in the prompt that the environment is activated. And we could even sanity check and see that it's picking up that version of Python. I type in Python version. There we go. Great. So now let's just run Python in an interactive mode. Okay, so I'm going to paste a little code snippet in here, and I'm just going to hit enter at first. Then we're going to go over it. Oh, I received an error here. So first I actually have to import struct because we're using that. And I also have to import C types. I'm just going to say import everything from there. All right, so now what I'm going to do is paste in this code snippet again, and I'm going to hit enter. Now, what do we see? Well, okay, cfloat is a 32-bit floating point value that Python gives you a structure that lets you create those. And so what's being done here is one of those is being created, and then struct.unpack is being used to access the underlying bytes of that cfloat. Now, in picking this apart, if I go and get rid of a lot of these things here, so let's just get rid of all these and just have this unpack here, okay? So with the unpack, if I just run this, you see we get this kind of raw bytes representation here. So that's why here you'd see me indexing that first element because there's one element in this tuple here. And so this gives us access to that one element. And then what I'm doing is I'm calling hex on that so that we can see the hexadecimal representation of it. And that shows us in little endian format 3F000000. Low byte is first because little endian, right? So the number is 0x. 3F 000000. So this is just kind of a simple way to use Python to look at the underlying binary value of a given 32-bit floating point value. And so what we see here is 0.5 is equated with the hexadecimal value 0x3f000000. And so if we go back over to the editor here, we can see a whole bunch of those here. Those are our 0.5 samples. And if we scroll down further, we're going to see it changes, and you can kind of see that the sine bit gets set. Because we go from 3F and then you see this BF, and we know 3 doesn't have that high bit set because 3 is those lower 2 bits of that high nibble, if you will, right? 3F. So 3 being that highest nibble of the 32 bits. Highest nibble meaning the highest 4 bits. And so of those highest 4 bits, the 2 lower bits of the highest 4 bits, those make up that digit 3 of 3F. If the most significant bit were set, we would see something like what we see with these other samples. We would see BF, for example, or some other value that clearly indicates it's higher than the value 8. If you see a number in that highest hexadecimal nibble there that's higher than 8, then you know the most significant bit is set. And if the most significant bit is set, the number is negative. And we know that from the earlier sections. So if we go over here back to the window and we put in a -5, let's see what the underlying representation is. And of course, it's BF, 000000. So we have a match there. So here we're looking at a 32-bit floating point audio file we created with a very simple square wave. We basically generated the square wave in an array. The array was an array of floats. We didn't have to really do any more processing on those floats after we created them. We could just write those things out to disk. So the toughest part about working with that 32-bit audio from a programmatic standpoint, given these simple walkthroughs, is probably writing it to the file. And you might say generating the WAV file or doing something to process the audio. That might be a tough thing to do, but there really is not much going on there in the conversion to float because the samples were already in float because we were doing all the math stuff and the sample creation stuff in floating point. So it just naturally kind of flowed right out there to the file. Now, I'm not saying your DAW or other application isn't doing some more advanced processing before it's writing something to a file or that kind of thing. But you can see that there is a little bit of a simplicity there in that processing and writing to file compared to dealing with that step of conversion to an integer format. And this is not to knock the integer format. People really like that, but it's just to call this out that, you're dealing in a format that you don't have to convert from in order to write it to the file. And that's not to say that you couldn't be working in, let's say, 64-bit float and you need to write to 32-bit float that you wouldn't have to convert and all that kind of stuff. So I'm not saying there isn't ever any kind of converting going on with 32-bit floating point samples, but I'm just saying in these simple walkthroughs, we're already dealing with floating point, and that goes out really nicely naturally to the 32-bit floating point file. So back here in the editor, let me expand this out, and let's go back here to where... So I wanted to point this out. This is the function that writes to the 32-bit floating point wave file. Now, there's a lot of stuff in here that sets up the RIFF header and all that. I want to skip down here to where this audio data is created. This audio data thing is doing a thing to join bytes together, and it's doing that with the output of struct.unpack for each element of data. So for each element of data, this is our input array of samples. For each such sample, it is actually using struct.unpack to pack that into a floating point value. So here in the browser at the Python documentation, I'm actually going to search for struct.unpack, and I want to show you something here. If we go to struct, or actually I'm going to go to struct.unpack, and somewhere up here where it says byte order, size, alignment, I'm going to click on that, and then I'm going to go down here, and you can see these types here are defined. And these are like the format types. So if we look for F here, you can see F is float, and you can see up here it says standard size 4 bytes. So this is for a 32-bit float. And there's a little footnote here 4, and you can go and look down here at footnote 4, and it'll explain a little bit about how this format's handled or whatever notes they put there. So if we go back over to the walkthrough, you can see that for each sample, it's actually packing each sample into a 32-bit float using struct.unpack, and it's doing it in little endian order. So that was something we glossed over at first. We're looping back here to show that when it writes it to the file, it's actually processing each sample to take it and pack it into a 32-bit floating point value. And it's putting one right after another into a long stream of these values. And the little less than sign means little endian, and then the F, as you saw in the documentation, means floating point. And we saw that it was 4 bytes, the standard size, which is kind of a giveaway there that it's a standard floating point value, a 32-bit floating point value. And so on some level, there is a little bit of conversion going on there to get the application's floating point data into the right low-level packed format for writing to the file. So if you're dealing within an application space with like something like double precision floating point, you can't just have the app say, well, it's floating point, so just write it to the file. It really does need to be in that correct, 32-bit floating point format when it's written to file. This might be obvious, but it's worth pointing it out in this context. Okay, so let's close this source file and let's move on to the next walkthrough. Okay, so next I'm going to drag over the walkthrough 05, and this is the floating point, the second floating point example. And this example is just like the one that we just went through, except it changes the amplitude values. And in fact, the first 3 integer samples have parity with the second 3 floating point walkthroughs, where a lot of the code is pretty much the same, except we're changing the amplitude values. So for these subsequent run-throughs, we'll just skim through the code here to go down to the bottom to look at the amplitude values. And we can see here that these amplitude values are different than the prior example. Instead of going from negative 0.5 to positive 0.5, we're going from 0.5 to 1.0, just like we did in the second integer sample walkthrough. And it looks like with these, I have this old comment here. Sorry about that. I will remove that, and I'm going to remove the comment out of here too as well. I'm sure it's in here too as well. Yeah, a little bit of copy paste there. Sorry. So next I'm going to grab the 05 floating point sample, and this is largely the same as the prior example, the prior walkthrough. So I'm going to just scroll down here to the bottom so that we can see the amplitude value changes, and we can see that the amplitude values now are 0.5 and 1.0 on the high end. And that's just like the second integer walkthrough that we went through. And there is parity between those 3 integer walkthroughs and these 3 floating point walkthroughs. They basically have largely the same code, but they change the amplitude values. So basically we can compare the results of the loudness or amplitude or volume level of the various audio files. So pretty much I'm just going to run this one with F5. I'm going to click Python debugger and it's going to run. And there it is. It's already finished. And I'm going to right click here and choose reveal and explore. And here is the new WAV file right there. And I'm going to double click on that. Okay. And then I'm going to double click on the one we just created right before this. Louder. And I'll go back to the one we just created. Okay, and now I'm going to go to the integer one that we created that has the same amplitude level. Let's listen. Right, and then we'll go back to the one that we just created on floating point. So basically, you can kind of see the same anomaly exists with floating point, and that probably is just very straightforward, but I kind of wanted to show it. Now let's close this Explorer window, and let's actually open this WAV file here in VS Code. I'm going to right-click up here and reopen editor with the hex editor. I'll drag this over to create some more space, and we can see that we no longer have that 3F000000. We have 3F80. 0000. And let's go over to our Python terminal and let's actually recall the prior command line and let's change this negative 0.5 to 1.0. And for the floating point value 1.0, we see the underlying bytes are 3F800000. So if I go back up here and I select 0.5, so we can see the values change. So when the 1 bit changes, when that 80 appears there, it becomes 1.0 instead of just 0.5. So if we kind of wanted to break this down sort of informally in Notepad, let's just take these high values here that we have, right? So when we had the 0.5 sample, right? And actually this file actually has two samples that are on the positive side, right? This new walkthrough file that we just went through, the 05 file, is using 1.0 and 0.5. So we should see the 3F without the 8.0 here, see? And we do. So if you look here, you can see here is 000080 That's little endian. So you reverse all those. That's 3F 800000. That's one of the sample values. And then the other sample value here is 3F 000000, all zeros. There's no 8.0 there after the 3F. So if we take both of those values, and I just typed them in here. So let's just take the first one here. We'll just put them in like this. And let me make this larger. Okay, so this one is 0.5, I believe, yes. And then 1.0 is 0x3f 800000. So hex helps us break this down, right? We know that the high bit is the sine bit. And so the sine bit we can see is 0 on both of these. Let me just put 0 here. Now the next 8 bits after the sine bit is the exponent. And so we can clearly see here we have an F in this lower nibble here, and then there's 3. And all of those are actually part of the exponent. So what sort of exponent do we have here? Well, we know the sine bit takes the highest bit up there in that highest byte. It is the leftmost bit. That means the next 7 bits there are for the exponent, but the exponent's 8 bits. So the lowest bit of the exponent is the highest bit of the second byte. So basically the second byte has all zeros here, and all of these seem to be 1. So since this has all zeros, we know that lowest bit of the exponent is 0. We know these are the next bits up, so these are all F, these are all 1. And then 3 is 2 1 bits next to each other, so it's like 1 1 and then 4 1s and then a 0. So we can say E equals, we can say we see a 0 for that highest bit of the exponent, then 1 1, that's part of the 3. The F takes up 4 bits, and then the lowest bit is 0. So if we put all of these together, what do we end up having here? Well, we know that this is 127, so if you just take that away, it's 126. So we could put a B there, and then we could just say 126. Now that's the biased exponent. We have to subtract 127 from that to get the real exponent. So the real exponent is 126 minus 127. So it's 2 to the 126 minus 127, or 2 to the negative 1. So we know 2 to the negative 1 is going to shift that binary point over 1, right? It's going to shift it over to give us a fractional value. So if we look further here, we see the mantissa has all zeros. So we're just going to put a 0 there, but not really, because there's that implicit 1 dot in binary, right? So I should put binary there. So we have a mantissa that's effectively 1.0 in binary. So if we bring all this together, we basically have, well, it's negative 1 to the 0 for the sine, which is basically 1, and then we multiply that times 2 to the negative 1, and then we multiply that times 1.0 binary, and that's going to give us 0.1 in binary, which equals 0.5 in decimal. And so that's our 0.5 sample. Now, if we go down here to this one where we see this very curious bit here being set, really we could start off by just simply copying all of our work here, or almost all of our work, and we can just put that here. Now we see that this bit is set here with that 8.0, so we know that we're talking about that bit being set, which will make this 127, which will make this 127, and that becomes a wash where you've got 2 to the 0, and we know that that becomes 1. And then we have the 1.0 binary mantissa, that has not changed. And so we can actually just borrow from this. We can paste this down here. We can say we have negative 1 to the 0, which is 1. And then we have 2 to the 0, which is 1. And then we have 1.0b, and 1.0b will be the result there, and that's 1.0 in decimal. So we're not going to do this with every walkthrough, but I just thought it'd be fun to just do this with one of them at least. Okay, so we can lower that down and dismiss that, and I will close this hex editor here, and we can close this walkthrough, and we'll move on to 06 here, and I'm going to go down to the bottom, and we see this is one where the amplitude does not change. It's 0.5 and 0.5, and we know that's going to be silent, but we'll just run this anyway. And it's already created the WAV file. We can just go ahead and open this right away here, right clicking and choosing reopen and our friend hex editor. Then we can just bring this over. And now we're just going to have all three Fs because everything is 0.5 in decimal. So we can actually go ahead and play that if we wanted to. I'll click on the WAV file again and just click play here. And we don't really hear anything. I can go back to the prior one, click on that, and play. Okay, I'll leave that, and then I'll click on the quiet one. There we go. All right, not much to hear there. I'll just click stop on that and close that. Okay, so that's it on this walkthrough. So let's close this source file. Okay, so next I'm going to load walkthrough 7. And this one's going to create a sine wave and write it out as 24-bit signed integer audio. And so we'll scroll down here to the bottom. We have the usual main stub here. It calls main. Our sample rate is 48 kilohertz. We have frequency of 400 hertz. Duration's 5 seconds. The amplitude is 0.5. We only have one value for the amplitude here because we're going to use sine wave related math here to produce all the samples given that amplitude value. And this is fairly standard stuff, so you can find a lot of stuff available on the internet about it if you want to get into it. But we'll skim over it right now just briefly. So this is going to create a file name that's going to be used to write the file. And this calls a function generate sine wave. That's similar to our generate square wave. We have a typo here. This is actually supposed to say sine wave. A little bit of copy paste here. I'm going to hit F2 and I'm going to type in sine wave and I hit enter. And you notice it changed the type name here and it also changed the type name down here. And VSCode's really great with that. It works very quickly. And you can just rename stuff and it'll change all the names like that. So this is going to call generate sine wave and it's going to assign the array that's going to contain the sine wave information in sine wave. Those are going to be the floating point values that represent the actual sine wave. And then it's going to call this function to convert those to 24-bit samples. That's the same as the earlier examples that we went through. And then like the earlier examples, it will write those out to the 24-bit audio file. So the only new function here is generate sine wave. So we can go to that function. I just pressed F12 to jump to there. And you can see how simple it is. So we have frequency, duration, seconds, sample rate, amplitude. And then it applies some fairly standard math here. So NP linspace is going to create an array of num frames, and num phrase is going to be our total number of samples. And this array is going to have time values from 0 to the total duration in seconds. And when NumPy arrays are used in mathematical operations with other arrays, or when NumPy functions are called with those arrays, the operation occurs on the entire array. So all the elements of the array generally participate. I speak very loosely. You have to look at the individual functions and the context and the data that you're working with. But for most of the fundamental operations, that's kind of what's going on. And this array is going to have time values from 0 to the total duration in seconds. Then it uses NumPy sine to actually operate on all those time values in connection with pi and the frequency. And that will result in a NumPy array. And then that's going to be multiplied to the amplitude, which will have a multiplying effect on the overall level of the overall sine wave. So this is not a NumPy overview, but I just wanted to give a quick blurb on that. At the end of the day, this function returns a NumPy array that has amplitude values that represent the sine wave we're trying to create. And I can hold the Alt key and press back to get back to where we were before, where this gets called. And that NumPy array goes into sine wave, and sine wave gets passed to the function that's going to convert it to 24-bit samples, and then you can write it out to PCM with this function here. And if you wanted to do the same thing and write to 32-bit float, you could actually just plug in the code to write to a 32-bit float file. All right, let's hit F5 to run this. I'll click Python debugger, and it's running. And it looks like it's created the WAV file here, so let's click on that. Let's hear what it sounds like. Much cleaner and nicer sounding than that rough, simplistic square wave. Okay, I'll close that file there. I'm going to right-click here and open Explorer. And I want to go down to the wave file we just created, and I'm going to open up Audacity, and I'm going to drag that wave file into here, and I'm just going to zoom in so we can see if there's a sine wave there. Oh my goodness, look at that. We have a sine wave. All right, there we go. Let me close that down, and then we can close down Explorer, and I'll exit that file. And for the last walkthrough, number 8, we have generate square wave. And this is going to generate a square wave by using a sine wave. So this function here is just like the sine wave function of the prior walkthrough, except it has this mpsine function call here. And mpsine will return a positive 1 for any element of the array that contains a positive value, and will return negative 1 for any element of the array that contains a negative element. So if you can imagine the sine wave going positive, negative, positive, negative. So for any portion of the sine wave that's positive, mpsine will return a 1. And for any portion of the sine wave that's negative, mpsine will return a negative 1. So mpsine ends up returning an array that's full of 1s or negative 1s, depending on the sign of the original element of the array used with mpsine. So in a sense, mpsine ends up creating this square wave where you have 1.0 and negative 1.0. Very similar to our first walkthrough, except we didn't use 1.0, we had 0.5 and negative 0.5. And what happens is it multiplies amplitude by all those 1s and negative 1s. So it takes that square wave of max amplitude and reduces it by whatever the ratio is represented by the amplitude. So if the amplitude is 0.5, it essentially cuts the square wave in half in terms of amplitude. A little bit off topic for our focus, but just wanted to mention that. And again, this is not a NumPy overview, but I just wanted to mention that in case you glance at this and were curious. Otherwise, everything else in here is very much the same as the prior walkthrough. Let's go ahead and just run this. I'm going to hit F5. Now, it didn't prompt this time because I had run it before I started the video. And it's already finished. I'm going to click on here, and we can play it. Yeah, that's definitely a square wave. We can go back to the sine wave. Square wave. Anyway, all right, that concludes this walkthrough. Let's go to the next section. All right, let's add walkthrough number 9 to the editor. So I'm going to drag that over. And if you didn't see walkthrough number 9 in the editor list before, it's because it's been added since that earlier part of the video. This walkthrough is very similar to walkthrough number 7. It generates a 24-bit PCM wave file that contains a sine wave. This walkthrough, however, is going to increase the amplitude of the sine wave over time. It's going to do this in 3-second sections of the file. The factor increasing amplitude will be increased by 1/10 every 3 seconds. The amplitude factor starts out at 0, so the initial samples will be 0 or negative infinity, quiet. That factor will increase 1/10 every 3 seconds. So after 3 seconds, it will increase to 0.1. And 3 seconds after that, it'll become 0.2. And it'll do this until it reaches 1.0. A factor of 1.0 won't change the sine wave. The factors that are lower than 1.0 will diminish the sine wave. The way you can think of this is that the sine wave gets generated at max amplitude, and we apply a factor to reduce it from that maximum. If we have a factor of 1.0, we don't change the sine wave. It remains at max amplitude. If we have a factor of 0, it's going to silence the sine wave. And all the factors in between, 0.1, 0.2, 0.3, and so forth, all the way up to 0.9 and then 1.0 after that, will have a varying degree of effect on the amplitude. The net effect of this is that the amplitude of the wave file will increase every 3 seconds. So the resulting wave file should have this sort of stepping increase every 3 seconds. It should increase by 1/10. And 1.0 doesn't affect the sine wave and leaves it at its maximum. In an upcoming utility walkthrough, we're going to graph the samples in the file so that you can see the increasing steps in amplitude visually. But initially, we're going to look at the source code, generate the wave file, and then we'll examine the wave file the same way we did with some of the other ones. So here we are at the top of the file, and this is one of the main differences, this function here. Let's skip this function for right now. And as we did with the other walkthroughs, we'll scroll all the way to the bottom here. Now, once we get to the main function, there's a lot of this that looks similar. Let's go through it really quickly. We have the usual sample rate of 48 kilohertz. We have a sine wave of 400 hertz. We have these values here. Let's skip these really quickly. Let's continue on down, and then we're going to jump right back up here and talk about these values. So we have the usual code here that's going to build a file name for the output wave file. Scrolling down, we see the call to that new function. Let's skip that for a second because that's a new thing, and we'll jump right back up to that. Let's go down here and look here. These two functions, the one that converts the sine wave into the 24-bit PCM samples, that's the same function as from the earlier walkthroughs, as is the write 24-bit PCM function. So we know we're going to convert that sine wave into PCM samples the same way, and we're going to write it out to disk the same way as we did in the earlier, samples, the earlier walkthrough. So let's jump up to the one big anomaly. That's this function here. And relating to that, we have some values up here that are not exactly the same as the earlier examples. So pretty much we want to focus on these values, and we want to focus on this function call and the body of that function. So duration seconds is the total duration of the wave file. Start amplitude is the amplitude we're going to start at, and as I described it earlier, we're going to start at negative infinity, and as we know, an amplitude of 0 is negative infinity, and we're going to increase that amplitude every 3 seconds by 0.1. That means we're going to increase the amplitude 0.1 of 0 dBFS. If you can imagine, from negative infinity to 0 dBFS is the whole. 1/10 of that is what will be increasing in amplitude every 3 seconds. And the step duration is 3.0, and that's the 3 seconds that I've been mentioning. So the meaning of these values is fairly straightforward. Let's go down to the function call. So I'm going to go back down here to the function call, and we have this function call here that's going to generate a sine wave with a stepped amplitude. That function takes the frequency, which is our 400 hertz. It takes the duration, the total duration of the sine wave, or what will end up being the file. There's the sample rate. We know that's 48 kilohertz. Here's our start amplitude, our amplitude increment, and the step duration, which is that 3 seconds. For every step of amplitude, we'll let that amplitude be the amplitude for a 3-second period. And after that 3-second period, we'll increase the amplitude factor by 1/10, and we'll move on to the next 3 seconds, and so on. All right, let's go into the body of that function. I'm going to put my cursor on that function and press F12. You can also do right click if you forget that it's F12 and then choose to go to the definition. Okay, so here we are. These are all of our parameters. We don't need to go through those again because we kind of know what they are. Let's scroll down here into the function. We have a bunch of value checks. Those should be fairly straightforward. I'm going to skip over those. Okay, then we set up some values before we enter a loop. Let's go over those values. We have num samples, and num samples is the total number of samples in the entire file. And the total number of samples in the entire file is the number of seconds multiplied by the sample rate. So we have 48 kilohertz as the sample rate. That's 48,000 samples per second. And we have duration seconds. So if we multiply duration seconds by 48 kilohertz, we end up with a value that equals the total number of samples we'll end up producing in this file. Number of samples per sec is actually number of samples per section. I should probably change that to section because it sounds like second. And that happens sometimes. Sometimes you're putting some code together, you come back later, and you look at a variable name, and you're like, must have been late. So we're going to highlight that variable and press F2 in VSCode because VSCode makes it very easy to fix these kinds of problems. I'm going to press the forward arrow because I want to mostly keep the variable, and I'm going to take this and name it section there at the end and then hit enter. And that'll fix that variable, so now its meaning is a little more clear to us. And you'll notice with num samples, we have int here, and that's basically going to floor the int. So if we have a fractional sample there, we don't deal with fractional samples here, so we're just going to floor that. Same thing is happening with the num samples per section. Now the number of sections we're going to have in the file is the total number of samples that will be in the file divided by the number of samples per section. Fairly straightforward. All right, let's go on to the next line here. So now we have some usage of numpy here. We're essentially going to create this t array, which is going to be our time value. And we're going to use linspace for that, and it's going to go from 0 to the duration seconds, which is the total duration of the file. And for that duration, from 0 to the total duration of the file, we're going to break it down into the number of samples that we're going to end up producing. So there'll be a time value in that array for each sample. Next, we're going to use that time array and we're going to create a sine wave. This is very similar to the walkthrough number 7. which is pretty much what we did in the earlier sine wave examples. Now, amplitude is the current amplitude that the loop is using, and it's going to default to start amplitude. And then basically we're going to loop from 0 to number of sections. And if you're familiar with range will start at 0 and it will go to 1 less than the endpoint that you specify. So num sections plus 1 is exclusive to the total values visited or provided by range. And another thing you can do when you're diving into some new code that somebody else wrote, or some open source thing or something like that, is you can kind of just get the gist of it by looking at it, right? So we look at this right now and we know we're processing sections and we know the general goal, and we kind of just see here's a start index, here's an end index, and then there's something being done from start to end here in the sine wave data. And then we do something to amplitude here. Oh, it looks like we're increasing its value every iteration. The keystroke output window here was not active before, so forgive me for that. I just activated it so you can see like keystrokes appear there in the lower window. But I'm also mentioning them out loud, so hopefully that's been good enough. Okay, great. Let's continue here. So our start index, well, what is that? Well, so this loop is going to start at 0, and it's going to go to 1, 2, 3, 4, 5, and so on, all the way up to the last section there. And so we know that I is going to be 0, 1, 2, 3, 4, and so on. And we know num samples per section is how many samples per section that we're going to be affecting with a unique amplitude value, or a unique amplitude factor, I should say. So at the beginning of the loop, when the loop is 0, we multiply 0 by num samples per section, and that gives us 0. So our start index starts out at 0. And as we move through each section of the sine wave, it will just simply multiply that index, and like if the index is 1, it'll go to the next 3-second section as the start index. So in the next iteration, I will be 1, and 1 times the number of samples per section will bring us to the start index for the next section of samples, that next 3-second section. So start index is finding a sample index location, but it's effectively finding the start of each 3-second section that we're looking to modify. So the end index is 1 past the current section we're working on. So that'll be the num samples per section times I plus 1. So you can imagine the start index is going to be the start of the section of samples, and the end index will be 1 past the last sample of that 3-second section. And just to prevent us from going past the last sample in the entire file, we perform a min here to prevent it from going past num samples. Great, now we have start index and end index. We can use Python slices with the array to affect only the samples from that start index to that end index. And you can see that's what we do right here. So from start index to end index, we multiply all of those samples by the amplitude factor. Now the amplitude factor actually happens to be the amplitude, because we can think of the sine wave as starting with an amplitude of 1.0. So the amplitude factor is just simply going to take some portion of that 1.0, or that maximum, which is effectively the amplitude. And so after we affect the amplitude of that one section, we prepare to process the next section by increasing the amplitude by the amplitude increment, which is 1/10 or 0.1. And then we move on to the next iteration of the loop. And after we're finished processing all the sections of the entire sine wave, we basically return that processed sine wave. And since you're already familiar with the earlier walkthroughs, you know already, and we can go down to the bottom of the file here, that that's just simply going to be returned here, and it's going to be converted into 24-bit PCM samples, and it will be written to a 24-bit PCM wave file. I need to mention one thing. I did make one change here, and I believe it was in the convert data to 24-bit PCM samples. Let's actually press F12 and go there, and I think it was here. Oh yeah, it's here. So the earlier walkthroughs had very short files, like 5 seconds. This particular walkthrough creates a much larger file, about 30 seconds. Because it's a larger file, it has more samples. You'll notice that this line here is different than from the earlier walkthroughs. If I go to walkthrough number 7 here and open that up temporarily, and I go down to the same function, you can see I'm using a normal Python byte array, which is not mutable. It being non-mutable means that this line down here at line 28 is not really performance friendly. Now that's something you generally wouldn't wouldn't notice if you're dealing with relatively small amount of data. But if you're iterating through a loop and you're constantly appending, you're having to regenerate an array every iteration. So for a 30-second file with all those samples, this was taking a long time because it kept appending and creating a new array as part of that appending. So I'm going to close this walkthrough 7 and go back to the file that we're focused on here, walkthrough 9, and you can see we're creating a byte array. Now a byte array is a counterpart to bytes. From an interface perspective, they're very similar. However, a byte array is mutable and it's much more performance friendly as you're appending to it, or you're otherwise modifying values that would require something immutable to be regenerated. So we don't really want to regenerate anything. We just need a buffer of bytes, and we want that thing to just be appended to or modified along the way without recreating it each time, each iteration, because doing that can get very slow. And then within the loop here, I'm using a slice to modify sections as I add the 24-bit PCM samples. Other than that, it's pretty much doing the same thing. It's just much, much faster than the function in the other walkthroughs. In this case, these are simple walkthroughs, and I really wanted to keep the initial ones very familiar to those who are kind of new to Python. But in this case, it was taking a while, so I decided to optimize this, which had me adding stuff that made it a little more complex, but much more performance friendly. Okay, I wanted to clarify that. Now, we already generated the file. I'm just going to hit F5. There's no breakpoints. It's just going to run and regenerate the WAV file. Just in case somebody pops to this place in the video, it makes sense. All right, great. So here's the WAV file. We're going to take a quick glance in that file in a second, but first let's right-click on the tab here and View or Reveal in Explorer, and let's go here right below that Python file, and let's double-click on the WAV file. And we don't hear anything at first because the first one is all zeros, which is, negative infinity. And we can hear it increasing. Okay, so we have a sine wave that's increasing in steps. All right, let's close the media player, and I'll close Explorer. And now we're back here in VSCode. So I'm actually just going to make this a little wider so it's clear this is a WAV file. And I'm going to click on the WAV file, and I'm going to drag it here into VSCode. And it wants to play it, but I'm going to right-click and change the editor by Reopen Editor and choose on Hex Editor. Okay, here's the 24-bit PCM WAV file. We can see the RIFF header and all that stuff there at the top. We discussed that a little bit in the earlier sections. And what we're going to do is take a really quick fuzzy tour of this file. We're not going to worry about understanding all the exact details. We're just going to do this to kind of just look at a few samples and whatnot. We know the start of the file has an amplitude of 0, so all those samples are going to be 0. And the end of the file has an amplitude of 1.0. So those values are going to be very high at the end of the file. We kind of have that general understanding. So let's get our calculator out. All right, let's type in our sample rate of 48,000. Now each sample is 3 bytes, so let's multiply that by 3. So we have 144,000 bytes per second. This is mono, so there's only one channel. So each section is 3 seconds. We can multiply that by 3. And that gives us 432,000 bytes per section. We see the hexadecimal value for that is 69780 in hex. And VS Code's hex editor gives us a little handy hex address here of the file starting at 0. So I'm just going to click my cursor somewhere in there, and I'm going to press page down until we get to that 69 whatever. Now actually I'm going to go back over here and just see that 69780. So I can hold this down, and actually what I'll do is I'll use the cursor here. This can be a little sensitive, but we want to find 69 something or other. We can just go down here until, oh, there we go. So we have some non-zero samples, and then there's 0. So somewhere around here. So I'm going to click the cursor here, and I'm going to press page down until we see some non-zero samples. And there we go, right there. So we can see that this is one transition from the amplitude of 0 to the amplitude of 0.1. Remember, a sine wave can be depicted visually with a 0 midline. And you can imagine 1.0 is at the top end, and negative 1.0 is at the bottom end. So as you have a wave, it's fluctuating depending on the amplitude, up and down, up and down. So even if the amplitude is 1.0, there's still going to be changes. So our goal is not to find like a static set of similar samples. We're looking at this to just kind of get a gist here of where we're at. Now we kind of know that this is the first section of the file up here, and it's got all zeros. That makes sense to us. Now we look here, and if you look, this is the first non-zero number. And I'm going to make an assumption right now that that's the low byte of the first non-zero sample. And if that holds true, then this must be the second byte. And then the high byte of that first sample must be this one. And since this is 0, that sort of makes sense to me that this is 0. Let's see the next one to kind of see if these assumptions are holding up. Well, the next one has 8556, and look, we have an 01 in that high byte. In this particular fuzzy, look at this, that high byte can kind of help us here because it's not going to change as often as the other bytes. So I'm kind of just glancing at that quickly, and look at here, we go 3 over and we see a 2, and we go a couple more over here and we see a 2, and we go a couple more over and we see a 3, and a couple more over 3, 4, 5, 6, and so on. So we can kind of see it's going like from that midline on up. Actually, it seems to be starting by going up there, and it'll eventually go up and then come back down and go to the negative side. For the negative side, we should see that most significant bit set. I'm going to drag the scroll bar and go all the way down here to the bottom of the file. I'll click in here somewhere. So let's assume these last 3 bytes are a sample. Well, that high byte has the most significant bit set, so that must be a negative sample. And if we look over here, we see another one with the high byte. So we see an F9 and an F2. And if we go 1, 2, and then 3, we see EB. 1, 2, and 3, we see E5. You see how that's a negative number that's getting higher, right? Because the most significant bit is set, but because it's a signed integer, it's actually increasing in value. And so let's scroll up here a little bit and see if we can find some 7Fs here. Oh, here we go. We scrolled up a little bit, and notice there's a 7FFF here, right? So that catches my eye. But I would expect for positive that 7F would be the high byte here. So I'm going to assume here for a second that these 3 are a sample. If that's the case, this must be the low byte of the next sample. And look, we see FF, FF, and here's a 7F. That's the maximum possible sample. That's effectively 1.0 on the high end, or 0 dBFS. Let's see if this assumption continues to hold up. Well, this would be a low byte, low byte. Oh, we got another 7F. That makes sense. Notice it's going down. We have 7D, 4C, 7F again. Let's see if we can find the first non-7F. Oh, here we go. 7E is a high byte. Then we go 1, 2, 3. Here's 7D. So obviously it's going down. What we might discern from this is there's a little bit of a steep drop as it gets going. We have 7E, and then we have this 7D, and then we have 7B, and 7, 7, 7, 4, 7, 2, and so on and so forth. In a small bit, we're going to actually graph this file so that we can see the steps visually. But first, let's set up the utility that's going to help us do that. Okay, let's go to the next section. All right, so I'm going to actually close this file here, and I'm going to close the source file here, and let's minimize VSCode, and we can actually exit the calculator for now. And here we are at the command line. So the first thing that I want to do is recall the command line that we use to activate our Python environment. So I'm going to press enter on the activate script, and we can see our Python environment is active because of the parenthetical that's right next to the command prompt. That's great. I'm going to type in ls so that we can see the folders that are underneath the repo that we cloned earlier. Okay, I'm going to change into the audioutil directory. And what we're going to do is we're going to install this. Now you need an internet connection when you do this so that it can find the necessary packages to install this. So you'll type in pip install space -e and dot. Now audioutil is a command line utility, and it's written in Python. And Python provides a very convenient way to install a package like that in what they refer to as an editable install or an edit mode install. And that's what that -e switch does. So when we install an executable in editable mode or developer mode, it's what developers can use to actually install a package for something like audioutil, but to do so in a way where the main source code for the package isn't in the package area of the Python installation, but rather what editable mode does is it sets things up in a way where the source code, where it is right now, is the source code for the installed package. So you can actually edit the package and kind of work on it and debug it and whatnot, yet it gets installed as part of the Python environment. So any command line, executables and whatnot do get installed there, as you'll see in a second, but they aren't only installed there with all the source code. Rather, that environment is going to be using the source code in our current location here, where we have VS Code set up. So we can actually load the audio util in VS Code and debug it if we want to. Now, you don't have to install it this way to go through the walkthroughs that we're going to go through, because I don't think we're actually going to debug the tool live right now in these walkthroughs. I can't say we won't do that. I might change my mind, but I don't think we are. So you could install it however you want, but this is what I'm going to do because this is the way I work with the tool. So while I'm in the audio util directory, I'm going to type in pip install -e for editable mode, and then dot, meaning install this current directory. So -e is editable mode, and the dot is in this current directory. So we'll hit enter, and Python is going to go and see what this package requires. Going to download any necessary packages that this package needs, this audio util. Always use caution when you're using external packages and things like that. And so just FYI. Okay, great. It's finished. I'm going to type in clear to clear the window here. And what I'm going to do is we're going to test to see if it's installed. So I'm going to type in audio util and I hit tab, and I'm going to type in -h and hit enter. Okay, great. The utility is installed, but I do notice a warning up here that ffmpeg is not installed. So I'm on Windows, and I'll show you how I resolve that here on Windows. First I type in clear, and then I'm going to use winget, and you can just type in winget search ffmpeg if you want to kind of see what's available. So I'm going to go and do that just to see what's available. So I'm going to scroll to the top up here. This is the one that I want because this is the one that I've been using. And you always have to be careful of the things you download and whatnot. And I can't vouch for all downloads and all that kind of stuff. You have to do your due diligence. But I recall looking into this guyan.ffmpeg, and it seemed reasonable enough to use on a development system or in a VM or something. So I'm going to copy this and right click to copy it to the clipboard. I'm going to go down here and type in winget install, and I'm going to paste in that ID and just hit enter. Okay, great. ffmpeg's installed. Let's actually clear the window here, and let's type in ffmpeg help. Oh, you know what? Let's reopen the command prompt. So I'm going to type in exit. I'm going to do a win-x and then select terminal. And I'm going to go back into the repo. And I'm going to recall our Python environment activation line and activate our Python environment again. And we see it's been activated here. And I'm going to run audio utility -h for help again. And this time it runs without the ffmpeg error message. Great, everything is set up. All right, let's change into the walkthroughs directory. And I'm going to make this a little bit wider here like this. I'm going to move this out a little bit. All right, since we've gone through these walkthroughs, all the WAV files should be created. You can see this by doing ls, and you should see the WAV files there. Now, if your WAV files aren't there, you can just regenerate them all again by doing the following command. gci star.py, and then you're going to run Python against each of the Python scripts. That'll basically just run all the scripts and regenerate the WAV files. I don't need to do it, but it's not a big deal, so I'm going to run it. Great, all the walkthrough WAV files have been generated. Basically, in all of these walkthroughs, we've been using a 400 Hertz frequency. So let me bring up the calculator here in Windows, and I'm going to go to the scientific calculator. So I'm going to type in 1 divided by 400. And I'm going to hit enter. This is the amount of time it takes per cycle. So a 400 Hertz tone has 400 cycles per second, and each cycle takes 0.0025 seconds. So if I bring up Notepad here for a second, we can say that 0.0025, and let me make this larger, okay? 0025, that's how long it takes per cycle. So from the beginning of the file, the first cycle will end at 0.0025. So we might then say that 0024 is just before the end of the first cycle. It's 0.0001 before the end of the first cycle. And going down here, we might say that 0.0026 is 0.0001 past the end of the first cycle, or 0.0001 into the next cycle, the second cycle from the start of the file. So let's go back to the command line. Audioutil has a command here called dump. So if we go and type in dump-h, we can see the help for that command. Let me actually just clear the window and recall that command line so that we can see the help on the fresh screen here, on the fresh terminal. So dump is going to dump out some raw samples. So let's actually have it do that. But since there are so many samples, even in a 5-second file, we don't want it to do so many. Let's try to actually dump the last few samples of the first cycle in the file and the first few samples of the next cycle, the second cycle from the start of the file. Well, what we can do is let's specify the file for walkthrough 1, and that would be the wave file. So I have that specified. And then I'm going to type space and -- start at, and I'm going to type in 0.0024, which we know is a little bit before the end of that first cycle. And then I'm going to type space -- stop at, and 0.0025 is on the cycle beginning there, the beginning of the next cycle. Let's go one past. Let's go 0.0001 into that second cycle of the file. So we're going to dump samples starting at 0.0024 and stopping at 0.0026. And it looks like our calculations were right. We can see here there's a signed negative integer value here, and that's 0.5 on the negative side. And we can see that 400,000 hex is 0.5 on the positive side. So we've been able to peek at the samples at the end of the first period and at the start of the second period. All right, let's clear the terminal window. All right, so now let's try the same thing with the floating point file. Now, just because it's floating point doesn't mean that the frequency cycle is any different. So what we can do is we can recall actually the dump command that we just ran, but we can actually remove the 01 file. And then what is our floating point, walkthrough number? Let me just comment that out. And let me type ls star float star. I think that'll show us. Yeah, great, 04. So I'm going to clear the window here and then recall this command line here. And I'm going to type in 04 and tab. And we can actually extend this out a little bit here. All right, terrific. Let's run this. Oh, that's wonderful. What's the matter here? This is failing. Oh, what happened? Oh, you know what I did? I specified the Python file. Okay, so let's actually clear. And let's go up here, and we're going to go here. And we are going to type in 04 and hit tab and tab. I needed 2 tabs there. And I'll expand this out a little bit there. Okay, terrific. Now let's hit enter and see how it does. Terrific. We see in the floating point file, it has negative 0.5 at the end of that first cycle. And the start of the next cycle is plus 0.5. Now with the floating point dump command, you can actually put a -v in here and get a little bit more information about the floating point values. Let's hit enter with a single -v. And you can see here, what it does here is it shows us the sine bit. The sine bit is 1. The biased exponent is 126. That 126 equates to a real actual exponent of -1. It shows us the mantissa value, and it shows us the overall raw 32-bit sample value. Okay, I'm going to clear the terminal window. Let's add 2 verbosity switches, -vv. And with -vv, you see it adds this 24-bit integer sample here. So we can see the equivalent 24-bit integer sample, and we can see for -5, of course, it's C00000, and we see for +5, it's 400000. Terrific. Let's clear the terminal window, and let's add a third verbosity switch to the end of the command line there. So I have VVV. Let me actually pull this out there a little bit. Okay, great. Now let's hit enter. And this just adds the normal integer value for the sample, which is -4194304 for the -0.5 value, and 4194304 for the positive 0.5 value. And let's clear the terminal window, and let's add a 4th verbosity switch. What this does is it takes the 24-bit value that was derived from the floating point value and rederives the floating point value. And we can see here that these actually match in this particular case. So basically, all 24-bit values that you can derive from a floating point value isn't going to produce a 24-bit value that exactly matches the floating point value. So in a case like that, you would see a difference. But in this case, 0.5 can be represented without quantization error in both formats. Hey folks, quick insert here. When looking closer at the dump command, I figured I should add floating point output for the 24-bit PCM sample dump. So I went ahead and added -v support for the 24-bit dump. So here's the 24-bit sample dump, just normal without -v. So the current command line is going to dump the wave file we created in walkthrough number 1. That's the -0.5 to +0.5 wave file. And I'm going to press enter to dump those samples that we were looking at. And that's the normal dump that we looked at in the walkthrough. And now I'm going to recall the command line and just add a -v to that. And it'll give us the first level of floating point verbosity. And then I'm going to recall the command line again and add another -v, and we'll get the next level of floating point verbosity. And then of course I can add another one to add that third level of floating point verbosity. Depending on where I put this in the video, the verbosity for floating point might be after this point in time, so forgive me for that. I think I'll put this after the floating point verbosity, so it'll make sense. But just in case. In any event, you can see it's still outputting the 24-bit PCM samples that we were looking at. These are from the end of the first period and the start of the second period in that wave file from walkthrough number 1. And so now it's just going to output the floating point information for that sample right next to the sample. And of course, with that extra verbosity for floating point information, it's going to have what the sine and stuff would be had it been a floating point sample as an example. Although keep in mind, since it's deriving the floating point sample, so to speak, from the 24-bit sample, it's not going to magically arrive at some original floating point value that this 24-bit sample was derived from, simply because that information is lost once you convert to 24-bit. So this is simply taking a 24-bit sample and producing the floating point sample. And so there's going to be no quantization error in that, since the floating point sample is derived from the 24-bit integer sample. So just keep that in mind. Therefore, when you look at the re-derivation of the 24-bit sample in the verbose floating point output, it's just simply going to arrive back at the 24-bit sample that it just used to create the floating point representation. And that's different than dumping actual floating point samples, which will have actual quantization errors if they were to get converted to 24-bit. Just keep that in mind when you're looking at the output and when you're considering one sample format and another and the conversions back and forth. All right, that's it. Now back to the video. Okay, so we've generated all the wave files for all the walkthroughs, as you can see. And you should have the same thing if you're following along. So I'm going to type in audioutil plot samples, and then I'm just going to choose one of these. Let's just choose the one from the first walkthrough, and I'm just going to hit enter. Oh, it's samples. So I have to type in samples, not sample, sorry. All right, so this is a plot of the 5-second wave file. Let's actually maximize this. Now you might be saying it looks like a big rectangle. Yeah, but that's because you're far away from the detail. We need to zoom in. So this is a result of matplotlib here. And I think one good thing about these walkthroughs, and perhaps this utility, is if you haven't used matplotlib before, it might be a nice introduction. So when matplotlib makes a plot like this in its default window, there's some little icons down here, and I'm going to click on the magnifying glass. And after I click on the magnifying glass, I'm going to go up here, and then I'm going to drag this down like this, make a very narrow sort of window or selection, if you will, and then I'm going to release. And when I do that, you can clearly see there's a square wave there. And we can actually do that again. So I can drag right here and just, select a few of those. And here, I'll just do it like this. And then I'll release. And now we're very close in like this. And it's kind of cool like that. And you can see here on the side the equivalent floating point value. So if you're not used to scientific notation, pay close attention to the -01, the E-01, because that means that this is 0.6. It's not 6.0. You have to pay attention to the E-01. Now, actually, if I exit from here and we look here, if I type -H, we can see that there is a switch. Type in fixed, and then it should show fixed. I haven't used this in a while because I don't mind the scientific notation. And then we're going to go here and we're going to select this. And you can kind of see this might be a little more sensible for this particular file. It's kind of cool. Okay, great. So I'm going to exit from here. Now, what I'm going to do is clear the terminal window, and then I'm going to paste this command line in right here. And this command line is going to act as a mask to select these particular files. In fact, I can just backspace here and you can just see it's going to select these files and load them in. So we can say audioutil, plot samples, and those files, and then we can just hit enter. And there we go. It's going to show us all these files at once. Now, the default title it gives to each graph is going to relate to the file name itself, as well as some metadata that it gets from the file. So we can see here, this is a 24-bit format file. We can see here's 24-bit format, and there's 24-bit format, and this is 24-bit format. So I've selected 4 different 24-bit format files. Now, this is from the first walkthrough, second walkthrough, third walkthrough, and this is from the 8th walkthrough. Now, you remember the first walkthrough was -0.5 to plus 0.5. Remember again, this is scientific notation. And this is the wave file that produced a square wave by going from plus 0.5 to plus 1.0. And you can see, even though this had higher sample values, the distance between the sample values was less than this. So this one was quieter than this one. And this is the one where we kept it at 5. We didn't change the samples at all. So it just stayed at 5, which created no fluctuations. There was no frequency being recreated. And so we see a line for that. Now, just like the other graphs, we can zoom into this one. So if I click down here on the magnifying glass, I can go up here in this window and just grab a small little area like this and release. And after I do that, it zooms into all of them at the same time so we can kind of see them, side by side. Okay, great. So we see there's a little bit side by side here. Let's go on to the next one. So I'm going to close this window and I'm going to clear this terminal window. All right, now let's plot one of the sine waves that we have here. So let me actually see which one is a sine wave here. I'll just do ls sine. All right, it looks like 07. So let's start with 07 and then we'll do 09 after. So we're going to say plot samples and 07 tab. And this time I'm going to say fixed here so we can just get that kind of normal fixed appearance there on the side axis here. On the y-axis, it looks more normal there. Sorry, my voice is going. It's been a long day. So I'm actually going to click the magnifying glass down here, and then I'm going to select a small section right here, and we can get a close-up look at it. Well, that's looking like a sine wave to me. All right, let's grab another section here so we can zoom in even further. And there we go. This is our sine wave, and we can see it goes up here to about 0.5, and it goes down here to about 0.5. And this just kind of oscillates there 400 times per second, -0.5 to +0.5. Okay, pretty cool. Let's close this, and let's actually clear the terminal window. All right, remember 09 where we had not only the sine wave, but we were changing amplitude throughout to the end in 10 different increments. Each one would increase that amplitude factor by 1/10. That's 1/10 of that range from -infinity to 0 dBFS, or 0 to 1.0 in floating point. So let's actually recall, we can actually use our the prior command line. So I will actually go here and let's replace this with 09, tab, and let's hit enter on this. And here we go. So you can see here's where we start out at 0, and this is where we go up 1/10, another 10th, another 10th, so on until we get to 1.0. Now what we can do is, I'll tell you what, let's click on the magnifying glass. Let me actually let me maximize this. I'm going to click on is I on the magnifying? Yeah, I'm on the magnifying glass now. And now I'm going to select right here between this change in amplitude, and let's release. And let's do that again because we're still kind of zoomed out. So I'll select a smaller portion here. And there we go. And we can kind of see it goes here. It looks like 0.3 would be here. And it goes from 0.3 to 0.4. And we can click the back arrow to go back and back arrow again to go back. And that should take us to the original thing. And we can go somewhere further out. Let's go here and select a very thin, narrow area here and see if that's zoomed in enough. Let's do it again. And we'll click this area here. And we can see for this segment, we went from, let's see, that's 0.6. So this must be 0.7 and it went to 0.8. Okay, very cool. Let's actually exit from here. Let me clear the terminal window. All right, so let me type in audioutil-h, and you can see there's a thing here called steady levels. So I'll type in steady levels and we'll type in -h. So rather than reading through all this, let me just clear the terminal window. Let's actually run this. So let me bring back the steady levels, 09, tab, and we're just going to hit enter. So this particular steady levels is textual in nature. So I'm going to make the characters smaller here. I don't know if they'll come through on the video, but this is a way of looking at the various levels within the file. Now, steady levels is only meant really to be used on a file where there's some sort of test tone playing, and it remains at some steady amplitude at different points in the file, like as if you're performing some test. So I think with this one, I did add the CSV option as well. So you can type -C and you can paste this into Excel. We're actually not going to do that right now. I'm going to clear the window here and I'm going to recall the textual command line here. I'm going to get rid of that -C and I'm going to go here and type in plot steady levels and I'm going to hit enter. And I'm going to maximize the window. And what this is doing is actually showing here's level 2, and it's just showing that it's at 2.0. And this one's level 3, and it's at 3.0. And so on and so forth. And down here it has like the dBFS value. So this is 0.0 dBFS. This is 3.1 dBFS right here. And so on and so forth. All right, so I'm going to close this window here. Now for this next one to make sense, I want to show you a little test that I had run. I took an old Tascam and I had a test tone on it, and I played that test tone back. It was going into the F6 at a mic level with the dial set to 0 dBFS, recording in float. And so I want you to see that experiment first, and then we'll come back here. So this is level 0. This is level 0. This is level 1. This is level 2. This is level 3. This is level 4. This is level 5. This is level 6. Level 7. Level 8. Level 9. Level 10. Level 11. Level 12. Level 13 doesn't go right away, so we have to go back and do it again. Level 13. Level 14. Level 15. Level 16. Level 17. Level 17. Level 18. Level 19. Level 20. Level 21 won't happen right away, so we'll click again. Level 21. Level 22, and the H4n says it's exceeding the maximum input level. We will stop here. Okay, great. Now that you've seen that, imagine now I take that file from the F6. It was recorded at some live thing. In this case, it was the Tascam. So now with that experiment in mind, you know that I was adjusting the Tascam volume or output while the F6 was recording in float mode. And I increased that volume step by step. So what I want to do is I want to run steady levels on that file that was just run. So I'm going to clear the window here. So I'm going to type in audioutil plot steady levels. And C:, and I think I have it in here. And there's the wave. Now this is the wave that was recorded where the level was exceeded during recording. So let's actually see a graph of those levels. So I'll hit enter. And I'll maximize. Oh, now this at the end was stuff that I did that was not shown in what you just saw. So the levels here go from level 0 up to 22. So there's 23 levels we're interested in. So I'm going to exit from this and I'm going to say -M23 because I only want to see 23 different levels and just forget the ones at the end there. So I had just adjusted the volume and stuff after the experiment was over. And so that affected what was actually recorded in the wave file. So by ignoring the level changes after 23, we don't see that extraneous stuff. So I'm just going to hit enter. And here we go. I'm going to maximize this window. And basically what we can see here is for each level on the Tascam's volume output, for each level of output that it has, we can see the floating point value that it ended up creating on the F6. Now, I'm not saying that's some kind of fantastic piece of information. You could learn something about your equipment or your situation by using a test like this. For example, you could run a test tone in a room and kind of see, what sort of samples it's creating or what general levels you're hitting in terms of that sample range. Also, we know the F6 was getting to what it felt was its exceeded level for the microphone input. And we see that that exceeded level didn't even get up here to 0 dBFS. It's actually here around 0.75. So that was a little piece of interesting information. As well, I also noticed during this experiment that the Tascam's level can go above 22, but those levels above 22 have no effect on the actual floating point values. And that's because those volume levels above, I think it's above 22 or 23 on that old Tascam, don't really do anything. At least in the mode that I was using it in. And that doesn't necessarily mean it's bad or anything like that. It just means that there were extra levels that whatever being used in there had no purpose for those levels, but they were nevertheless being reflected as though, you were incrementing something. I confirmed it was Tascam DR-22WL volume levels after 25, which did not have any effect despite the increments on the display going all the way up to volume level 33. In other words, levels 25 through 33 are the same. This was for the mode or settings I was using it within, though I don't suspect any modes or settings had anything to do with the issue. I think this is just something about the design of the unit, although I just want to clarify that's an assumptive observation. Now, it's not that this thing was a big find or anything, but I found it interesting to learn a little bit about my equipment, something that I may not have caught had I not been doing some level checks or tests of this nature. And there are other things I've run into, but this was just the one example I wanted to present right now. Suffice to say, if you test levels with your equipment in various different ways, you might learn more about the nature of your equipment. "21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Hey folks, this is a quick insert created after the walkthrough of plot steady levels. So let's go ahead and close this plot steady levels. Now there is a textual variation of steady levels. So let's recall the plot command line here and remove the word plot. So I'm just going to remove that, and now it just will have steady levels. And we will have steady levels. It'll be the same command line, except there's no word plot. And that will output text to the display here, to the terminal window. Now it's quite a bit of information in human readable format, so I'm going to actually make the text very small in the terminal window. This may be too small for the video, but there's a CSV output option, which I tend to focus on for these textual output commands that we're going to go over. This is actually just one of them. There's a couple of others. So what I'm going to do is actually clear the window here, and I'm going to recall that command line, and I'm actually going to make this large again. Let me just see how large I can get that. Great. And now what I'm going to do is add a -C, and I'll press enter, and I'll do it first here to the console. If you just do -C, that comes out to the terminal window. I'll scrunch this down again. Okay, it's a little small, so I'm actually now going to just increase it back again. And I'm actually going to clear the terminal window and bring that command line back. So now what I'm going to do is I'm going to say -O for output, and I'm going to put a space and steady levels.csv, and I'm going to press enter. Okay, so now that I've done that, we have a CSV, and if I just type in steady tab until I get that CSV, I have Excel installed, so just pressing enter will start Excel up. Now Excel has observed something that looks like scientific notation, and it's asking if I want to apply scientific notation to that data that looks like scientific notation, and I always click on convert. So yes, affirmative. So this is a little bright for me. I'm going to change the colors to kind of make a dark mode. All right, so when I use an Excel spreadsheet with numbers like this, I'll click up there to select all and then double click a column to get the columns sort of auto fitted. And then I'm going to select column B through column K, right click, format cells, and I'm going to go to number format, and I'm just going to give each number 3 decimal places. And we're not going to spend a long time here. I just kind of wanted to give you an idea that this is the same information from the steady levels plot, except it's output textually in a CSV format by the utility, and it can be used as desired. So if I were playing a test tone in a room and adjusting the gain knob on a recorder or some kind of amplifier or device within my analog or digital chain, and then I wanted to look at those steady levels to kind of see, like, what happened at the different settings, I might use this spreadsheet, for example, to make notes there or whatever. For myself, I largely used it to kind of verify things while working on the video and to just check things out and whatnot. All right, so let's exit from this. I'm going to say no, we don't need to save that. Okay, let's clear the terminal window. All right, let's go to the next section. All right, so the next command in the utility that I wanted to show is interactive. So that's audioutil space interactive. And you can press question mark to get help from this mode. Basically, this mode allows you to enter a 32-bit floating point value in a number of different ways, and then it will output some information about that floating point number. I not only put this in place as something that I could share as part of this video, because if you're interested in looking at the format and toying around with various values, it can be a great way of interacting to kind of learn about the format. As well, it was one of the ways I used to double check my work as I was working on the video, so it had some utilitarian value there as well. And again, I'm sharing it for what it's worth. We're not going to spend a long time on this, but I'll give a quick overview here. Let's start with a very simple value. I'll just type in 1.0. We've seen this value a number of times in this video. 1.0 is biased exponent 127. We kind of know by now 127 minus 127 is a real exponent of 0, and 2 to the 0 is a 1. The sign bit is 0, so that's negative 1 to the 0, so that's a 1. So we have 2 factors that are 1, so it's pretty much up to the mantissa what our value is at this point. Well, we see that the mantissa is empty, it's blank, but since the biased exponent is not 0, we know it's not a subnormal number, and therefore we have that implicitly prefixed 1 dot in binary point, which is prefixed to the mantissa, so the mantissa is effectively 1.0000, etc., in binary point. This is all to say that it's 1.0. Now, what this is showing is that 1.0, which we entered, is 1.0. It's also breaking that down into the various components, which we just verified, and it's actually showing if this were converted to 24-bit audio, what would it be? And it's showing that it clamped it at 7F, FF, and as we have discussed, due to the 2's complement anomaly, the value 800,000 hex is not available on the positive end. The positive end is 1 short of its max, which is this 7F, FF, and therefore that 1.0 ends up being 0.999999. And remember, this is scientific notation, so 9.9 is not 9.9 in decimal, it's 9.9 times 10 to the negative 1, because you have this e minus 01. Another way to look at it is you can take the 01, if you see a minus there, it means you move that decimal point to the left that many times. So if you were to move the decimal point over to the left 1 time, you would have 0.999999 and so forth. Okay, another format you can enter is just the raw hex value. So we'll just take this raw hex value here because it'll just be easy for us to test, and I'll just enter this. So you can see from the raw 32-bit hex value, 3F800000, the interactive prompt is able to derive 1.0, and of course it breaks down the floating point, information and so forth. If we were to choose another floating point value, value like 0.5. This is another one we should be familiar with by now. If I enter that, we have a biased exponent of 126, which ends up being 126 minus 127. So that's going to be an actual exponent of -1. That's 2 to the -1. And 2 to the -1 we know is 0.5 by now. And the mantissa has all zeros, but we know there's that implicit 1 period before all those zeros. And what is 1/2 of 1.0 in binary point? Well, that's 0.1 in binary point. We shift them all over to the right by 1, so that prefixed 1 gets shifted over 1 to the right of the decimal point, or the binary point, I should say, and that's 1/2, which makes sense because it's 1/2. Now, another thing you can do if you wanted to play around with this is you could enter in the values individually. So I could say the sine is 0 and the biased exponent is going to be 126. I can say the mantissa is going to be 0, and I hit enter here, and we see that it derives 0.5. Now again, this is not 5.0. Remember, we have the e minus 01, which is 5.00000 times 10 to the -1, which is 0.5. So remember to keep an eye out for that scientific notation. Easy to get confused with fixed point if you're not looking for it. So by entering the individual components, we were able to kind of rederive that 0.5 value. But you can actually play around with it. You can say, well, what if the sine bit were 1 and everything else were the same? And you press enter, and of course the sign changes, everything else is otherwise the same. But let's say you were interested in the smallest subnormal number. You could enter in 0, comma, and 0 for the biased exponent. Remember, when the biased exponent is 0, that's a subnormal number, and there is no prefixed 1 point on the mantissa anymore. So the mantissa is itself that binary point number, and let's give it the smallest mantissa possible, which would be a 1. If I press enter, that yields the smallest subnormal number. So we have 1.4 e minus 45, or times 10 to the -45. Extraordinarily small number. Very, very small number. And you can actually look at the breakdown of that here. Since we entered these values, we kind of know that this is the breakdown. You can actually use up arrow and put a 2 here and hit enter, and you could see the difference between the lowest and the second lowest subnormal numbers, and so on and so forth. So the interactive tool is a way of kind of getting in there and typing in numbers to kind of see what the 32-bit representation is, or to start from a 32-bit representation and find out what the floating point value is, or maybe enter those components of the IEEE-754 Float32 value directly to see what the resulting floating point value is. All right, let's quit this here and hit enter, and let's clear the terminal window. All right, let's go on to the next section. Okay, before we get into these range commands, the first ones that I'm going to show are the ones that output to the terminal window in a sort of human readable format. Now, the lines that are output for those commands can be quite large. Now, it's manageable to glance at those when you're right in front of the terminal window, but on a video like this, they'd probably be very, very small. Probably readable if you're on a big display or if you want to zoom on your phone or something, but just in case that's inconvenient for folks, what I'm going to do is output, let's say, the range simple format and the detail format in the terminal window. And I'm going to zoom in, and it's not going to look very pretty when it's zoomed in, but it'll be larger. And I'm going to go over the first line of those formats. And then after that, I'll create a CSV to load the respective range into Excel. And so we won't be going through each and every line of all those details. And I just wanted to give a heads up on that, because if I didn't do that, you might be thinking, are we going to go through all these lines? And I just want to give you a heads up on that. Okay, so I'm going to press on Win key X and open up a terminal window. And I'm going to go to Demo and going to hit Enter. And I'm just going to recall our activation script command line to activate our Python environment. I'm going to hit enter, and we see it's active because it has the environment name next to the prompt. And I'm going to type in audioutil-h, and we can see that there is a range. Let's look at that. And we can see that there's range simple and range detailed. Range simple is obviously going to be simpler in some way or another. I'll explain that in a second. Range detailed is much more detailed. Both of these commands were born from this notion of wanting to have something that sort of mapped out the ranges from 0.0 to 1.0 of both the 24-bit integer and 32-bit floating point formats. And I did that for myself really because I wanted a way of using Excel, for example, to examine these ranges and maybe look through them and kind of see some of the interesting correlations of different areas of the ranges. It was from doing this that I created some of the graphs in the earlier part of this video. I'm showing these commands here because they can be useful for glancing at that range from 0.0 to 1.0 and to see some interesting values about that value range relating to the two number format systems, 24-bit integer and 32-bit floating point. So I'm not going to spend a lot of time on these. I'm just going to touch on them and give a brief little overview. And so let's get started. So first I'm going to clear the terminal window and I'm going to recall our command line for range and I'm going to type in range simple and I'm just going to hit enter. Now let me resize this terminal window here a little bit because there's quite a bit of text there. And initially I'm just going to zoom this out so you can see that you can look at it as one flat line. This is the human readable non-CSV mode. And this is what I used initially just to sort of glance at these different ranges. Now this simple command by default is dumping the range from 0.0 to 1.0 in tenths, where each range is 0.1 in size. So it dumps a range of 0.0 to 0.1. And 0.1 to 0.2, and 0.2 to 0.3, and so on and so forth. And for each of those ranges, of which there are 10, it dumps out information about how the 24-bit signed integer format and the 32-bit floating point format relate to the individual range of the line item. So for example, this first line, even if you can't see it, because I'm going to zoom in a second, I just want to highlight the first line. So this first line is for 0.0 to 0.1. And so it dumps information about the 24-bit and 32-bit floating point format for that range on this one line. And it does the same for 0.1 to 0.2 on the next line. Let me zoom in so we can look at that first line here a little bit closer. So this I24-bit size is the 24-bit signed integer resolution for the range. Let's come back to that in a second. It actually shows this resolution in hex and decimal, but we'll come back to it in a second. Same with this floating point size. This is the floating point resolution for this range. Let's come back to that in a second. Here's the 24-bit signed integer range in hexadecimal. You can see it's 000000 to hexadecimal 0C, CC, CD. And you see a colon, and then it's followed by a floating point value of 0.0 in scientific notation, so that's 0.0. And then I'm going to shrink this a little bit so we can see. That is showing 0.0 to 1.0. And let me just shrink that a little bit, or let me make it really big, actually, so it goes to the next line. We were looking here at the 24-bit range there, and here's the floating point range from this to this. So that, remember, this is scientific notation. We have EO1, so this is 1.0 times 10 to the negative 1. It's actually technically 1.0000, and these numbers, and so on and so forth, times 10 to the negative 1. But effectively, what we're talking about is 0.1. So this is 0.1 in float. So what we have seen here is a simple showing of the range in 24-bit and floating point. Now the range is reiterated in greater floating point detail. So you have the source, or the first part of the range, the start of the range, which is 0. That does not change from this earlier showing of the same. But after that, there's going to be all that detail about this particular start of range number. So it's going to show like sine 0 biased exponent 0. So we're at the very start value. So that's a subnormal range. But actually, since this is 0, I think it's technically not the subnormal range because it's a special case of being all zeros. So it's the number 0. And the mantissa, let me actually just resize this. The mantissa is 0. And then let me actually resize this again. And so here's the raw 32-bit floating point value for that start of range. And then they have the number 2 to indicate that this is the reiteration of the end of the range for this particular one single line of output. And in the parentheses, we have the detail about this start of range number. So I'm going to, sorry about that, I'm going to actually zoom out here so we can find that 2 line. And here's the 2 line with all that detail. Now I'm going to zoom in a little so we can see the tail end of that line has these values FLT start ink and FLT end ink. Let me see if I can get that. Sorry. And so we have at the end of each line this FLT start ink and FLT end ink. That's floating point start increment and floating point end increment. And what that is for the start of the range, if you increment the mantissa by 1, what is the delta between the start of the range and that 1 increment? And for the end of the range, what's the decrement of the end of the range minus 1 mantissa value? And because the granularity in floating point changes, this can allow you to assess what the precision is at the various points within the ranges that you're dumping out. Okay, now that we've gone over one line, rather than focus here on the command line, what I would like to do is actually create a CSV file, which we can look at in Excel, which will be much easier, and it has the same information. All right, so I'm going to recall the audioutil range simple command, and I'm going to add a -C for CSV. Now I'm going to hit enter, and you can output this to the console, and I'll just make this small for a quick second. And you can see there the headers are there. This is probably only valuable if you're going to copy paste from the terminal to, let's say, Excel, but we're going to output directly to a CSV. So I'm going to make this large again, and I'm going to type in clear with the terminal window clear. I'm going to recall our command line. I'm going to put a -C there and then -O, and we'll call this range symbol.csv. I'm going to hit enter. I'm going to type range and tab until I see range symbol.csv, and I'm going to hit enter. Now Excel is asking if I want to convert apparent scientific notation values into scientific notation, and I'm going to say, yeah, convert. I'm going to activate my so-called dark mode colors. Just give me a second. So I'm going to do Control A, select the paint can, go black there, go down here on the colors, and let's choose a bright green. I'm going to choose more borders. I'm going to say none. Go here and choose a color like this. Then I'm going to choose outline and inside and OK. And this is just a dark mode that I happen to like to use because it's easier on the eyes. I'm now going to click up here in the corner and double click between one of the columns, and that will do an auto fit. And I'm just going to make sure that auto fit didn't truncate a column at the end here. Nope, looks like everything's fitting on here. Now this is the same data that we just output with range simple on the command line. I love this much better. It's a great way to go down and look at the values. By the way, note that this is scientific notation and it's quite abbreviated by default. If I click on one of these numbers, you can see there's much more detail, much more precision that's available for these. So you could right click on a column like this, and let's say a column like that, and let me choose that column, and then this one over here, which is also a floating point, and I'm going to right click and choose format. I'm going to go to number, and why don't we just add, well, shoot, I'll add 9, and I'm going to click OK. Now, actually, it changed it to fixed point. I'm actually going to go back here and choose format. I'm going to go to scientific and keep it at 9 and click OK. And the reason why I'm doing that is with scientific notation, we can have a visual representation of how small a number actually is in the case of looking at these tables here. Another thing that I like to do is I'll select the entire table by clicking up here, and I probably should have done this first as I type in consolus. I would normally type in like 10, but I think since we're looking at this, I'm going to type in 12, which is quite large. After I change the font size, I click up here and I double click in between a column to do auto fit. And we can see it's kind of going off the edge there. I can actually shrink it down a little bit to bring it in, or I can bring this out a little bit. I think that's barely fitting there. Yeah, that looks good. Maybe what I can do is actually make it bigger for the demonstration right now. And so that's what I'll do is I'll make it bigger and we'll use the scroll bar. So when we were on the command line and we did range symbol, I said we were going to go back and talk about I24-bit size, and we didn't do it there, so we can do it now. First, let me say that this first line here is the line that we looked at on the command line, and you can see that the values are the same as what we saw on the command line. Now, this I24-bit size means that for this range, now this range on this first line here, this is going by tenths, so you can see this is 0. This is going from 0 to the end of which is 1.0 times 10 to the negative 1, or just more simply dot 1. So this is going from 0.0 to 0.1, and this is going from 0.1 to 0.2, and so on and so forth, all the way up to 1.0. Now you'll notice the endpoint here is 0.99999, etc., and that's because it's clamped here because the highest 24-bit value is 7ffffff. That's due to the tooth complement anomaly we've discussed quite a bit. And so there's the number in floating point that's just shy of 1.0, but depending on the context, we can effectively think of that as plus 1.0. So basically we have 10 tenths, and that's what we're representing here. We're breaking down 0.0 to 1.0 in 10 sections. And then we're able to look at how the 24-bit format views each of those 10 sections and how the floating point format views each of those 10 sections. And one of the things you can look at is the resolution of the format for each section. So you notice that fairly consistently, the 24-bit format has the same resolution for each of those sections. Now, depending on whatever rounding errors or things that are run into when calculating everything, there might be a slight difference here depending on the nature of how the table is created. So the way I created it, it largely has this value for all of them. There's a case here where it's off by 1 compared to the other rows. And basically I'm adding a tenth for each one, so the quantization error was slightly different for that line. Likewise, you can see here it's slightly different for that line as well, probably due to the clamping. I've gone over these before, so I'm fairly certain everything's okay, because when I see things like that, I kind of go over them. But there are a number of different ways that these calculations can be approached, including the rounding method that's used. And so depending on a number of choices, there can be slight variances in subtleties that different applications might observe depending on their approach. And console us, and there we go. Let's click up here and double click on one of the bars here. So we can see there's about 838,861 values for each of those sections with 24-bit integer. And it's largely static for each section. And that's because the 24-bit format is linear in nature, and so it divides itself up evenly across that range of 0.0 to 1.0. And of course, as we've discussed, it has no representation beyond 1.0. And of course, it can represent the negative range from 0.0 to negative 1.0, but it has no representation below negative 1.0, of course. In contrast to that, if we look at the floating point resolution for those different sections, we see something quite different. We see a large amount of resolution for this first range. This first range includes the subnormal range. That's the range where the mantissa will not have that implicit binary point, 1 point prefixed onto it. That's for biased exponent 0. And so for the value range 0.0 to 0.1, which is that first tenth of the entire range we're looking at, we see there's quite a bit of a magnitude or bit space, if you will, sort of dedicated by the 32-bit float format to that particular range. To be really clear, our segmenting these in tenths from 0.0 to 0.1 to 0.1 to 0.2 in tenths and dividing it into 10 sections is a very human thing that I chose to do. So I'm human and I use the decimal system, and so I understand tenths of a point. So if I want to count from 0.0 to 10 in 10 steps, I'm using tenths: 0.0, 0.1, 0.2, 0.3. So I'm dividing up the range in this kind of human division that I'm used to. And then I'm asking a question based on the data of these tables. How are each of these sections that I understand as a human represented by these different formats? And we're seeing the linear format is pretty static across all the sections in terms of its resolution, whereas the floating point format starts off with this whopping really large amount of resolution for this low end. And then if we go one step up, this is 0.1 to 0.2, we see it has a resolution of about 8.4 million. And while there's kind of a logarithmic change here, if you will, it never quite diminishes to the point which is equal to 24-bit. So even as it gets closer to 1.0, it exceeds 24 bits resolution, and it exceeds it quite significantly. So throughout this entire range, a lot more detail can be maintained in theory. Now, of course, there's a lot of things relating to what we're talking about, what you're recording, and we're not going to get into those details now, but suffice to say, there's a lot of space there. And especially closer to the lower end, there's a lot of room to capture detail there. And given the way floating point numbers scale very elegantly, assuming you can record your low levels and maintain them, and maybe even things not so low, as long as noise is mitigated in a reasonable, or if not most optimum manner, if detail can be captured and kept in that format, there's just really plenty of detail space here as needed. So that's one of the big things you can see here from the spreadsheet, is just the difference in how each range can be represented in terms of just the fundamental or basic resolution of both formats and how that's allocated to these different areas of that 0.0 to 1.0 range. Now, floating point has a lot of space above 1.0. So to the extent it has the ADCs or whatever to capture a broad dynamic range, the floating point space is incredible for representing that. There's plenty of room there. And to the extent that such a dynamic range has a so-called normal area below 0 dBFS and an area above a so-called clipping point, it might actually even be helpful to think of that as a non-clipping point, really, but just something above what has once been called a clipping point. But really, we're talking about a range of values relative to some, let's say, lowest value, which we might say is negative infinity or silence, and then stuff leading up to some maximum that our audio system that's capturing audio can support. So you can imagine, in theory, if you have multiple ADCs, or if one day they create fantastic super duper ADCs, which just by themselves, capture a huge broad dynamic range. I mean, it doesn't really matter to differentiate between these now. I mean, if we think about today's components, maybe that does matter. Well, it does. But what I'm trying to say is, if you have an audio system, regardless of its components, regardless of ADCs or construction or whatnot, that is capturing high quality audio across a broad dynamic range, that's the most important thing to be able to do. If that can be done, then the 32-bit floating point format can be used to hold that information quite effectively. So going back to this, another interesting point to look at is you can see for this first line, there's a huge number of exponents that cover this one first range of 0.0 to 0.1. in decimal. So we have quite a number of exponents being used. And then we have the straggler remaining exponents leading up to 1.0. Pretty much that's 123, 124, 125, and 126, representing the remaining of values. So again, this is to accentuate there's quite a bit of room here, not to say that there isn't quite a bit of room here for a lot of detail. And floating point, of course, has a lot of room up here for stuff that goes above 0 dBFS. Okay, so if we scroll over here, let me just see. If we scroll over, now, by the way, these things will say start, and then they will say end for the end of the section. So you can see the end values right here at F32 end. All this stuff is just pretty much the ending values. And they're in columnar format, where the other one had sort of a human readable line format. Another thing which might be interesting to look at is if you look at the increment here at the start of that first range. So that's right near 0. So in that subnormal range of 0, going to the first mantissa point, we have a distance of 1.40 blah, blah, blah times 10 to the negative 45. It's a really small number. So the increment, to that one mantissa point is very tiny. And then if we look at the end of that range, and remember, a lot of exponents get used for that, range there from 0.0 to 0.1. If we look at the end inc, and the end inc is going to be the high end of the range, which is 1.0 minus one mantissa point. And you can see it's 7.45 times 10 to the negative 9. Now compare that 10 to the negative 45 versus 10 to the negative 9, and there's a huge difference. So basically, an increment of the mantissa at the end of that range is significantly larger than an increment of the mantissa at the lower end of the range. But even though it's much larger, its precision is still very fine-grained. It's a very small increment still. And even if you look at the end increment as you get to these higher values near 1.0, they are quite small. If I start up a calculator here and I type in 1 divided by 2 to the 23, we come out with our linear increment of the 24-bit format. Now let me save that. If I take the largest one from the end ink here, 5.9604644. Actually, you know what we can do? I think this will let me paste this in here. Does it? No, shoot. Let me try bringing up Notepad here and pasting this in. I believe if I make this E small and then I go over to calculator, it should let me paste it in. Yeah, now it does. So if I hit enter, we now have the value and it converts it to a fixed format here. So I know it's accepted that number. Now what I'm going to do is I'm going to take this number, which is smaller than the linear increment of the 24-bit integer format. I'm going to recall that increment here, and I'm going to divide that by the floating point increment. And we see that that highest increment of the range there, so this is at the high end of 1.0, the end of that range there. That's this number here, 5.96 times 10 to the negative 8. We see that that's about 2 times smaller than that linear increment that's applied to the entire 24-bit range. So I'm going to close calculator and close Notepad. So one of the things you could kind of do with a spreadsheet like this, and I kind of played around with things like this, is you could, for example, you could say, well, here, let me see if is POW. I think it's POW, right? Power, and then it's say 2 to the 23. Terrific. And I'm just going to put these in here. And we'll call this I24 max. Over here, I'm going to say I24 increment, and I'm going to say, actually, this will be 1 divided by that. And so now we have, let me move the scroll bar over, and we'll populate all of those. Okay, what's going on? Cancel. Okay. And now I'm going to double click there. And now I want to look at the ratio of the 24-bit linear increment to the floating point increment at the different sections. And we can call this I24 inc to F32 inc, something like that. And then what I want to do is I want to divide the much larger 24-bit increment, which is linear and non-changing, and I'm going to divide that by the smaller float increment. But it's smaller at these lower ranges. And so I'm just curious to see if I do this and double click here, we can see it's about 16 times more precision there in this first range approximately, because the range has a lot of variance within it. And so we're just looking at this n value. So we know at the end there's this ratio or a comparison of the two. And then it goes down to 8 times, 4 times, and then 2 times, which is what we observed in our earlier calculation. Anyway, that's enough for this simple spreadsheet. I just wanted to show you just generally what it's about and how you can go in and toy around with the values. So I'm going to go ahead and close Excel, and we don't need to save this. I'll say don't save, and I'm going to clear our terminal window. So one thing you can do with audio range simple is you can say, like, for example, -i.05 to increment by 0.5, which is basically going to divide up the 0.0 to 1.0 range into 2 sections, each 1.5 in size. I never really used that because I just looked at things in terms of tenths. I like to see the section divided up into 10 parts, but I just wanted to mention that. You also can choose to increment. There's ink type, so you can say ink type, and you can increment. The default is float, and that's the one that we looked at. And let me actually clear the window here. And we'll look at ink type float, and I can just make that. This is the same thing we just looked at. Okay, so if I clear this window and I look at ink type exponent, it will increment by exponent from 0 to 127, basically from 0 to 1.0, but by incrementing exponents instead of incrementing by 0.1 in float. Those are 2 different ways of incrementing through that same range of 0.0 to 1.0. So that was an initial thing I used early on, but then I created this detailed range thing here, which is detailed right here. And that's the one I'm going to focus on right now instead of looking at the range symbol with the ink type of BX. So let's start and look at range detailed. So for range detail, I'm just going to type in audioutil, range detailed, and hit enter. Now I cleared my terminal window so I can easily scroll to the top here. Now, like range symbol, this goes from 0.0 to 1.0. And it basically goes from biased exponent 0 all the way to biased exponent 127. So basically with the detailed output, it has the ranges divided by increments of biased exponent. So this first one is entirely about biased exponent 0. Biased exponent 0, or which is exponent negative 126. This is the subnormal range. And for each such biased exponent range, if you will, and let's just say the biased exponent range is the biased exponent itself, we're dealing only with the positive sign. And so we're talking about a mantissa that's all zeros to a mantissa that's 7F, FF, FF, the maximum mantissa. So this one is mantissa 0, and this one is mantissa 7F, FF, FF. These ones in here are just extra values that help us look at how the increment is changing, or the precision. So this low end plus one is basically the mantissa with a 1 here, with 1 added. So this one is 0, this one has a 1. Likewise, at the high end, this is high end minus 1. So it's basically a mantissa 7F, FF, FF minus 1, which is 7F, FF, FE. What you can do is you can look at the difference between those two values, or you can take these values and put them in a calculator and look at what the difference is of those two values, the delta between them. That delta would be similar to the increment that we were just looking at before. Generally, I don't use this detailed output from the terminal window. So let's clear the window. Let's recall that command line and add a -C to create a CSV named range detailed.csv. That's going to be the output CSV file. So I'm going to hit enter, and then I'm going to type in the CSV name, tab, and I'll hit enter, and that will start Excel up. Excel starts up and it wants to convert, and I will tell it yes, convert. Now this is too dark for me, so I'm going to put it in my own custom sort of dark mode by changing the colors. Control A, and let's choose a black background. Let's choose a bright green for the font. Let's go and add some borders here, and I'm going to say none, gray, and then I'll choose outline and inside and click OK. And there we go. Now I'm going to select all, Control AA, Consolus, enter, click up here and double click here to auto size. Now I'm going to select the second row, and I'm going to go to the view menu and choose freeze top row. Now the top row is frozen, so when I scroll, those headers remain there. Now this is the same data that we saw in the detailed output in the terminal window, except it's in a nice table here in Excel. Now each line corresponds to a range that's defined by the exponent itself. So you can see this is the low end here. This is the low end exponent, and you can see it starts at 0 and it increments all the way up here to 127. Let's scroll back up to the top here. So this line right here represents the range with biased exponent 0, with mantissa going from 0 to 7F, FF, FF, which is the highest mantissa value. We're only dealing with the positive sign, so there's no need to worry about sign. And so the same thing happens with the next line. This next line is a range that's defined by biased exponent 1. And that's from the lowest mantissa, which is 0, to the highest mantissa, which is 7F, FF, FF. And so let's take this first line. This first line is for biased exponent 0. That actually happens to be the subnormal range. But what I mentioned here will apply to all the other ranges as well, pretty much. And so the low end biased exponent is 0. The low end mantissa is 0. The low end 24-bit value is 0. That means in the 24-bit assigned integer format, what is equivalent to the lowest of the floating point value that's at the low end of this biased exponent? And you can see for the 24-bit format, this is 0. In fact, it's 0 for all of these until it gets to this biased exponent down here. We'll come back to that in a second. Let's continue on to the next column. This is the low end 24-bit in hex. So that's pretty straightforward. Now this is low n plus 1. Well, low n plus 1 is the same as low n, but the mantissa bit has been incremented by 1. Let's skip the scientific notation right now and just go over to low n plus 1 mantissa. And you can see that low n plus 1 mantissa is pretty much 1 for all of these. Because when we're incrementing by biased exponent, the low n mantissa, which is right here, is always 0. And so 0 plus 1 is always going to be 1. And so if we scroll on over here, let me just go quite a bit over here. This is low n plus 1. Then we'll get to the high n minus 1. Where is that? Here's high n minus 1 mantissa. So you can see that the high end minus 1 mantissa is 8388606. Now recall, let me bring up my calculator. The mantissa is 23 bits, right? So if you have 2 to the 23, that's 8388608. Now, if I go to the programmer's calculator and I type that in, it's 800,000 hex. We subtract 1 from that. That's the maximum value that 23 bits can represent in terms of a raw representation of a value, because that's 23 bits all set to 1. So basically, we clamp that positive side down to 7F, FF, FF. Quick insert and voiceover here, folks. I just want to clarify that the 7F, FF, FF that we're arriving at here is not related directly to the 2's complement anomaly we've discussed with 24-bit signed integer. In this particular case, we're referring to a 23-bit value that we refer to as the mantissa, just focusing on that one value alone without respect to the rest of the 32-bit floating point value. We basically look at the mantissa as this value that has 23 bits. And if we want to figure out the maximum number that can fit into those 23 bits, we basically raise 2 to the power of 23. 23 is for 23 bits. And then we subtract 1 from that value. And you can do that basically with any number of binary bits. So if you want to get the total number of values that you can fit into a byte, that would be 2 to the 8. One byte has 8 bits, so that would be 2 to the 8. That's the total number of values that can fit into a byte from 0 to 255. If you want to get the maximum value that can fit into a byte, it's 2 to the number of bits, which would be 8 bits in this case. So that's 2 to the 8, which is 256. And then you subtract 1 from that. So it's 2 to the number of bits minus 1 gives you the maximum value that you can fit into a byte. And we're just applying the same thing here to arrive at the largest mantissa value. The mantissa is 23 bits. As a 23-bit value, it can hold up to 2 to the 23 different values, ranging from 0 to 7F, FF, FF. If we want to figure out the maximum value, that would be 2 to the 23 minus 1. And that gives us 7F, FF, FF. We're not clamping down to 7F, FF, FF here in this case for the sake of the 2's complement anomaly. We're just simply trying to figure out the maximum value that can fit into 23 bits. Okay, with all that said, let's get back to the regular video. So going back over here, this should therefore look familiar. It's 8388606. Well, we can clearly see if we go back here, 2 to the 23 is 8388608. Well, we subtract 1. That's the highest value that you can represent in terms of a raw value. That's equivalent to 7F, FF, FF. So what's 1 less than the maximum? Well, that would be 7F, FF, FE. Or if I subtract 1 from here, that's 8388606. And that's what we see here. If I actually insert a column here, I can call this high-end mantissa, hex. Let me do that. Des to hex. And hit enter. And there we go. So we can see that this high-n minus 1 mantissa is always 7F, FF, FE. So if we go to the high-end mantissa, we're expecting that's going to be 7F, FF, FF, or as we know, it's 8388607 because 2 to the 23 is 8388608. And we know we have to subtract 1 from that. We can't really represent 8388608 in 23 bits. So we could do a similar thing here. We could insert a column here and I could say high-end mantissa. mantissa hex. And you could say equals des2hex and hit enter. And you can see that these are all 7F, FF, FF. So the point being is our ranges for each of these lines is pretty much the biased exponent from mantissa 0 to mantissa 7F, FF, FF. However, we're including some extra data in here, which is that low end value plus 1 mantissa bit and the high end value minus 1 mantissa bit. So don't let that plus 1 and minus 1 confuse you. It's just more data that was added, so it would be easy to glance at what the increment was for each of these biased exponents. As we go through each line in here, the distance between the two values, the low end value and the low end value plus 1, will increase as the range increases as we go to higher biased exponents. All right, let's go back over here to where the biased exponent is. So recall that this is the low end biased exponent. So each row represents a range starting from the lowest end of a particular biased exponent, or we could just say exponent, to the highest end of the same biased exponent, or exponent. And so the goal here is to display various values relating to that particular range. And we have one such range for every biased exponent from 0, and as we scroll down here, this column D right here, all the way through to 127. Now I'm scrolling back up to the top here, and for each biased exponent that's represented by a row, the low end is also shown in scientific notation here. And there's also the same for the high end. We're just focusing on the low end here. But for the low end and the high end, so that's row D, and then let's go to the high end biased exponent here just to make this point clear here. The high end biased exponent, which, where is the high end biased exponent? So here's the high end biased exponent. So notice the high end biased exponent matches what the low end would be, right? And the low end is not visible on the screen right now, but notice this just counts up to 127, just like the low end did. And why is that? Well, this is very simple. Each row is associated with one and only one biased exponent or exponent. And what we're interested in is the range of 24-bit values and the range of floating point values for any given biased exponent. So what we're doing is just focusing on the low end, and all I'm trying to point out is that this low end biased exponent is the same as the high end because each row is associated with one and only one biased exponent, and there's one row for each biased exponent from 0 through to 127. Okay, so now we should be clear that each row is relating to one and only one biased exponent, and that biased exponent defines the range of values any one row in this table is discussing or pointing out or defining or showing us values relating to. And that range begins at the positive 32-bit floating point value that has the biased exponent in question with a mantissa of 0. And the high end is the same 32-bit value with the mantissa bits all set. So that's 7F, FF, FF. And this column A contains the floating point value for the low end of the range. And the low end 24-bit column contains the equivalent 24-bit value for the low end of the range of any given row. Notice how the low end floating point value has detail here, lots of detail and precision. Just generally speaking, from a fuzzy standpoint, when you view it, you see numbers that are changing and you see exponents here that are changing. Contrast that with the low end 24-bit column here, which is all zeros until, and I'll scroll down here, you get down here to row 105 here. Row 105 is the first row where you see a non-zero value. Now the question is, why is that the case? Well, remember there are far fewer values in the 24-bit signed integer format than there are in the floating point format. Additionally, for the values that are available in the 32-bit floating point format, there is much more flexibility to express a much larger range than one would with a linear format such as 24-bit signed integer. 24-bit signed integer performs a very simplistic translation from floating point values to the 24-bit format and back again. If you're going from a floating point value to a 24-bit signed integer value, as we discussed earlier in in the video, you're going to be using the floating point value you're coming from as a ratio against the maximum 24-bit signed integer value in order to determine what value is related to that 24-bit signed integer range. The caveat here is that for floating point values that are 1.0 or higher, the 24-bit signed integer value is clamped down and limited to 7f, ff, because it has no headroom, no value space above that maximum. That maximum represents like 0.99999, something like that. It's effectively the 1.0 for 24-bit signed integer. It's as close as you'll get to 1.0 in that format. Now, let me start up the calculator here and make a really simple point that has already been made in the prior portions of this video, but this should be a good clarifying point. Let's take 1 here, and let's say that this is 1.0 in floating point. Now, let's divide 1.0 in floating point by 2 to the 23. Remember, 2 to the 23 is effectively the maximum 24-bit signed integer value to either the positive or the negative side. Even though the positive side can't go as high as 2 to the 23 given the 2's complement anomaly, we still use that in our calculations. We just clamp down on that top value to ensure it's never above 7f, ff. This gives symmetry to the calculations on both sides and keeps things simple. Now, I'm not saying you won't run into some context where something is doing something differently, but this is what we're doing here. So by dividing 1 by 2 to the 23, which is the maximum number of different 24-bit signed integer values you can represent on either the positive side or the negative side. So each side has that many different values which it can represent from 0 to 2 to the 23, with the caveat that the positive side can't go quite as high to 2 to the 23. And when we go to 2 to the 23 on the negative side, it is negative. So it's negative 2 to the 23. So given that, if we divide 1 by 2 to the 23, we're going to get the floating point value that each count in a 24-bit signed integer represents in the total floating point value it expresses. So for example, this number you see here, 0.00000119209, etc., that value is the floating point value that 1, positive 1, and 24-bit signed integer equals in floating point. So if you were to say 24-bit signed integer 1, what is that in floating point? You would say it is equal to this. What would 2 in 24-bit signed integer be equal to? It's quite simple. If this is 1, then 2 is going to be times 2 of that number. And we hit enter, and that's the floating point value that 2 is equal to in 24-bit signed integer. So you have 24-bit signed integer, and if it's a value of 2, then this is what it actually really equals in terms of amplitude levels or a floating point level in the way that we convert floating point or signal values, floating point values, to 24-bit signed integer. So this should all just be a recap of the prior material covered. But I'm trying to be very specific here because it's kind of bringing it sort of all together in a certain way. So hopefully this is helpful. So another way to express this, by the way, might be, and I'm just going to elaborate on this, to say 1 divided by 2 to the 23 times, and then whatever your 24-bit signed integer value is. So if the signed integer value is, let's take the maximum that can be represented, 8388607 on the positive side. Remember, 7f, ff is what's used as the max on that side because we can't go one more because of 2's complement. So 8388607 is 7f, ff, and if I multiply 1 divided by 2 to the 23, which will equal the floating point value that each count in the 24-bit signed integer format has or contributes towards its overall floating point value that it ultimately represents. If I take that value and multiply it times that max, we're going to get that 0.99999, value. So let's hit enter. And sure enough, that's what we get. That's actually like saying 1 divided by 2 to the 23 times times 2 to the 23 minus 1, it ends up being the same thing. So because that's what we just did just now. The whole point here is that the way I like to look at it is, and this is not to knock the 24-bit format, signed integer format, but I try to look at it like this. Each count in the 24-bit signed integer format contributes this value that we calculate with 1 divided by 2 to the 23. If you look at the increments that in the floating point system that you have when you can go from one value to another, the precision is much finer. The values you can increment in floating point are much finer, much smaller. Plus, the 32-bit floating point format uses its total value range, or bit space, if you will, in sort of a logarithmic fashion, which means it distributes the values that it can express more broadly, so you can express much higher and much smaller numbers. Okay, now, recall when we talked about quantization error, there's an effort through the use of rounding to minimize quantization error. So if you think about it like this, let's say the 24-bit system can represent a floating point value here and a floating point value here, where the float system can represent one here, 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 here. So you have these two possible 24-bit integer values that can be chosen, and you have like a floating point value here. Which is the better integer to be chosen in the conversion? And obviously it's going to be the closer integer, because basically either integer is going to lead to a loss in precision. The floating point value has a relatively more precise notion of what the amplitude is at a given point in time. And if you have to convert that to a 24-bit format, you're losing some of that precision. Whatever the actual amplitude is getting lost to some degree in that conversion process. So if you're right in the middle of two integer values and there's a floating point value right in the middle, it'll use whatever rounding is being used, and there's a couple of different rounding approaches that are used. But if it's not a tie in rounding, it's a little bit closer to this integer, it will go to this integer. If it's a little above and closer to that integer, it'll go to that integer. And generally what we can do here is we can say 2 to the 23. That's our max 24-bit signed integer value, right? Now let's take that value again, as we've been doing a couple times here, and let's take 1, which is 1 in floating point, and divide it by 2 to the 23. Now this is our minimum floating point increment value in that 24-bit signed integer format. That means if we have those two signed integer potentials that I just mentioned, the distance from this one to this one in floating point, if you will, even though these are not floating point numbers, they represent them effectively given the rules we come up with to say, we're going to say that every 24-bit signed integer value is representing some value within the span of 0.0 to 1.0. So if you have two 24-bit signed integers side by side, then the distance between them in floating point is going to be 1 divided by 2 to the 23, or 0.000000, I think, 6 zeros, 119, and so on. If you have a floating point value that's right in the mid, that's closer to this one, let's say, it's going to choose this, right? If you have one that's in the middle, it'll use rounding. And if there's one that's above, it'll go to the higher integer up here. And this is conversion from float to integer. One thing we can do is we can take the amount of floating point value that each step in the 24-bit signed integer format contributes to the overall floating point value, which is this value we have here, which is 1 divided by 2 to the 23. And if we just simply say divide that by 2, and when we split that in 2, we become knowledgeable of what that middle point is that could be a deciding factor. If a floating point value is below that value, then the equivalent 24-bit signed integer value will be 0. Because remember, the one that we just divided by 2, that's equivalent to 1 in 24-bit signed integer. So if we take that floating point value that equals 1 in 24-bit signed integer and we divide it by 2, we're midway between 0 in 24-bit signed integer and 1 in in 24-bit signed integer. So if we're a little bit below that midpoint, it's going to round down, and the floating point values in this area will convert to 24-bit signed integer 0. If they're above that midpoint, conversion will assign those floating point values to the number 1 in 24-bit signed integer. And so therefore, when we see this 1 appear here, what it kind of hints to us is that at the biased exponent of 103, which is actually the exponent that is 103 minus 127, which is negative 24 is the actual exponent. But let's not worry about that right now. Let's just stick with the biased exponent of 103. That's where we begin to see a non-zero 24-bit signed integer value. And so what we know is within the range defined by that biased exponent is the beginning of a floating point value range that's greater than 1/2 of the floating point value that a single count in the 24-bit signed integer format represents, or that number that we just calculated, which is 1 divided by 2 to the 23 divided by 2. So this biased exponent must include in its range something that goes to this point or higher. It also implies everything below that point is below this value. So if we go back to the spreadsheet here, let's go look at what the low end floating point value is. That could be of interest. Oh my goodness, what do we see here? Well, we see 596 times 10 to the negative 8. Or if we look up here in the bar up here, we see that Excel put a fixed point number there, which is 0.0. I'm going to count the zeros first. 1, 2, 3, 4, 5, 6, 7, and then there's one digit there, 5, 8. That's the 10 to the negative 8 that I was just mentioning. So that's 5.96 times 10 to the negative 8, or 0.0000000596, etc., etc. Okay, let's go. I hit escape just now in Excel to end my focus from the formula bar there. Let's go back to the calculator here and notice what we have here with this 1 divided by 2 to the 23 divided by 2. We have 0.00000000596, etc., etc. So there's 1, 2, 3, 4, 5, 6, 7. And then the digit, that's our 10 to the negative 8, right? 5.96 times 10 to the negative 8. And I think I counted 7 zeros in here, right? 1, 2, 3, 4, 5, 6, 7. So basically, the floating point values in the range for this line, which relates to this biased exponent, includes values that are at or above that quantization center point, which is 1 divided by 2 to the 23 divided by 2. Sometimes they might refer to this in ADC speak as 1/2 LSB, but that's just a whole other world, so let's just stick with this. Now, when it comes to rounding, if you have a tie, so you're right in the center, that depends on rounding. I've chosen relatively simple rounding. Rounding is a topic that we can touch on later, but right now that's not our primary concern. What we see here is that these two biased exponents have a low value that is 1. What that tells us is this begins to go above that midpoint of the quantization error center point, 1 divided by 2 to the 23 divided by 2, or that 5.96 times 10 to the negative 8 number, right? This number right over here. So this range goes at least above that. It doesn't seem that this range exceeds the halfway point for the next up step in the 24-bit floating point format, because we can see that down here on the next row, the low end is also 1 in 24-bit floating point. So if we go to the end of this row, though, I bet you the high end. So here's the high end. You can see that the high end actually for the prior row, that's the row where we first start to see non-zero 24-bit signed integer numbers. That's where we see our first 1. You can see that the high end for this is 1.19 times 10 to the negative 7. Or if you look up here, you can see it's this 119,209, etc. number. And interestingly, if you go in here and divide 1 by 2 to the negative 23 and just hit enter, that's the floating point value that each step adds to the overall floating point value represented or expressed by a 24-bit signed integer value. So the number 1 in 24-bit signed integer is equal to this. The number 2 would be equal to 2 times that. The number 3 would be 3 times that, and so on. So you can see that the high end here is roughly equivalent to that value that a single step in the 24-bit signed integer space is equivalent to. Now, if we go to the beginning of the row, again, this is the first row where we see a non-zero 24-bit signed integer value as the low end. That carries over to be the low end for this row. And if we go to the high end here, let's see what the high end integer is. And the high end 24-bit integer here is 2. So it moves to 2 within this single row's biased exponent range, if you will. And then that carries over to here. So the first one was inclusive of the 24-bit signed integer value 1. The next one was inclusive of a switch or a changeover from 1 to 2. And the next one goes from 2 to 4. And you can kind of see that they're increasing here. And you can kind of see a pattern here with that increase. And so the interesting thing about this, and this was in one of the graphs that, was shown earlier in the video, is that this entire range here, if you will, aside from the number 0, is the value space that can be expressed or represented by the 24-bit signed integer format. That it really has no detail for values lower than that. And that's just kind of interesting. It doesn't mean that it's a bad format. It just means that the linear nature of it and the way that you would distribute that or relate it or compare it to the floating point format is kind of skewed to the high end in a sense. Or another way to look at it is that the floating point format has a lot more detail it can express on the low end. And I just thought this was interesting. Now, there's a lot of things you can look at with this particular audioutil detailed range spreadsheet, but we'll leave it here. I think aside from just showing you the general format of the table, this was like one of the examples that I wanted to show. Okay, that's it. Let's go to the next section. There are plenty of videos on root mean square or RMS. So here's a quick intro or refresher depending on where you're coming from, whether you have experience with RMS or not. And of course, if you have experience with RMS and you don't want a refresher, feel free to skip this section. In fact, regardless of your experience of RMS, you don't really need to have knowledge of RMS to continue with this section. So you can skip the intro to RMS if you're not interested. First, a quick clarification regarding the use of the term or phrase audio samples within this RMS introduction section. When we refer to audio samples, we're referring to floating point audio samples. If you wonder whether this excludes 24-bit signed integer audio, no, it definitely does not. It simply means we assume that if you're talking about 24-bit signed integer audio samples, that they have been converted into floating point before calculating the RMS of those samples. You should know by now from the past sections that really, effectively speaking, all audio samples are effectively floating point samples. Now, even though their format might be integer, like in the case of 24-bit audio, each 24-bit signed integer value is equated with a particular floating point value. And those values for 24-bit signed integer exist between 0 and 1.0. That value between 0 and 1.0 is a ratio to full scale, where 1.0 is 0 dBFS, or the clipping point in a digital audio system. 32-bit floating point samples have headroom to represent samples above 1.0, so have a larger dynamic range. But really, what I'm trying to say here is it doesn't matter which audio sample format we're talking about. For the sake of this discussion, when we talk about them in this section, we're assuming they've been converted to floating point for the sake of discussing what we do with them in this section. It just keeps things very simple, and I just wanted to state that up front so I don't qualify it multiple times within this section. Okay, let's move forward. RMS stands for root mean square. You can think of the three words root, mean, and square as three different functions, each having the name that I just mentioned, root, mean, and square. So these three functions are sort of nested, where the innermost function is square, the middle function that wraps square is mean, and the outermost function, root wraps mean and square. So you basically have square where you pass the audio samples, for example, to the square function, which will square all those audio samples, and then you pass the result of that, which is all the audio samples squared, to the mean function, or the average function. You can think of it as the average function. And that mean function or average function will calculate the average of all those squared audio samples. And after doing that, it'll take that average of all those squared audio samples and it'll pass it to the quote-unquote root function, which you can think of as the SQRT or square root function. Its job is to calculate the square root of that average of all those squared audio samples. But the whole point here is to just express very simply at a high level, root mean square is not some big complex thing. It's essentially three math functions which probably are familiar to most folks. You're calculating the square of the number of values you wish to calculate the RMS of. You take the result of squaring all those values and you pass it to a mean function, which calculates the average of all those squared values. And then you calculate the square root of that average. Or in terms of audio samples, RMS calculates the square root of the average of all the audio samples raised to the power of 2. Fairly straightforward. In a nutshell, that's root mean square. The benefit of doing that with respect to audio, well, let's just say that there's a lot going on with that simplicity, and that's what we're really going to highlight in this section. So an RMS average of an audio signal not only averages the signal's amplitude level, but more so. It averages what the signal's contribution to power will be when it's played back. And that also happens to be one way in which you can get an estimate of what the signal's loudness will be on average when it's played back. This method of averaging loudness relates to RMS. It's not the only way, but it's a way, and it's one that has been used for many, many years in audio. So you might be wondering, isn't LUFS, L-U-F-S, supposed to be for loudness, and what's this RMS thing? Well, those are good things to wonder. There are indeed numerous ways human beings can measure and average loudness of a signal. LUFS or LUFS being one, and RMS being another. RMS, which has been used in audio for over 50 years, is used to calculate a signal's average contribution to power using a relatively simple formula. And that average offers a basic measure of the signal's contribution to energy or power. And that contribution to power or energy is considered a reasonably good general indication of loudness as perceived by humans. LUFS is a more recent 21st century development which provides a more nuanced, more accurate, more detailed, if you will, oriented measure of a signal's perceived loudness by specifically accounting for how humans actually hear. It's more nuanced and more complex, and therefore it's more involved to calculate properly. Other than this brief mention, we're not going to get into the details of LUFS and calculating LUFS here. And while RMS is less sophisticated than LUFS, it is simpler. I mean, as you saw, it was 3 functions and we went over it fairly quickly. So it's very easy to implement. I mean, if you have a spreadsheet, you can actually put functions together to calculate it very easily. You can't really do that with LUFS because there's a lot more involved. So RMS has been around for much longer. It's simpler, it's familiar, and it provides a reasonably good average of a signal's loudness and its average power. Or in the case of audio signals, it provides a reasonably good average of what a signal's contribution to power will eventually be at the time it's played back, and therefore an average of what its loudness will be when it's played back. And it's important to note that when it comes to RMS and LUFS, you will find differing opinions out there. Different people have different systems. Some people use RMS, some people use LUFS. Most people probably use both here and there depending. So you can find a lot of opinions out there and whatnot. We're not going to argue the merits of one or the other here. RMS is used a lot for comparing signals, including comparing noise floors, calculating signal-to-noise ratios, and other tasks. And that's kind of our focus of discussion here. Coming up later in this video, I'll be using RMS-based values, and so that's one of the main reasons why I'm going over this here, is because it's related to some of the content later, not really to say anything about LUFS. It's just not a focus right now. So you might ask, what's all the hoopla about? Why do all this root mean square? Why not just calculate calculate the normal everyday average on all the audio samples, right? You have a bunch of audio samples, just calculate their average like you normally would. Add them all up and then divide them by the number of samples. Boom, done, right? Well, that's a great question, and it's best answered visually. Let's bring 3 AC waveforms in here so that we can compare and discuss them. Let's say that these graphs represent 3 different audio signals. We have mostly looked at graphs that go from the range of negative 1.0 to positive 1.0. These graphs you see here are using a larger range. We're doing that to limit the use of fractional values and to make the points of this discussion very clear. So don't get thrown by the different range here and the larger range of numbers. Any value range for an AC signal going from negative to positive will work for everything that we discuss here. It's the notion that it's an AC signal which fluctuates between positive and negative values. Remember that positive and negative audio samples are directly related to positive and negative voltages as sampled by the ADC. For this discussion, you can assume these graphs represent, let's say, voltage levels of 3 different audio signals. Now, the voltage levels here are a little high, but again, it doesn't matter. As long as we have an AC signal with values that fluctuate between positive and negative, you can make the same observations we're going to discuss here. By using these larger whole numbers, it's going to really simplify this discussion, and I hope you find it helpful and understand my rationale for doing it this way. You can see on each of these graphs there are several dots which appear on the waveform, and each of those is annotated with a value. That value is the y-axis value, and we would generally refer to that as the amplitude level. Let's say that each of those is a sample of the AC signal represented by the graph itself. So we can see that each of these graphs have 4 samples represented. 2 of them are negative and 2 of them are positive. It's negative, positive, negative, positive. Now there's no need for us to deal with tons of samples. Again, as long as you're dealing with an AC signal, even with a few samples, you'll be able to make the same observations, and you'll know exactly what I'm talking about after you see what we discuss here. So looking at each of these graphs, we have the following samples. In the first graph, we have negative 3, positive 9, negative 2, positive 8. In the next graph, we have negative 2, positive 14, negative 4, positive 4. And the last graph, we have negative 5, positive 27, negative 15, positive 5. Now, each of those values that we read for each of the graphs, we'll call those the set of samples for each of the graphs. Now let's take the set of samples for each of these graphs and let's calculate the normal everyday average. Not the RMS, but the everyday average. Oh wow, 3 different audio waveforms, and the average of all the samples captured comes out to 3 for each one of them. Each one has the same average, so they must be equal on average, correct? Well, obviously not based on how we introduced this section. Well, offhand, maybe they are, the same. We haven't proven that they aren't. I mean, if we look at them visually, the one on the right certainly looks like it has, a significant amount of more amplitude or power than the one on the left. So assuming they're all scaled identically, it sure seems like there's a difference with these audio signals, and we're not seeing that difference when we calculate a normal everyday average on the samples. I mean, if you look at the third graph, it goes as high as 27, and I mean, it just seems obvious it has larger amplitude values. And unless each graph isn't on the same scale or something certainly seems larger, at least in the third one compared to the other two, but frankly, the one in the middle looks larger than the one that's on the left. Okay, well, I tell you what, let's look at another set of 3 graphs that each have their own separate set of sample values, similar to the ones that we just looked at. These 3 graphs will help drive a point home here. All right, so there's 3 new graphs here, and like the first set of 3, these have 4 sets of samples each. 2 of them are negative and 2 of them are positive. So we create a very simple fluctuation, negative, positive, for all 3 graphs. So for the first graph, we have negative 6, positive 5, negative 3, positive 4. And the middle graph, we have negative 12, positive 14, negative 6, positive 4. And with the third graph, we have negative 10, positive 27, negative 22, positive 5. These graphs don't seem that different from the prior three. Visually, the different amplitudes of each of the graphs, at least visually in a fuzzy sense, looks quite similar to the prior three. Each has varying amplitude, and the third one seems to be the largest of all three. Let's calculate the normal everyday average of each of the three sets of samples from each of these three graphs. Well, in this case, the normal everyday average of each of these graphs comes out to 0. That is, with each of the graphs, the negative values perfectly offset the positive values, and vice versa. They ultimately have equal weighting, and the average is that midline, which is 0. So something seems really wrong here if we're going to use this value 0 to represent the average power of the audio signal of each of these graphs. First of all, they don't all look like they contribute the same power to their output. Second, none of them looks like it's a 0 signal. There's definitely something audible here with each of these signals, so they certainly wouldn't be an average of 0. So the number being produced by a normal average isn't working for us. It's not reflecting anything about the power of these audio signals. So the big question is, what's going on here and how can we fix it? Well, there are actually two issues here, one more obvious than the other. The obvious issue is that the normal method of averaging fails us here because an AC signal, which includes audio signals, is a fluctuating signal. It's fluctuating above and below a 0 midline. It has both positive and negative values. And in calculating a normal everyday average on positive and negative values that fluctuate like that, the positive and negative values end up sort of canceling each other out in terms of understanding the true power of the overall signal, the true level. I mean, if you were to have a perfect audio signal with just as much above 0 as below 0, as we just saw with those three graphs, it wouldn't matter how large the amplitude values are, we'd always get an average of 0. Obviously, that's not something we're after. But even with an imperfect signal, as most audio signals are imperfect, meaning they don't have perfect symmetry above 0 and below 0, it doesn't really matter. There's still signal that goes above 0, positive values, and signal below 0, negative values, and there is some cancellation, if you will, in terms of using a normal everyday average to determine the power of that signal. A normal everyday average is just not going to help because it's looking for the average value within this range of fluctuation, which ends up being around 0, give or take, depending on how imperfect or perfect the signal is. So to determine an accurate average of the audio signal's true level or power or strength, we need to take some different approach. We can partially fix the problem by fixing the obvious issue, and that would be instead of taking an average of all the sample values directly, to instead convert all the sample values to their absolute value, that is, make all the negative values positive, and then take an average of all the sample values as positive value. In other words, perform a normal everyday average on the absolute value of all the samples. And you can see we're taking the average of the absolute value of the entire set of samples for each of the three graphs. And we can see that gives us for each of the three graphs the averages 4.5, 9.0, and 16.0. All right, that seems better. When we take the average of the absolute value of all the samples and we end up with these three averages, when we at least consider the relative difference between these three averages, we can see some correspondence to what each graph visually depicts. The smallest average is associated with the graph that seems to have the lowest amplitude. The middle graph has the middle value, and the graph that seems to have visually, seemingly the largest average overall amplitude has the largest average when we take the average of the absolute value of all of its samples. Even though this looks correct, it's actually not an accurate average. Why? The reason why the average voltage or amplitude is incorrect when we average it this way is because this way of averaging the samples of the audio signal omits an important characteristic of the audio signal. That characteristic is each sampled voltage's unique contribution as a factor to the actual power of the signal at the time when the voltage is sampled. Now, if that sounded like a mouthful, I fully agree with you. So let's get into a couple more details and see if some of this can gel a little more clearly. An everyday average or normal arithmetic mean won't work because it does nothing to incorporate within the average it produces what the average power of the signal will be over time. RMS does include that, and we'll explain why. Now, you might be wondering offhand, isn't a signal's amplitude level its power? And no, a digital audio signal or samples just by themselves really don't have power. But what they do represent is a mapping of the amplitude as it was observed when the signal was being sampled. And there is a correlation to a signal's amplitude level and how it changes over time, and how the signal itself will drive changes in power over time. In other words, there's a relationship between the voltage level or the amplitude level of a signal and the power of that signal over time. Now, when you just have samples, that power is not really realized. It's not happening when you just have samples in a file. But that doesn't mean the samples themselves don't have within them, within the changing amplitude levels that they represent, information that relates to how power will change over time when those samples are played back. Audio samples do have that information. And that's because the changing amplitude levels of an audio signal will affect the power of the audio signal in connection with how the amplitude changes. And we're going to discuss that in a second. Now, this may sound puzzling and unclear, so let's elaborate for a second. One of the main benefits of an RMS or an RMS average of a digital audio signal is that it is a value incorporating an accurate and useful average of what the audio signal's contribution to power or use of energy will be at the time that signal is played back. And there's a reasonable correlation from that signal's contribution to power or energy usage at the time it is played back and the average loudness of that signal as perceived by humans. Let's kind of recap here for a quick second. You have digital audio samples which represent amplitude level changes. And those amplitude level changes, while they do represent some change in level, they don't tell the full power or energy usage story as is. By performing certain calculations, i.e. by squaring those samples, you can cause them to represent their very own contribution to the use of energy or power at the time they're played back. And by having them include that by squaring them, you're also including within them their contribution to loudness as perceived by humans. So you can kind of see, while these things sound similar, amplitude, loudness, power, we're talking about different things. And there are relationships to these things, but their levels are different. The amplitude level is not directly the contribution to power that the signal will make when it's played back. But by squaring a sample, you arrive at a value that represents that sample's contribution to power at the time it is played back. And when you average the squaring of all samples, you're essentially averaging that contribution to power of the entire signal. You might ask, what is it about the RMS formula that allows it to include within it the average contribution to power and therefore to loudness that a signal will make once it's played back? How does it accomplish that? The key part of the formula that does this is the squaring of the audio samples in that first step of RMS, which is to square the values that are to be averaged. The squaring of the audio samples in this regard has a connection to fundamental principles in electronics. In electronics, there is Ohm's law and Joule's law. Don't let those terms intimidate you if you haven't heard them. If you're into electronics, you've likely heard of Ohm's law and Joule's law. But if you're not into electronics, no worries. We're just going to give a brief overview here of the formulas within Ohm's law and Joule's law that help us to establish that relationship to the amplitude being squared and the relationship of that to the power of a signal. Ohm's law And Joule's law. Ohm's law explains the relationship between voltage, current, and resistance. You can think of voltage as the potential push or pressure that makes electricity flow, like the water pressure that, if you turn the faucet on, will come out into the hose and cause water to flow through the hose. You can think of current as the amount of electricity that's flowing, like water flowing through the hose that we just mentioned. So electricity might be thought of, loosely speaking, as the pressure that drives that water to go through the hose, and the actual amount of water going through the hose might be thought of as the current. Resistance is how much the circuit opposes the flow of electricity. Now that might sound like a negative thing, but actually the whole thing with electronics and it being able to make things happen has everything to do with what happens when things resist. Or perhaps we could say when they resist and not resist. Lots of little ebbs and flows going on with our computers that drive them to do what they do. You can think of resistance as maybe when you bend the hose at a certain point to create a kink. That sort of makes it more difficult for the water to pass at that point in the hose. That point in the hose would be a resistive aspect of the hose at that point in time. Now that might be an example of something that doesn't seem very useful unless you're playing a prank on somebody. But let's take the hose example and say it's connected to a sprinkler. You've seen those sprinklers before, that like they're and what happens with those sprinklers if they're one of those sprinklers that's fully mechanical and driven by the water? And that's what I'm thinking of in this analogy. The mechanics in the sprinkler are driven by the voltage that's pushing the water, which is like the current. So it's driven by the current, but the voltage is connected to all this. It has that pressure which pushes the water through. The amount of water is the amount of water flowing through the hose and then in the sprinkler. Now the sprinkler, in order to do what it needs to do, needs to kind of hold back some of that water. It can't let all that water come through despite whatever the pressure is. In fact, the sprinkler has to have some ability to hold back the water no matter how high the pressure is. So the sprinkler can hold that back, and mechanically it can regulate the amount of water it will release. And at the same time, it can also drive its mechanical parts to do what it does. Like very often those things are going and they're actually moving back and forth. And all of that is driven without, well, it's ironic. It's driven without electricity, although we're using it as an analogy of electricity. But I think that makes it actually an especially good analogy. A sprinkler system is fully driven by that pressure of the water going through the hose, making it to the sprinkler system. The sprinkler system represents a form of resistance, of opposition to the water. But that opposition leads to positive things happening. That opposition allows the sprinkler to guide the water, to limit its release, and to ultimately guide it in a way so as to drive the mechanics of the overall sprinkler, to give that positive experience of watering the lawn, or providing something that you can run through in the summertime, etc., etc. Joule's law describes how electric energy converts into power. Loosely speaking, and relating to that analogy of the sprinkler system, Joule's law would tell you how much punch that flowing water has when it encounters the resistance of the sprinkler system. It's about the rate at which energy is being delivered and dissipated due to the resistance in the path. These analogies are imperfect, but you might relate this to the power driving a speaker during playback of an audio signal. When the amplitude of an audio signal increases significantly, let's say, at a certain point in time during playback of that audio signal, there is a direct relationship from the amplitude or voltage at that point in time of the increase and the power or force driving the speakers. And that relationship is not merely linear or one-to-one. It's actually more so, which we're about to get into right now. Given the principles of Ohm's law and Joule's law, there is a quadratic relationship between the power of a signal and its voltage, where the power of a signal changes quadratically with respect to its voltage. What this is saying is, given a voltage and its signal, if you double the voltage, the signal doesn't simply increase linearly 2 times, but rather the power of a signal will increase 4 times what it was before you doubled the voltage. Another way to say this is that for each doubling of the amplitude of a signal, its power quadruples. Ohm's law states that V equals I times R, where V is voltage, I is current, and R is resistance. Now you might be wondering why I is current. You can read up on the history of that. You can think of the I as standing for intensity of current. Also at the time, C was already in use for coulomb and capacitance and other things. So just remember intensity I, intensity of current. This equation states that voltage equals current times resistance. Let's just put that aside for a second and discuss Joule's law. Joule's law states that P equals I squared times R, where P is power, I is current, and R is resistance. This equation states that power, or you can think about it as the level of power, if you will, equals the current squared, or the current raised to the power of 2, times the resistance. One prominent fundamental thing folks learn when beginning to delve into basic electronics is that all of these formulas are related and can be reworked to find or use different values depending on the data you have available and what your goals are. And we'll discuss one example of that here. Recall that digital audio signals, a set of samples, are related to samples of changing voltage over time. This is what we've discussed in the past sections. The digital samples we have discussed are effectively born from measurements of voltage levels by an ADC over time. Even though samples themselves are not voltage levels, they nevertheless have value levels connected with the relative change in voltage levels sampled by an ADC over time at the time the signal was sampled. ADCs effectively map voltage levels to sample values, as you have seen. You can therefore think of audio samples as an abstraction away from the original voltage levels sampled by the ADC, or wherever those samples came from. The abstraction provided by audio samples allows us to work with those samples in a uniform manner within our DAWs and so on. Therefore, whether we have a set of voltage levels or samples, we effectively have amplitude levels one way or another. Or, in a sense, we always have voltage levels even if they're abstracted away from what those voltage levels actually were at the time the samples were created. The abstraction to samples still retains the relative distance that the voltages had from one another at the time of sampling. So this is all leading up to me saying, given that we effectively have voltage values or changes over time, whether they are direct values or whether they are audio samples that were born from those voltage level changes, in some sense we have a change of voltage over time, whether they be samples or actual explicit voltage levels. And because of this, we can use Joule's law and Ohm's law equations relating to voltage on audio samples just as equally as we can use them directly on voltage levels. So whether we have sample values or voltage values, we effectively have with both the relative changes in voltage over time of an audio signal. And given that, it would be helpful if we could use Joule's law, the one that expresses power in connection with current and resistance, if we could express that in terms of changes in voltage over time. In other words, can we use Joule's law, P equals I, or current, squared times resistance? Can we rework that in order to express what power is or how it changes over time with respect to voltage? And we can. Joule's law says that power equals I squared times resistance. That's power equals current squared times resistance. We want to replace I, current, with V, voltage. And so how can we do that? Well, if you guessed by using the information we have available to us via Ohm's law, you'd be correct. Now, before we move forward into that, let's talk a little bit about R, or resistance. You might be wondering what that is. And if you were, that's great, awesome. For the sake of using RMS on one or more audio signals, we can usually ignore more R, or resistance. Why do you think that is? You can think of R, or resistance, as the amplifier and speakers and all of that kind of stuff during playback. It's the resistance portion of the power equation, and it very often won't exist unless you're actually propagating the signal actually electronically to some sort of playback medium or something that has a resistance of some kind. In a sense, you can think of R, resistance, as the resistance part of the playback experience. When we want to compare audio signals, we assume R is constant or the same thing for all of those signals. For example, if we're comparing 5 different audio signals, we assume we're comparing them with respect to some medium, which would be the same for all of them, that we would be playing those signals back upon. I mean, largely speaking, there are many things you want to do with RMS values and the averages they ultimately represent of audio signals, where you don't really need to understand or use or consider that resistive load that would exist during the playback of those very signals. That's because there's a lot of value in just the levels themselves without getting into particulars of what kind of resistance will exist when they're actually applied and used to drive electronic equipment to reproduce the audio signal. This is not to say that R never has importance, but when it comes to a DAW, or let's say your own scripts or programs that you write to process samples and the audio levels they represent, when you're doing that and you need to use RMS to compare different levels of different audio signals or simply look at the RMS of one particular audio signal, considering R is largely unimportant for many of the valuable reasons why you'd want to analyze those levels. In other words, we really just don't need to consider R for many of the purposes where we need to use RMS to look at the average levels of an audio signal. Given this, you can imagine that R is 1, which means it would effectively do nothing in our equation. Or you can imagine it's the same for all comparisons. And so we effectively remove R from our consideration. Okay, so now let's go back to Joule's law and Ohm's law and how those relate to RMS. So Joule's law states that power P equals current I squared times resistance. And Ohm's law states that voltage V equals current I times resistance R. Notice how this particular Ohm's law equation is solving for V. V equals I times R. How about we modify that equation so that it solves for current, or I? If we do that, we would have the following. I, or current, equals voltage over resistance. Great, now that we have reworked Ohm's law to say I, or current, equals voltage over resistance, we know that current can be replaced with V over R. Since Joule's law uses I, or current, we can replace I in Joule's law with what Ohm's law tells us is okay to use as a replacement, which would be V over R. That would give us the following modified Joule's law equation. So we have P power equals voltage over resistance squared times resistance. Let's expand that out to remove the exponent. That would give us P power equals V over R times V over R times resistance. Now let's combine all those terms. We have P power equals V squared times R over R squared. Great, we see there's an R in the numerator and the denominator, which means we can cancel that one R out. That leaves us with P power equals voltage squared over resistance. There's an interesting property or characteristic in this viewpoint of power. Can you see it? We can see that power is quadratically affected by whatever voltage is present. If the voltage doubles, it as a factor ends up quadrupling power for any given resistance. Since we assume that resistance is the same in our discussion, regardless of which signal we're scrutinizing, what this generally means is that for any doubling of voltage, power increases 4 times. For example, if voltage is 2, 2 squared is 4. If we double voltage, so we take it from 2 to 4, 4 squared is 16. So you can see that 2 squared produced 4, and 4 squared produced 16. 16 divided by 4 is 4. So we see a doubling in voltage led to a quadrupling in power. This causes us to say that power is proportional to voltage squared. This relationship of power to voltage squared is important. If we have two audio signals whose levels we wish to compare with one another, before we compare those averages, as part of creating any averages we wish to compare, we need to ensure we properly account for the relative power one signal has with respect to another. RMS helps us achieve this by taking into account this property of power we just discussed. That voltage of an audio signal has a quadratic effect on that audio signal's power. Let's simplify this further. Let's use the proportional to symbol, which is this one shown here, where we can express that power is proportional to voltage squared. This can be thought of as ignoring resistance, because we assume it's the same for all of our audio signals, and to accentuate that power has not a linear relationship with voltage, but rather it has a whopping quadratic relationship with voltage. Do you see how power of a signal changes in relation to a signal's change in voltage over time? For some quote-unquote linear change in audio's voltage level, power at that point in time changes quadratically. Therefore, when averaging audio samples, you want to square the samples before averaging them, so that you're averaging not the original samples, but rather their contribution as a factor to power. This squaring is part of what RMS does. In fact, the S in RMS is square. With that foundation set, let's get back to RMS now and see it in action. So you can see that Ohm's law and Joule's law together help us understand that power or loudness at a particular point in time has a relationship with the amplitude level at that same point in time. Specifically, the amplitude level at that same point in time, when it is squared, represents the audio signal's relative contribution to its energy usage or power usage and its level of loudness as perceived by humans at that particular point in time. So you can see in RMS that first step of squaring all the values that you're calculating in RMS for. So in our case, that's squaring all of those audio samples. That one step, which is seemingly very simple, and in fact it is quite simple in a relative sense, but it ends up performing so much for us. That squaring converts all the values we're going to average to positive values, and it converts them into that sample's relative contribution to power, which is also its contribution to loudness. And because of the quadratic nature of that, given we're squaring those amplitude levels, the higher amplitude levels will actually have a significantly larger contribution to power and loudness in the overall average. And so in effect, squaring the amplitude values ends up giving the proper amount of weight to each sample with respect to that sample's contribution to power and therefore loudness when the signal is played back. After audio samples are squared, the mean in RMS will average those squared values, which is the same as averaging the signal's contribution to power and therefore its contribution to loudness for the entire signal being averaged. Finally, the root or square root of that average contribution to loudness sort of undoes the earlier squaring. It sort of removes that squaring inherent in that resulting average, which results in the final RMS value, which you can sort of think of as an average amplitude, but with some weighting that has it also embodying the average loudness and power of the entire signal or all the samples. And this is, of course, according to RMS and the basis for why it's used in that regard. And this is different than other methods such as LUFS and whatnot. So I'm not trying to discuss this as though it's the end-all be-all, but this is just the way that RMS works. One way to look at this is if you took the average of the absolute value of all audio samples, you would arrive at this average amplitude level. But that average amplitude level would include no weighting, if you will, relating to that same signal's average contribution to loudness or power. So RMS, in a sense, you can think of it as doing these acrobatics that have it taking all those amplitude values and putting them into this format that represents a relative contribution to a signal's power or a signal's loudness over time. And then it's averaging that relative contribution to power and loudness. And once it has that average, which is going to be weighted based on that quadratic effect of squaring those amplitude values. So in a sense, we're averaging those weighted values, if you will, and then we take the square root to turn it back into sort of an average amplitude level, but not really purely an average amplitude as though we average the absolute value of the direct audio samples, but rather this average amplitude that is derived from a proper averaging of the relative contribution to power or loudness of that same signal. So we sort of get this average amplitude that has built into it a proper weighting and representation of the signal's contribution to power or its loudness. And I find that's kind of cool because it's very simple on some level. Granted, it is related to Ohm's law and Joule's law. You could probably spend a whole lot of time delving into the derivation of those and whatnot, but still knowing some of those principles and seeing the simplicity of RMS, it's kind of cool. So now that we know how to calculate the RMS of samples, let's apply it to the samples of our three graphs. So first, let's start by squaring each sample. That gives us -6 squared, 5 squared, -3 squared, 4 squared. And that gives us the values 36, 25, 9, and 16. These values are not only the effective absolute value of all the samples, but the squaring means they now embody or include the original amplitude's factor of contribution to power. Now we calculate the average of those voltage, power, factor values, if you will. And that gives us 36 plus 25 plus 9 plus 16. Since we have 4 values, let's average that total by dividing it by 4. And that gives us 21.5. In a sense, this 21.5 is the average contribution to power of the overall audio signal. That's pretty cool, huh? Now we're not finished yet. Now for the last step, let's take the square root of that average value. The square root of 21.5 is approximately 4.64. You can use a calculator or a spreadsheet to figure that out. So our average amplitude level, which includes consideration of a signal's contribution as a factor to power, is 4.64. And if we take the same steps with the other two graphs, we end up with 9.90 and 18.29. We can see that that third graph is properly represented with 18.29, which is significantly larger than the second and first graphs. The end result of an RMS of audio samples is a reasonably good average of the contribution to power and therefore loudness those audio samples will have when played back. While RMS is not as elaborate as LUFS or LUFS, it has simplicity, ubiquity, familiarity, and a reasonable connection to loudness as perceived by humans. And all of this means that RMS is very useful for many different purposes throughout audio production and otherwise. Once you have the RMS averages from one or more audio signals, you can perform a number of interesting tasks. Of course, you can take the RMS average of one audio signal and compare it to the others. You can also do things like perform signal-to-noise ratio calculations, or perform noise floor comparisons, as we'll do later in this video, and much more. All right, that's it for this quick introduction to RMS, or root mean square. I hope you found it helpful. All right, with that understanding of RMS out of the way, let's get back to our walkthrough. So for this next walkthrough, I want to go through some noise floor recordings, which I captured using my Zoom F6. Now for these tests, I basically just used a dynamic microphone. The Zoom F6 input was set to mic level. The recording mode was 32-bit float mode, so there's no input gain trim to set or anything like that. The only level setting would be the knob relating to the mic level input. I had the Zoom F6 knob mode set to record level or rec level. That allows the knob to always be there there to adjust the so-called record level. Now, I believe in 32-bit float recording mode on the Zoom F6. That knob is some sort of post-ADC scaling factor. So in other words, after that floating point sample has been generated, which is well after the ADCs have already digitized the audio, I believe the Zoom F6 on board must do some sort of scaling at that point, using whatever that so-called rec level is set to. Now that's assumptive on my part, but all things seem to indicate that. Regardless, I set that knob or rec level to 0, which I believe is some sort of unity gain type of scaling factor, meaning they don't scale the sample beyond whatever its sort of default disposition is after they've finished processing the samples and they have a floating point value. But that is assumptive on my part, but it's not something that really impedes me going through the process of showing you what I'm about to show you. So what I did is I took this dynamic microphone and I wrapped it in a blanket with its switch on. It has an on-off switch, so I kept it switched on. So what I did is I took this dynamic microphone and I rolled it in a blanket. So I rolled it many times in a blanket, and then I just put it into a simple filing cabinet sort of box thing. It's like a plastic container, like a big Tupperware box that you can put files in. It's not necessarily a big soundproof thing or anything like that. Of course, wrapping the microphone in the blanket is isolating it from a certain amount of noise in the environment, and it's a pretty thick blanket, so I rolled it many times in that blanket, so it's kind of in the center of all that stuff rolled up. And then I just put it in this plastic filing box, and I was able to take that box and position it wherever I wanted to position it. And one of the places I used was a closet that is relatively quiet. So we had the microphone rolled in a blanket, put in this plastic file container, and then that container was placed in a closet, which is relatively quiet. So there was a decent amount of isolation from the environmental noises. To be totally clear, this wasn't a super high professional soundproof environment, and certainly noises could make their way into that box if they were loud enough. So even with all that isolation, I had to actually take multiple takes because I was dealing with a lot of environmental noise. And of course, anytime I'd press record, that's when the environment would start to want to make noise. And when that kind of thing happens, you have to basically reject that sample and move on to the next. After doing many of those, I ended up with a few that seemed to offer the best set of samples, and I extracted the data so I could load them into Excel and look at them in a spreadsheet format. And I was doing all this not with a specific mission. Now, one of my main reasons for doing this is the Zoom F6 is a fairly decent recorder, and I wanted to see how well it would perform in terms of a noise floor. And I also wanted to actually see the sample values firsthand so I could see, how low do these samples get. I wanted to see where those samples fit into all of the possible exponent ranges. I think one of the values of approaching things like this, even if you don't have a specific reason or need, but you want to be a little more savvy or understanding of your own equipment, and so you go down these avenues to kind of see what will crop up, what you'll run into. Long story, very short, I ran into a whole lot of anomalies, which essentially just improved my appreciation for sound professionals and what they do. And so it was one of those things that, after delving into so many details, there were so many different avenues of potential things I could present. I needed more time on some things. On some other things, I felt like, well, those could be good, but the noise floor things seemed better. And these noise floor tests that I'm going to show, they aren't meant to be a comprehensive noise assessment or anything like that. But there are some interesting points I want to show you about the nature of the samples that were captured when working to mitigate the noise in the environment. Okay, so with all that said, let's dive into this. So I'm going to do WinX, and I'm going to start the terminal up, and then I'm going to change into the demo directory into the repo that we cloned earlier as we've been doing. So I'm just going to work out of the same location here, and I'm going to recall the command line to activate our environment that we set up earlier. We can see that the environment is active because we can see the name of the environment as part of the prompt. With the environment active and with us having installed audioutil util in an earlier section. Audioutil should now be on the path, and I'm going to go ahead and type the help command for it, the audioutil-h. And you can see here there is a stats command. Now this stats command didn't actually appear in the help in the earlier sections because it had not been incorporated yet into the utility. So if you see that earlier part of the video and you don't see the stats command listed there, and just keep that in mind when I make a video like this. I may add a tutorial or I may update a command, and so there might be some little differences here and there. And usually if I make a little change like that, I'm not going to go back and redo the earlier section or whatnot. It's just too much stuff. So hopefully that makes sense. Let's recall our help command and let's type in stats and then -h, and we can see there's a whole lot of information here. We're just going to go and walk through it rather than read this help text, but I just wanted to show you can read some stuff here to learn about this particular command. A little caveat, a little insert regarding this command. This is something I created as part of experimenting with the overall libraries that are available and along with delving into the Zoom F6 noise floor tests. And I thought it would be fun to incorporate this particular command to help process the samples and get some data from them. And so I'm not saying that this command is the end-all be-all command or anything like that. I know there's a lot of wonderful tools out there or whatnot, but for those folks who want to get some hands-on on seeing samples be processed, or maybe they have their own ideas of things they'd like to do to process samples, I think by using some of the libraries out there myself to explore my own curiosities in that same regard, this is a good chance to kind of share that. And so if you have an interest to create some tooling to help process samples to get some values you're interested in or whatnot, you can see this if you want to, and I'm sure that there's plenty of other stuff out there that you can dive into. For me, it's just a great way to become familiar with this particular aspect of the space. So rather than us focus on all this help or whatnot, you can look at this if you want to. I'm just going to go through some steps here, and you can see those steps and follow along if you want to. And you can maybe create your own, noise floor samples and look at them. And I would say if you create your own noise floor samples, the one thing I'll say is when I first created some noise floor samples, I had a certain approach that I was taking, and then I quickly realized I needed to do certain other things and I had to retake the samples, and that happened across a few iterations. So like I was saying just a second ago, this particular world of audio analysis and delving into the samples and getting a good noise floor recording and all that kind of stuff, on the surface it kind of seemed relatively straightforward to me, but actually getting the right environment, setting up the right things, being cognizant of noise factors around you, including electromagnetic interference and that kind of thing. For me, there was a world that opened up there. I could actually make another video of things that had tripped me up and, things that created a puzzling find that I want to dig into that I still haven't dug into. I have a little action item on some of the things I ran into. That's not what this section's about. But what I'm trying to say is if you want to delve into your own device, never worry if you have the expertise or whatnot, because frankly, if you just dive in and start going into it, you might hit a few snags and this and that. But all of those things can be things that can help you build up an understanding of stuff as you delve into things and, learn about them and whatnot. So I just wanted to offer that point of encouragement. And if you think getting good noise floor tests and all that stuff is super easy, but you've never done it, let me just laugh a little bit and say, okay, well, maybe something I don't. I actually, walked into it thinking, hey, yeah, no problem. And, just even getting a good sample can sometimes be a challenge if you're in a noisy environment. But even beyond that, electromagnetic stuff is interesting. There's a couple interesting things. I might touch on some of those in this walkthrough. Okay, so let's proceed forward. Okay, let's clear the terminal window. Okay, I have my noise floor samples here in this directory. Now, these noise floor samples, they have a naming convention that's similar to the default in the Zoom F6 recorder, except I have renamed them to just make it clear that it's the F6, and I put some descriptive text here to kind of maintain a brief description of where it was taken and stuff like that. So we can see it says closet box slanket. Now, slanket is like one of those blanket things, that you kind of can wear like if you're sitting in front of the TV or that kind of thing. It's very sort of a little bit weighty, if you will. So it has a thickness to it, and it just seemed good to use with this. And it was small enough such that I could just roll the microphone out in it and get it into that box, as opposed to getting some big quilt or something that might not have fit in the box. So 0 dB here is just simply that front knob setting. And my assumption is that just simply means, hey, whatever the base sample is that gets created by the Zoom F6's processing of the ADC samples, don't scale it in any way, just leave it at its sort of default nominal value, whatever it happens to be, because they remove the trim setting. So there is no sort of pre-ADC gain setting or trim setting that gets disabled, unlike in the 24-bit recording mode where it's enabled. And that's something that's set per input via the menu system. So this 0 dB relates to that knob setting in the front, which just seems to me to be something relating to after the sample is created. So you can see we have 7 samples here. And let's just say, for example, that I just captured these. Now this comment like okay and best 0, best 1, outside noise, good touch button early. These are all my own little comments. Now what okay means and best means, that is something I specify even before I've reviewed the actual sample. So I write down on a notepad what I'm going to name it here. So after I take the sample, I might write down best, for example. And the reason why I might do that is I might not observe any environmental noise, and it might overall seem like it was a good sample. Now, sometimes I've found discrepancies when I finally review the samples in the file and I play things back or I look at the data. But until I know, I put my best effort description there. And even if something happens, I put it down there. Like sometimes I'll say like, oh, well, this thing occurred. And because the thing is wrapped up in a blanket, I don't really know if it affected the recording for it or whatnot. And I've had situations where what I wrote down was accurate and other situations where I wrote it down, but then later listened to the recording and I saw it was either impacted or not impacted. Like right here, I put good touch button early. And what I mean by that is the recording seemed good most of the duration, but near the end, my finger started resting on the button on the Zoom F6, and I forgot, don't do that. And so on that particular instance, I had rested my finger and it kind of, touched the button a little bit and then pressed in on it because I was waiting to get to a certain point before I finally pressed. So I rested my finger on that button. And little things like that where you touch the mic cable or you touch the Zoom F6, if it's near enough to the mic, the microphone can pick that stuff up. Now, when it's wrapped in the blanket and everything like that, whether it picks something up or not will really depend on probably where it's facing and how loud it is. I do know that the microphone cable can be, can really propagate sound vibrations. So if you like rub that cable, it can like transfer to the microphone. I've seen that. And so when I finished that one recording, I just took a note that I had touched the button too early. And that doesn't mean that it's a bad recording. It just means like, hey, there may be something to this. And of course, the numbers will tell me what actually happened. But if I have to apply my ears to kind of hear the recording to see if something came through, there's 2 interesting things with writing good notes as you do this. One is you may discover some things that seemed like they would be an impact were not. And sometimes that can vary depending on the particular context. Where was the noise? Where was the mic? And so forth. And I find all of this just helps to open up my mind to exactly what, I might want to consider here or what might be an issue or what might not be an issue. So I find a lot of this stuff is about diving into these details, experimenting with them, and kind of seeing what happens, what unfolds, what do you learn from the data that you see? What did things seem like when you were recording and what actually happened? And I have to say, actually, after finishing all this, I think I became a little bit more savvy about what to be aware of when I'm actually testing and setting up my environment. And I've come to appreciate this notion of actually listening to the noise of your own noise floor recordings, which I did a little bit. I actually didn't do that initially, but then I eventually, a couple days later, I started doing that because I noticed some odd anomaly, and it really opened my eyes up about something. And it was just one of those many things I had, sort of alluded to earlier where it was like, oh my gosh, all these different avenues of things I could share. And that's why I'm just starting with this sort of fundamental thing to just kind of give you a little bit of insight as to what my experiment, sort of what my journey was in this aspect of things. Because this is a little bit away from the format discussion, but I went into this area to sort of talk about the format in a certain way. And we'll get into that in a second. So let me clear the terminal window. And then I'm going to do audioutil stats, and I'm going to reference that same folder again again, and I'm going to type in star.wait, and then I'm going to press enter. Okay, so there's a whole lot of data that just came out here. Hey folks, just a quick insert here. Since this section of the video was created, the command's output format has been updated and some fields have been renamed or added. The details on the changes are discussed in the upcoming CSV section where the CSV column changes are discussed. And those column changes relate to the output field changes I'm referring to and showing you here. For now, I just wanted to show you the updated format just in case you ran the command against your own files and saw the new output format. Let's take a quick look at this. I'll say that I prefer the CSV output, which we're going to mostly focus on here. But first, let's just scroll up and have a quick look at this. So I'm going to scroll up here. Now we can see there's some fundamental data here, sort of like, what was the duration? It says 8 seconds. It shows the target sample start because you can choose like a window within the file to process. So you can specify like start at and stop at and so forth. It's showing us the RMS of all samples, the dBU of all samples, the minimum sample, and the peak sample or the max sample. The minimum sample might be positive or negative. It's basically checking the absolute value of all samples and looking for the one that's largest. It's looking for the one that's furthest away from 0.0. So we can see here that the minimum sample is quite small. It's negative 0.0000, many zeros, and then 956 and so on. And then we can see that the peak sample is still very small, but it is a little bit larger than the minimum sample. But our real focus here is going to be this RMS number and the dBU number, and maybe some of the other figures that the CSV will have. So we see the RMS of all values here, kind of a small number there. It's certainly not E minus 45, so we know it's not way down there by that subnormal level, but it's fractional in nature. And we can see that the minimum sample is a little more fractional. And then we calculate the dBU, which we can do if we know the RMS value. And we can see the dBU here is coming out as negative 130 and so on. We're going to get into some of these. And we can see it's like doing it for all the files here. So I'm going to scroll back down. Okay, I'm going to clear the terminal window. Now let's look at all this in a CSV. Okay, so in order to create a CSV, I'm just going to go and get back our command line here. And I'm going to add to this start at. Now what this means is let's start analyzing the files at 2 seconds into the file. And for stop at, I'm going to add stop at, and I'm going to say equals -2. And actually for this one, I'm going to say equals. It's fine to put a space there, but there are some cases where if you have a switch that has a dash, where I have to use equals, otherwise it thinks it's a switch. In this case, it's clearly a number, and so it would accept it with the space. But just FYI, in case you run into that. So we have start at 2 seconds and stop at 2 seconds before the end of the file. That's what -2 does. So you don't have to know what the time value is of 2 seconds before the end. You can just put -2. If you put a positive value, it actually has to be how many seconds into the file that you want to stop. If you put -2, it's how many seconds before the end of the file do you want to go to before you stop processing the audio samples. And then I'm going to type in -C for CSV and -output for, well, let's say noise floor. And I'm going to call this 01 for our first CSV. And then I'm going to type in .csv. Now, by the way, these audio samples are, my noise floor samples, and they aren't included in the walkthroughs. So if you want to follow through with some of this, you can create some noise floor recordings in your own environment. And they don't have to be pristine. In fact, if they aren't perfect, but they are relatively quiet, that should be good enough. You probably just don't want something with a lot of crazy audio in there. I mean, it's not that you can't, but if you want to create a couple sample recordings, you can walk through this walkthrough with me using your own WAV file. So a quick insert here. I wanted to mention, I actually didn't mention that the reason why I put start at 2 and stop at -2 is that there can be certain kinds of noise induced when you're starting the recording or stopping the recording. So long story short, I just decided I'm going to capture a clip that's long enough where I can exclude the first 2 seconds and the last 2 seconds and just deal with that core center part. And to me, that just eliminates this kind of maintenance noise relating to getting the recording going or stopping the recording. Now, there's nothing to prevent you from using the start at and stop at as you wish. You might want to examine just the center of the file or something like that. But this is what I'm doing. And I'm going to hit enter, and it's going to go ahead and process all the WAV files in that directory and create this CSV. I'm going to type in noi and tab to autocomplete, and then I'm going to hit enter, which should open Excel up, and it does. And Excel is asking me if I want to convert to scientific notation, and I'll say, yeah, go ahead and convert. And now I'm going to click to maximize the window. I am actually going to immediately Control A. That selects all, and I'm going to go to my little dark mode thing here that I do where I set the background to black, and then we're going to set the foreground, the character font color. I'm going to give a decently bright green here. There we go. Yeah, that should be good. And then let's get some borders in there. I did Control AA again, and I'm going to say none. Click here and choose something like a dark gray for the borders, and then choose outline inside. Okay, there we go. And then I'm going to click up here in the corner, and I'm going to double click to auto size the columns. All right, terrific. Let's look at this. Hey folks, since this section of the video was created, some columns have been renamed and added as shown here. The average samples column is now AVG ABS samples to indicate it is the average of the absolute value of the samples. The DC offset column, which was newly added, is the normal average of all samples, both positive and negative, so it reflects positive or negative bias. You can ignore this column, but if you're curious, you can run stats on the walkthroughs with symmetrical waveforms versus those which have lopsided waveforms. And when you do that, you'll clearly see the difference in the DC offset. We don't have a need for this column, and we're not going to cover it in any of the walkthroughs, but I wanted to mention it in case you were curious. The dBU samples column was renamed to dBFS _ RMS, and the calculation was updated to appropriately use 1.0, or the equivalent of 0 dBFS, as the denominator or reference point in the dB calculation. The new column ordering is as shown here. The new ordering allows for easy selection of columns receiving similar formatting, at least in the way I tend to format them, which I assume some others may do as part of following along. So one of the first things I like to do when I load a CSV in is I like to go and save that thing to an XLSX file. Or if you're using another spreadsheet program, you can do whatever you're doing there. And then I click on save. And so now we have an XLSX file instead of just a CSV. And the XLSX will retain all the formatting and all the good stuff like that, where the CSV won't, of course. Okay, let's go through these columns. The first thing I actually like to do is format the columns. So I'm just going to go through that so you can kind of just see what I like to do. So I'm kind of used to this CSV format because I've been working with it for a while. So basically sample values and things like that, I like to use scientific notation with precision out to 9 places. And for things like time value or dBU and whatnot, I use fixed point and I have those out to 3 places. So what I'll do is I'll select things like time values like seconds here, for example, and here's another one which is a time value, and here's another one that's a time value. And let me scroll over here. I believe we have some other, here's dBU samples. So with all of those columns selected, what I do is I right click and I choose format cells, and then I'll go to number, and then 3 for 3 places. And then I'm going to click OK, and it'll just shorten those up. And then the next thing I do is I go through and I click on anything that's like a sample. So min sample and peak sample and average samples, and then there's RMS samples, and I right click here and choose format, and then I choose scientific notation, and then I'll put a 9 in the decimal places column, and I'll click OK. And it gives us this nice scientific notation with a little bit of precision shown there. And let me just scan over here and see if there's any other columns that I want to format. No, I think that's good for right now. All right, with the columns having some initial formatting, let's go through these columns really quickly. Okay, so the first column is a file number. That's just the numeric numerical order in which the file was processed by the utility. The second column, audio seconds, is how many seconds of audio was considered out of the overall file. So you can see here it's about 4 seconds, here it's about 3 seconds, and so on. Audio start second is the second within the audio file where the audio samples that are being examined began. So we specified start at 2 seconds, and so we can see that 2 seconds was indeed used. Oh, it looks like I forgot some time values here in terms of formatting. Let me actually just fix that really quick. And we'll say number, and we'll say 3. And I'll say OK. That's great. Let's click up here. And so the audio end trim sec is how much audio was trimmed from the end of the entire audio file. And we can see here that 2 seconds was trimmed out. And the total amount trimmed was 4 seconds. Did we specify any scaling on the command line? There's an option there to scale the audio either up or down. And since the scaling is 1, it means nothing was scaled. The scaling factor is multiplied to each sample. So if it's 1, it ends up not changing any of the samples because the scaling factor is 1. The min sample index is the array index of all samples where the minimum sample was found. The min sample second is the time at which the minimum sample was found. The minimum sample itself is in this column right here. And even though this is a 32-bit floating point file, this column here will display the minimum sample as a 24-bit sample in case that's of interest. And it shows it in hex as well. This min sample float details is not currently being used by us, so it shows up as blank. And then we have the same thing for peak. So we have peak index, peak second when that occurred, and then the actual peak sample itself. We have the equivalent 24-bit sample value for peak, and we have it in hex as well. Scrolling over, we can see that there's this peak sample float details. Basically, the float details is you can specify an option to have it output floating point details for the sample as well. That will show the sine, the exponent, and all stuff like that. Since we didn't specify that, it just keeps it blank. And then we have the average of all samples within the designated period. And then that average is shown in 24-bit and 24-bit hex. And then we have RMS. Now the RMS of all the samples is in that column RMS samples. And the dBU, which is derived from the RMS samples, is shown here in this column dBU samples. Now you'll see here there are 3 empty columns: RMS noise floor, RMS derived pure, and SNRDB. We'll get into that in a second. Right now they're blank because we didn't give the tool any data to calculate those columns. And then we have the sample rate, the bit depth, the number of channels. Right now only mono is supported with this. And then of course the file names. Now for our noise floor test, the first thing I'm interested in learning about is which one was the quietest, which one had the lowest overall amplitude. And I'm going to do that based on focusing on either the dBU column, which itself is derived from the RMS samples, or I might just focus on the RMS samples. So I'm just going to put my cursor here just to make sure it's in the spreadsheet, and I'm going to go here to the data tab. I'm going to click got it on that message, so it's not there. I'm going to go up here and click on the data tab, and I'm going to choose to sort. And I want to sort by, I'm going to choose RMS samples, and I think I'm just going to leave it at that, and I'm going to click OK. And it is now sorted by RMS samples. And you can see that the dBU samples follows the same sorting. Again, dBU samples is derived from the RMS samples. So we can see that the lowest value here is this one right here, which is this one that says best number 1. It's file number 8, this number 8 right here. So it wasn't necessarily the first one or the last one. It's just whichever one happened to pick up less noise or less environmental stuff going on, including EMI and things like that. And that happens to be this one here. Now, since that's my lowest that I have, let's say for now, I just kind of want to use that as a basis of the lowest that I'm aware of. And I kind of want to look at the other ones relative to that. Now, that's not a real noise floor test because essentially all of these include mic noise and whatnot. Generally, if we wanted to get some kind of noise floor basis, we would do so with like a dummy load on an XLR jack, something like that. So I'm going to click in this file name here, and I'm going to type in Control-A to select all and Control-C to copy the file name to the clipboard. I'll then hit Escape to cancel the edit on that that field, and I will click the X to close Excel. Back here at the command prompt, I'm going to recall our command line here, and what I'm going to do is I'm going to type in -H so we can see help, and then I'm going to immediately bring the command line back and get rid of that -H. I'm actually going to move this thing above the keystroke window here, and I'm going to raise this thing up here, and then I want to show these -NF options here. So this is where I'm going to specify the path to a file that's going to act as the noise floor basis. So I'm going to paste in actually that file name that we just got from the Excel spreadsheet, and I'm going to type in before that -- and let me actually enlarge this a little bit. Hopefully that'll make it a little more readable. And I'm going to type in -- -NF-path, and then the path is here. And let me just hit tab on this file. Whoops, excuse me. Let me just hit tab on this file, and it's not finding it. Oh, I know. I have to actually go and specify the full path. So let me just do that, and then we'll put this here, and let me just make sure that path is there. Yes, it is. And let me bring this window out a little bit wider. And then I'm going to specify the same start as I did with the other files. So I'm going to specify start 2 seconds and nf-start equals -2. And let me just go put equals here just for consistency. Now, what this is doing is it's telling the utility, go and read in this noise floor basis file. And when you read this thing in, use its RMS value as the basis for some noise floor that you want to use to compare with the other samples. So the idea is if I have some base noise floor and I have some other recordings that add something on top of that base noise floor, that this would help me see the difference between those two. So what this NF start and NF stop is doing is similar to what the -- start at and stop at do. We're just saying, hey, get the noise floor data from this file that I'm designating and do it for this range. So I'm telling it to trim the 2 seconds from the start, trim 2 seconds from the end, and just use that core data to calculate the RMS and to use that as a basis to compare with the other files that are going to be processed. Now, this file that we're specifying as a noise floor basis is also one of the files that's going to be processed by the utility. Now, it doesn't have to be, but in this case, it's okay for me to do that. So I could have some basis noise floor file that I created some time ago, and I might just choose to use that to perform some comparisons against some files that I captured, let's say today. But in this case, I captured all these files, and I'm just using the one with the lowest overall level as this basis for the quote-unquote noise floor. Oh, so one thing I'm going to do before I hit enter here is I'm going to go back to here, and I'm going to change this to noise floor -o2-.csv. So that way we don't overwrite the existing CSV file, and I'm just going to create a brand new one. With all that done, I'm going to press enter, and what it's going to do is it's going to load up the noise floor basis. Oh, it hit some error, and what was it? Oh gosh. Oh, you know what? I specified the wrong command line option there. I'm sorry. Actually, what I'm going to do is I'm going to clear the terminal window, and I'm going to bring back the command line, and I have 2 NF starts here. So let me backspace over this, and let me type in the word stop here, and let me hit enter. Great. So to be clear, it processed all the WAV files just as it did before. But before doing that, it went to read in the noise floor file that we specified. And it did some processing on that to get the base RMS to use as the quote unquote noise floor, which it would use to compare with the other files. Now let's type in noise tab. And that's the first CSV we created. I'm going to hit tab again to get to O2. And I'm going to hit enter on this CSV. And I'm going to say, yes, go ahead and convert, and I click on that. And rather than have you sit through me making this dark mode, I'm going to go and format this really quickly. Hang in there and let me get this formatted. So I'm going to say Control AA, and we're going to say dark. We're going to say a nice bright green for the font. We're going to go here and choose borders. We're going to choose none. Then go here to color, choose this dark gray, then choose outline inside, and OK. I'm going to click up here and double click, and it will resize those columns. And I'm going to do a save as to an Excel file and click save. And then I'm going to go and format the columns as we did just a second ago. So I'm just going to do this really quickly here. I'm going to choose all these time values here. This one, where is the DBU one? There we go. I think those are all the ones. is that I like to have with 3 decimal points. We're going to go to number, up arrow to select 3, and then I'm going to go here and just double check. Here's a sample, peak sample, average, RMS, pure. I think that's it. I'm going to right click, choose format, scientific, and we'll press 9 here and click OK. Terrific. And now I'm going to go back over here, click up here. All right, so I formatted all the columns in the same way that we did last time. And I want to go scooch over here to the end. And we can see that there are now values in the RMS noise floor, the RMS derived pure, and this SNR dB. I'm actually going to click on here to right justify that. So everything's kind of flush over here. And we can double click on that column, maybe make it a little bit bigger. Okay, so the first thing I want to do is to click somewhere in this data, and then I'm going to go to data and sort, and I'm going to scooch down here to select RMS samples. I'm going to click OK, and it's going to sort everything by RMS samples as we just did before. Now notice when it does that, this first item here is still the lowest one. That's the one that was lowest before. And this is also the one that we specified as the noise floor basis. And you can see here that the signal to noise ratio from itself to itself is negative infinity. And that's just simply because it itself is that reference point. But you can see it also shows a signal to noise ratio from the other files to itself. Now, again, this is not a true SNR in the sense of talking about the device's noise to the actual live signal that you're recording. But one thing this can show you is some relativeness between this top one here and these lower ones here. And you can actually see this actually increases as it goes down. This first one is the basis for the noise floor, which in a sense sort of means like that bass noise, which could be that of just the recorder without any microphone. But in this case, since that recording had a microphone connected, it actually includes not only the noise of the device, but the microphone noise. But it's still useful to use as a basis here just to show these figures and to show this in this spreadsheet. If I had an XLR jack with a dummy load or something like that where I could capture a good noise floor capture from my device, I would use that. I don't have that right now. And I tried using a 150 ohm resistor I have that is not really like the highest quality resistor. It works great for certain circuits, but I think, it was creating more noise than I was getting with an actual real test. So we're just kind of using that first file with the lowest overall RMS as our sort of pseudo noise floor basis, if you will. But for right now, I wanted to show something about the data we have here and some of the stuff we've been discussing regarding the 32-bit float format. So RMS noise floor is the RMS noise floor, and RMS derived pure is like the pure signal, and it's not really a true pure signal. That's why it's called derived pure. So this RMS pure for each line is the base noise subtracted out from the noise added by that particular line. So since this line is that base noise, when we subtract that out, we end up with 0. But for the other ones, the derived pure basically subtracts out something that is almost equal to it, but maybe a little bit less. And so basically this and this are used to calculate the signal to noise ratio dB. So in this case, actually, the SNR being lower is actually better if you are comparing one noise measurement to another, because in this case, everything is invalid signal. And the closer all that invalid signal is to one another is actually better, because it means there will be, in theory, more distance from that to the actual signal that is valid, that you want. So when we see this next one up here, we see that it has a -20, and we see it gets higher as we go down. That's because the distance from these other ones, which we assume it's all noise floor at this point. So if more noise is being added by the items lower down in the list here because we sorted it, it means that the base noise and the noise of the subsequent of the items that are further down on the list are further apart, which means that noise is spread out more. So in this particular case, this SNR figure is actually better if it's lower, or if you're talking about the relationship of a valid signal to some noise floor measurement, a larger SNR would actually be better in that case. So anyway, our focus is not these, and there's plenty of tools out there. You probably have stuff that helps you look at this stuff. But this is just something I was playing around with, and I kind of just wanted to show it as we get to the core of why we're going to be looking at this spreadsheet. Okay, so one thing I like to do with these spreadsheets here is when I'm not using anything, I'm going to hide the columns I don't need. And so right now, I don't really need these columns that have the seconds and the scaling information and the index and this thing, and I'm going to right-click there and just choose hide. As well, I'm going to take this empty one and hide that, and then there is another one here. This is index and seconds. I'm going to hide that. And we have another empty column here. I'm going to hide that. Yeah, and I kind of know the sample rate and everything is 32-bit, so I'm actually just going to go ahead and hide those as well. And we end up being able to show everything here on one screen. This average 24-bit samples here. I'm actually just going to bring this in here because we don't really need to see that as well. I'm going to justify hex values so that they're right justified. And actually, I usually like to use consolus, so I don't know why I didn't change that before, but let me change it to consolus. And then we can bring this down a little bit so it'll fit in here. Okay, great. Now, one thing you can see here is look at these minimum samples here in floating point. You see it's 3.57 times 10 to the negative 13. But you can see the equivalent of that min sample in a 24-bit sample is 0. And you can see all this detail here in floating point, but you can see that it's not represented here in all of these happen to be 0. It's not that it's bad. It really depends on what's getting lost down there. Now, this is all noise. The fact that it's all resolved to 0 is not bad. But the point being is that there's a lot more detail that can be maintained at these lower levels and beyond with the 32-bit floating point format. Now, I want to go back over to the command line. I'm going to clear the terminal window. Now, remember in an earlier section, we created that range detailed spreadsheet. So I'm going to open that up now. So I'm going to type in range tab. Oh, that's the CSV. I'm going to hit tab again. There's the Excel spreadsheet. Let me hit enter. And there it is. It's loaded up right here. So I'm actually going to click on a field so I can get rid of that selection. And I'll just go up here to the top and I'll click there just to put the cursor up here in the A1 corner. And I want to jump back over here to look at these minimum samples. Look at the lowest sample that's here. And you can actually see here's a peak sample. Okay, so that's the highest one. And then the average one is 1.872 times 10 to the negative 7. So that's basically dot and 6 zeros and then 1872, da 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 da. That's the average. But if you look at the minimum, that means the smallest one that was encountered in that particular file. It's some number times 10 to the negative 13, which is basically a decimal point and 12 zeros, and then this number that you see here, 357, and so on and so on. So what I want to do is I want to go over here to this file and I want to look to see where that sample here, that minimum sample, would fit into all of this range here between 0.0 and 1.0. So in order to do that, we'll just focus here on the low end. I'm going to highlight this low end column and I'm going to ask for a little bit more precision with the scientific notation. So I'm going to set this to 9 so that it matches the other Excel spreadsheet. And you can see it widens that up and gives us some more detail. Not required, but I just wanted it to look similar to the other Excel spreadsheet and the way we formatted those sample numbers there. So if I go back over to that other file, we're looking for 3.57 and E-13. Let's go back over to range detailed and see if we can see an E-13 anywhere in here. So we see there's a bunch of E minus this and that, and here's E-13 right here and right here. So let me just highlight both of these. And let's see if I can make that a little bit bigger. There we go. So I think it's, what is it? 3.57, some odd numbers, and E minus 13. And so we see 1.1 E minus 13, 2.2 E minus 13, or 2.2 times 10 to the negative 13. So 3.57 times 10 to the negative 13 would fit between this line here and this line here. We therefore surmise that that number resides somewhere in this area here. Now remember, this is a noise floor recording on the Zoom F6, and that's in 32-bit float recording mode. So there's two ADCs there, and it's able to capture these very low signals. So we have this dynamic microphone connected to the Zoom F6, so there is a little bit of microphone noise added by that, but based on my cursory review of things, it's relatively small. And if you go over here, you can see that this dBu figure is close to the area of the F6 specifications. Keeping in mind, my tests here and gathering of data is quite ad hoc, and it's not the same thing that they perform, but we're in the right ballpark in a sense. In other words, the microphone isn't adding some extraordinary, crazy thing to the noise for the purposes of our discussion here. I'm not saying, that you're going to like this microphone or something like that. Okay, let's go back over to the other spreadsheet. So keep in mind that this sample here, this 3.57 times 10 to the negative 13, this thing in this min sample column right here. And keep in mind, all these are fairly close to one another for all these. I'm just picking the lowest file because that has the lowest number. And so here I am recording with the Zoom F6 with a dynamic microphone, and I'm trying to see what is the lowest value that gets produced by this thing. And we see this lowest value is 3.57 times 10 to the negative 13. Well, we go back over here and we see that that's going to fit in somewhere around here. Well, let's actually zoom this spreadsheet out and let's see what we have above that. So, excuse me. So I actually want to select this line right here. And what I want to do is drag this up here to select all of this right here. So visually we can see it. I want to step back out now from this spreadsheet so we can see the bounding box is all of this. And let's actually zoom in now and look. You see the biased exponents here. We discussed these in a prior section. They go from 0 all the way down here where I end that selection to about 86. But there's many other exponents here above 86. We have this right here at 87 all the way up here to 127. And again, it goes higher than 127, but we're focused on that range that caps off there at 1.0 or 0 dBFS. So if I zoom out now with this other part of this selection, the part that goes towards the higher end, let me just try to see if I can fit this all in here. You can see that that audio file, which has all samples below 1.0, and the lowest sample is down around this area here. You can see that that audio file recording something at a very low level is only going down this far, meaning there is a lot more space below that lowest point for that one particular recording that is available to represent detail in audio at lower levels. And I just personally found that very interesting because this all started out because I was wondering if the F6 could naturally on its own, in some way use the subnormal range, but it doesn't even get close to the subnormal range in a number of tests I ran. And this may be a known thing, but it was something that I just really wanted to explore for myself. And not only that, though, it's very far away from these lower ranges. Forget about subnormal, just even the lower exponents down. I tried some tests with like the switch off on the microphone. I tried a floating input. I also tried my own 150 ohm resistor test. The point I want to make here is that this stats utility, even though it has some of the stuff that I was showing about the noise floor basis and whatnot, what it also does is it gives us some data on the samples that are used in the file, aside from dumping all the raw samples, which we showed a little bit of that. But the stats command is going to give us some data here about the file. And you might have an audio app or tool or something that already does that really, really well. This was just a little endeavor I went down to have something as part of the tutorial that you could use to glance at the stats in a WAV file. And for me, I just wanted to quickly get hold of that min sample and kind of see, what its value value was. And I really wanted to see, like, look, if I don't have anything that I'm recording, it's just the microphone or the switch is off, or it's a floating input, or any of these things, I couldn't get very far down at all in the range of floating point values. It was very, very far away from the subnormal range, and it left a whole lot of exponents. I mean, if you look here, we go back to that 357, and I think that was around this line here. I mean, you just look at all these exponents, exponent from like 87, 88 or something, all the way here, all this space, not even touched by that recording that was recording the lowest possible sounds it could record, and nothing else really. So anyway, all this is meant to build on the past discussion regarding this range detailed spreadsheet and how you can take some sample data like from this noise floor spreadsheet, or I should say quote unquote noise floor spreadsheet, but it nevertheless shows some pretty low recordings with minimal noise. I'm not saying it's the lowest possible with the Zoom F6, but from what I've seen, that dynamic microphone really isn't adding a lot of self noise. So we're fairly close to the Zoom F6 noise floor, and the way that's coming through in the recording, I'm not seeing anything dip down below what I see in there. Now, I don't know if I use some sort of dummy load, how much further down it's going to be able to go. My guess is not really that much further down in the range. Now, once a 32-bit float recording is created and it's brought into a DAW, and the DAW has to perform various calculations, or you're doing various kinds of manipulation to the audio samples, whether the DAW needs to use low ranges and how low it needs to go and whatnot would be up to, what you're doing and what the DAW does to process the audio samples. I know for myself, I can actually force going to lower level values by using a DAW to lower that amplitude. And that was really the only way I could find to actually induce very low exponents. I didn't see them created at all with the Zoom F6 in my recording tests. And my guess is this may be something just very well known by people who use these recorders, and what they generally know will be the range that's used by the stuff naturally coming from the unit. But I found it kind of interesting to find that lowest sample value in a 32-bit float recording from the Zoom F6, practically to that noise floor, maybe not quite, but practically there, being so far above and so far away from those lower ranges. And I just wanted to share that. So speaking of that test that I just mentioned, let me actually just show that to you really quickly. So let me actually minimize this spreadsheet. Let me minimize this spreadsheet, and we're back at the command line. I'm going to clear that terminal window, and I'm going to go into our walkthroughs directory where all of our WAV files are located that we created as part of those walkthroughs. And I'm going to paste in that file name, and I'm going to hit tab so we see that it's a valid file, and that PowerShell sort of kind of prepends that directory indication. And then I'm going to press enter on this to just get the stats on this file. And we can see here what the minimum sample is and what the peak sample is. So remember, those are based off absolute values. Since the thing goes from negative 0.5 to positive 0.5, the peak is 0.5. So what I want to do here is I want to type in -H so we can see the help here. And you can see that there's an option up here called scaling factor. So I'm going to copy this switch here, and I'm going to clear the terminal window. I'm going to bring back the previous command line, get rid of the help, and I'm going to type in the scaling factor, and I'm going to type in 1.0, which is no change, and let's see what that does to this particular file. We can see that the file is unchanged. Now let's go and bring that back, and let's type in .5 to scale the file in half. And we see that the file is indeed scaled in half. So now what I'm going to do is I'm going to scale this to 0, 0, 0, like 1. Something like that, just something that will make it much smaller. And we can see it went from an exponent on RMS of 10 to the -1 to 10 to the -6. And how about right now we focus on this minimum sample, which is at 10 to the -6, so 4.9 times 10 to the -6. Let's actually add some zeros to the scaling factor. So I'm going to add quite a few, and I'm going to hit enter. And you can see that now that minimum sample has 10 to the -19. So we're effectively scaling down those samples in the floating point file, and we see that the statistics for the file are scaling down as well. So I'm going to add some more zeros here. So I'm going to type in more zeros. And basically, I get to a point here where I see 0 and infinity here. This one's at 10 to the negative 31. And I know that I want to get to about 10 to the negative 45. So I'm going to type in some more zeros here. That's maybe too many. Let me just take that back a little bit. Yeah, everything is 0, so I've gone too far. Let me actually bring it back. Okay, so let's scale up. 1, 2, 3, 4. There we go. Now, if we take this number right here, this minimum sample, 5.6 times 10 to the negative 45, and we bring up audioutil and interactive, and we paste that number in there, we see that the biased exponent is 0. So that sample, which has been very, very scaled down, is in the subnormal range now. So the minimum sample, when it's scaled down that much, goes into the subnormal range. What this is kind of highlighting is it took a lot of scaling down to get into that subnormal range. That should give a little sense of the kind of magnitude reduction that's required there in order to get into that range, and it should also give you a sense that there's a lot of room in there to represent values of relatively decent precision. Let's quit interactive mode. Let's bring back this command line again and hit enter. It should be the same thing. I didn't change it. So we have our 10 to the negative 45 on the minimum sample. Let's add 1 0 there to go just a little bit further. And of course, no can do. We've gone to 0. Okay, so now let's start up Audacity. And let's start up Explorer here by doing Explorer and period. And that opens up Explorer where our walkthroughs are located. And the file that we just used was 04. So let's bring Audacity here and let's find that 04 wave file. We don't want the Python file. We want the wave file. And we're going to load that right into Audacity here. And then we're going to go to the Effect menu and choose Volume Compression and Amplify. I have to do Control A to select all the audio. I'm going to do Effect, Volume Compression, Amplify, and bring this slider all the way down. Click Apply. We see the visual waveform has effectively disappeared. We're going to actually go here and choose to export this audio. We're going to export it to the computer. And we're going to go here to our PowerShell window and copy this demo location where the walkthroughs are located. I'm going to go back over here to Audacity and I'm going to type that path in here. And I think I'm going to get rid of this long file name and just type in export1.wave. I'm going to choose here to select 32-bit float, and I'm going to keep everything else the same so it looks good. And now I'm going to choose to export. Now we're going to go over here and we're going to recall that stats command, and I'm going to get rid of this scaling here, and let's just go all the way back here. I probably could have just typed the command, sorry about that. And there's export 1. So I'm going to hit enter here, and actually let me bring back the original command line without any scaling whatsoever. And there we go. Okay, so there's our untouched audio file. We can see that 0.5 is that minimum sample. Let's go look at the export 1 that we just exported from Audacity after reducing the file. And we can see that the minimum sample is now at an exponent of 10 to the negative 3, where before it was at 10 to the negative 1. And you can kind of see how this is similar to the scaling that we did with just the stats tool. Now, the stats tool is not writing audio samples. It's just doing that for the sake of showing us what the scaled statistics would look like. But in this case, we literally told Audacity to scale down all those samples by using its quote-unquote amplify effect. So if you go here to Audacity, and I won't bore you with this, but you can actually go in here and continue to choose to amplify things down. So I can go here and choose to amplify this down, and I can click apply, and I can go here and choose to export this and export to computer. And I'm going to say export 2 here, .wave, 32-bit float, mono, etc. Click export. And now I'm going to go here and recall the command line and change this to export 2. And we can see that it has diminished the file even more. We're now at 10 to the negative 6. Now you can continue doing this with Audacity, and it will keep going to those lower possible exponents there in the 32-bit float format. And that is really the only way I've seen so far to get get any of the audio applications to naturally, if you will, even though we're kind of forcing something in an odd way here. Normally you wouldn't do this in a DAW, continue to scale something down like that. But it is the only way I have found to really go down and use those lower levels in the 32-bit floating point range. Those lower level samples generally don't seem to be used in my testing of things. I haven't been able to record anything much lower than like 10 to the -7 or -8 or something like that. Now granted, I haven't used an XLR test dongle with the 150 ohm resistor and all that stuff, so maybe there's a way to get an even quieter recording. I tried with the microphone switch off, and I tried floating, as well as the live mic test that we've discussed, and those did not get very far down as we discussed earlier. So I just thought this was an interesting point to make, and for folks that are kind of interested to get an understanding of samples, if it's been kind of a mystery for them, part of the goal of this video is to sort of focus on those formats from the bits and bytes perspective, but also to maybe, show some of these scripting things in Python and some of the libraries that are available that allow you to do things with these samples as you wish. And I feel that that can help alleviate some of the mystery that might exist for some folks that don't work in this area regularly. And I think part of that also too is if you're able to do an exercise like this where you're iteratively exporting something from Audacity and then you're gathering statistics from that file that you export and you see what it's doing to the samples, it's not necessarily some amazing thing on one level, but on another level, it might be a little bit of an aha for some folks where they might just be like, oh, okay, yeah, it might not be like the most important thing in the world, but sometimes it can be helpful to get your hands on not only some code or something and see it manipulate the samples, but then also kind of relate that to the DAW's behavior when, let's say, it's scaling some samples. Additionally, too, any of these things which are scaled down, when we scale them back up, they really scale up and maintain that precision. It's not that there isn't any quantization error on digitization of the analog signal. There always is, but it's less with 32-bit float than it is with 24-bit integer. And the flexibility of the range of 32-bit float makes it really well suited for operations that need to scale and do other kinds of manipulation to samples in a way where a lot of range is needed to move the values around without completely losing them or clipping them. And there's plenty of room above 1.0 with the 32-bit float range, and there's plenty of room below the lowest I've seen recorded so far with at least this Zoom F6, such that I can fully see there's lots of, headroom. There's lots of, foot room? Headroom and foot room. There's plenty of foot room. So anyway, that concludes this little walkthrough of stats. Just something I wanted to throw in here. And I think toying around with the DAW to export something and kind of look at the samples, it can be a little fun. Okay, that's it for this section. All right, that's it. I hope you enjoyed this video. If you like this video, I hope you'll click the like button. It's free to click the like button, and it can really help this channel grow, and it can help the algorithm share this content with other people. And there's a subscribe button below, and it's free to subscribe. And by subscribing, you will really be helping this channel grow. You'll be helping the algorithm recommend this channel and its content to others. Most importantly, subscribing means you'll get notifications when new content is posted. And after you subscribe, you'll see a bell icon. And if you click that bell icon, you'll be getting more immediate notifications for any new content posted. And all of that is free to do. Beyond subscribing, if you really got something from this content and you really want to support this channel and its content, you can look in this video's description for other options to support this channel. All right, that's it for now. Please be well, and I'll see you in the next video.